when you think about the forces that rule our universe, gravity feels like the undisputed heavyweight champion, right? Like it keeps your feet glued to the ground. It dictates planetary orbits. It literally holds galaxies together.
Oh, absolutely. It feels big and undeniable.
Yeah, it feels absolute. But what if I told you that you are entirely ignoring a force that is so unimaginably powerful, so violently explosive, that gravity is practically a rounding error in comparison?
A literal rounding error.
Yeah. I mean, a force that is a billion times stronger than gravity, yet it's just hiding in plain sight, perfectly disguised. So today we're doing a deep dive into a famously brilliant physics lecture.
Right, specifically focusing on its foundational opening chapter, chapter 201.
Exactly. And this chapter basically proves the universe is run by a completely different set of rules. We are going to unpack the terrifying true power of electromagnetism.
And honestly, it is one of the most rewarding scientific texts you can read, mostly because it forces you to completely rethink reality.
It really does.
Like, the author takes these concepts that scientists spent centuries agonizing over, and he reframes them to show that the everyday world you interact with is actually this delicate, almost miraculous balancing act.
Okay, let's unpack this, because I was reading the first section, and I honestly couldn't wrap my head around that initial comparison to gravity. A billion times stronger.
That's a lot of billions.
It's insane.
Right.
That number is so huge, it basically loses all meaning. It sounds like something a kid makes up on the playground.
Right, it does. But to ground it in reality, you have to look at the massive caveat the text provides. You know, unlike gravity, which only ever pulls things together, this electrical force involves two different kinds of matter.
Positive and negative charges.
Exactly, positive and negative. And like charges violently repel each other while opposites attract.
So instead of just this universal pull, you have this cosmic tug of war happening everywhere, all the time.
Yeah, and if you had a handful of just positive charges or just negative charges, the repulsive force would scatter them across the universe instantly.
Wow.
Instantly.
Pretty much. But because the universe provides an evenly mixed bunch of positives and negatives, they pull together. They form these impossibly tight, fine mixtures.
So the resulting attractions and repulsions balance each other out.
Almost perfectly, yes.
And that perfect balance is why we don't even notice this raging force field we are walking around in every day. The text actually has this thought experiment to illustrate the scale, and I want you, the listener, to picture this.
Oh, this is my favorite part.
It's so good. Okay, imagine standing at arm's length from a friend. If just 1% of your protons and electrons were imbalanced, like if you had just 1% more positive charge and your friend had 1% more positive charge.
Just 1%.
Right. The repulsive force wouldn't just push you apart. It wouldn't just be enough to lift the Empire State Building or, I don't know, Mount Everest.
Not even close.
That tiny 1% imbalance would generate a force capable of lifting a weight equal to the entire Earth. It's staggering. It completely redefines how we view solid objects. I mean, think about a skyscraper swaying in a hurricane but not snapping.
Right. Why doesn't it just break?
It isn't because steel has some magical inherent stiffness. That stiffness is literally the electrical force. It's the raw power of those incredibly strong attractions, holding every single electron and proton in that steel precisely in its proper place against the wind.
Okay, looking at it from that perspective, down at the atomic scale, the distances are so small that this perfect balance actually starts to fray just a little bit, right?
Exactly.
Like a negative charge on the edge of one molecule might be a microscopic fraction closer to a positive charge on another.
And that tiny residual mismatch is what creates the chemical forces that hold all biological and physical structures together. It is the foundation of chemistry.
That is wild. But you know, following that logic inward leads to a really fascinating boundary in physics. If positive protons and negative electrons are attracted to each other with earth-lifting force, why don't they just collapse right on top of each other?
Right. Why doesn't the mixture just pull itself into an infinitely dense, tight little ball?
Exactly. If the attraction is that strong, what's stopping them?
Well, the answer lies beyond classical physics. You have to look at the realm of quantum mechanics specifically, the uncertainty principle.
Okay, the uncertainty principle. Break that down for us.
So the rules of the quantum world dictate that as you try to confine an electron into a smaller and smaller space, like dragging it right up against a proton, its momentum has to increase.
It starts moving frantically.
Yes, exactly. That relentless quantum motion acts as an invisible barrier, keeping the electrical attraction from crushing the charges any closer together.
It's almost like trying to force a hyperactive dog into a tiny travel crate. Like the harder you push, the more it just violently bounces off the walls, pushing back against you.
That's a great way to put it. That quantum bouncing is what gives atoms their volume. But zooming in even closer to the nucleus itself presents a much more explosive problem.
Because the nucleus is densely packed with positive protons.
Right. And based on everything we just established about, like, charges repelling with terrifying force, the nucleus should instantly blast itself apart.
So what keeps it intact, there has to be some kind of incredibly strong glue holding those repelling protons together in that tiny space.
And that's where the text introduces the short-range nuclear force. It is a non-electrical force that is actually even stronger than the electrical repulsion.
Okay.
But the critical detail, the thing that defines our entire world, is that this nuclear force only operates at an extremely short range. It falls off dramatically the moment particles aren't right next to each other.
Oh, I see. So the nuclear force is like a super strong adhesive, but it only works if the pieces are literally touching.
Right.
Whereas the electrical force works over much longer distances.
If we connect this to the bigger picture, think about a really large atom like uranium,
Right.
which is packed with 92 protons.
That's a lot of protons packed together.
It is. And the nuclear glue is mainly just acting locally, between a proton and its immediate touching neighbors. But the electrical repulsion is acting globally across the whole nucleus.
Meaning every single one of those 92 protons is furiously repelling every other proton.
Exactly. As the atom gets bigger and bigger, that electrical repulsion just keeps stacking up and multiplying. Meanwhile, the nuclear glue can't reach across the atom to hold it together.
Wow. So in a uranium atom, that balance must be incredibly delicate.
Very delicate. The nucleus is essentially teetering on the edge of structural failure. It's practically ready to fly apart from that massive accumulated electrical repulsion.
So if you just tap it lightly by, say, sending in a slow-moving neutron,
The structure fractures.
Yeah.
It breaks into two distinct, positively charged pieces.
and the moment they are separate pieces, the nuclear glue can't reach between them anymore. But
Exactly.
the electrical repulsion is still there.
Oh, it's very much still there. So they fly apart with unimaginable violent energy. That is what we call an atomic bomb.
That is deeply unsettling.
Yeah, we refer to it as nuclear energy, but the profound realization the text offers is that it is really electrical energy. An atomic bomb is just the raw, terrifying power of electrical repulsion finally being released the moment it overcomes the nuclear glue.
That is just wow. Okay, so if this monstrous electrical force is hiding everywhere, animating the strength of steel, holding our chemistry together, and powering atomic weapons, how do physicists actually map it out?
Well, we can't rely on physical gears and strings to transmit this force, obviously.
Right, so we need a new set of rules to explain how it operates across empty space. Which brings us to the concept of fields.
Yeah, because trying to calculate the individual force every single electron exerts on every other electron in the universe would be mathematically impossible.
Your calculator would just melt.
Exactly. So instead, physicists use electric and magnetic fields.
Yeah.
You can visualize these fields as invisible arrows assigned to every single point in space, showing which way and how hard a charge would be pushed.
And the brilliant simplification the text highlights is the superposition principle.
Superposition.
Which basically says, if I have a bunch of charges over here creating a field and another bunch over there creating their own field, I don't have to invent a new kind of math to see what happens when they overlap. I just add the arrows together.
It keeps the universe calculable. But to truly understand how these invisible fields behave, the text asks us to visualize two very specific properties, flux and circulation.
The analogies the author uses for these are so helpful because otherwise it's just pure abstract math, right?
Oh, completely.
So let's look at flux first. Imagine you blow an invisible spherical bubble in space. Flux is essentially measuring the net breadth or field pushing out of that bubble.
Right. You just calculate how much of the field is pointing straight outward minus anything pointing inward.
It's the net outflow.
Exactly. It perfectly captures what a field is radiating into the world. Circulation, on the other hand, requires visualizing motion along a path.
Right, and the text's liquid analogy is brilliant for this. Imagine you are aggressively stirring a cup of coffee until it's spinning really fast.
Okay.
Now, imagine you instantly freeze all the coffee solid except for a 1-inch hollow ring of liquid right around the inner edge of the mug.
So just that outer ring is still liquid.
Right. The momentum of that unfrozen liquid trapped inside the ring will cause it to just keep spinning and circulating around the cup. That net rotational motion is circulation.
Having these mental models for flux and circulation is crucial. But historically, scientists struggled immensely because they took analogies like flowing liquids or spinning gears way too literally.
They couldn't let go of the physical stuff.
Exactly. In the 1800s, physicists desperately wanted mechanical explanations. They wanted to know what the invisible strings were made of.
The text mentions James McCulloch in 1839. He literally worked out the correct mathematical rules for how light behaves, and the scientific community entirely rejected his work.
They told him, "This is just abstract math. Light has to vibrate in something. Give us the mechanical gear wheels."
Give us the gears. It's so funny to think about now.
It was a massive historical detour. Attempting to invent invisible physical gears or mechanical jellies in space fails completely the moment charges start moving rapidly.
Yeah.
The profound leap was accepting that the abstract math, the fields themselves, described by flux and circulation, is the fundamental reality. There are no gears.
Okay, so now that we know how to measure this invisible force using flux and circulation, what are the actual rules of the game?
This is where we get to the four pillars.
Right, the four laws of electromagnetism that James Clerk Maxwell brought together to describe almost everything we experience.
And these four equations are a masterclass in elegant logic. The first law simply states that the flux of an electric field coming out of any closed bubble is exactly equal to the net charge inside.
So more charge inside means more electric field radiating outward.
Exactly, which makes perfect intuitive sense.
And then the third law is the magnetic equivalent, but with a major twist, right? The flux of a magnetic field through any closed bubble is always exactly zero.
Because magnetic monopoles don't exist. You can't have a north pole sitting by itself radiating a magnetic field outward into space.
It always has a south pole.
Right. Magnetic fields always loop back on themselves. Every arrow that points out of the bubble eventually loops back and points inward, so the net outflow always perfectly cancels out to zero.
Okay, so those first two handle the static, stationary stuff. The second law is where electricity and magnetism start talking to each other.
This is where it gets fun.
It says that if the flux of a magnetic field is changing over time, it physically creates a circulating electric field around it.
Yes, and this is the mechanism behind almost all the electricity power in your home. Inside a generator, you spin a massive magnet. The magnetic field changes, and that changing field physically pushes electrons around a loop of wire, creating a current.
But the fourth law, the text points to this as Maxwell's absolute masterstroke.
It really was.
It states that the circulation of a magnetic field is caused by electric current flowing through a loop. We knew that part. But Maxwell added something crucial. He said it's caused by electric current plus, the rate of change of the electric field.
That single addition revolutionized physics. Maxwell realized the math was fundamentally broken without it. And the text uses this incredible thought experiment with a capacitor to prove why.
Yes, I want to spend some time on this capacitor experiment because it's mind-bending.
Oh, it really is. Go for it.
Okay, imagine a simple circuit with a battery and two flat metal plates that are very close to each other but not touching. There's a physical gap of empty space between them.
Okay, so a broken circuit, essentially.
Right. When you turn it on, current flows down the wire, hits the first plate, and stops. Positive charge builds up on one plate, and negative charge builds up on the other.
Right, and since the circuit isn't fully connected, the current only exists in the wires, not in the empty space between the plates.
Exactly.
Yeah.
Now, we know that a magnetic field circulates around the wire where the current is flowing. But here is the trick Maxwell realized. Imagine drawing an invisible bowl-shaped surface.
A mathematical surface.
Right. The rim of the bowl wraps around the wire, but the deep part of the bowl dips perfectly between those two disconnected plates. The surface of this imaginary bowl passes only through empty space. No physical electrical current is piercing that bowl.
Right. And if the magnetic field depended solely on physical current, as the older laws stated, the magnetic field should instantly vanish the moment your imaginary surface passes through that empty gap.
Which is ridiculous. Moving a mathematical surface around in your head obviously can't make a real physical magnetic field disappear from the universe.
Exactly. The field had to still be there. Maxwell's genius was realizing that as the charges pile up on the disconnected plates, the electric field bridging the gap between them is getting stronger and stronger.
It is changing.
Yes. And that changing electric field acts exactly like phantom physical current. It bridges the gap and generates the magnetic field perfectly.
The implications of that phantom current are what give us our modern world, honestly.
Absolutely. What's fascinating here is that if you combine that realization with the second law, magic happens. A changing magnetic field creates a circulating electric field, and a changing electric field creates a circulating magnetic field.
They act as a self-sustaining feedback loop. They basically leapfrog each other.
Yeah, a changing electric field spawns a magnetic field, which is also changing, so it spawns a new electric field further out, and so on. They detach from the wire entirely and propagate through the vacuum of empty space without needing any physical charges at all.
That self-perpetuating, leapfrogging dance of fields is an electromagnetic wave.
That is literally the explanation for light.
It's breathtaking. The reason you can see anything at all is just electric and magnetic fields constantly triggering each other as they fly across the room.
It really is beautiful when you think about it.
But this brings up a massive question for me. We just spent all this time establishing that magnetic fields are created by moving currents or changing electric fields. What about the permanent magnet sitting on my fridge?
The fridge magnet.
Yeah, there's no battery in it, there is no wire, there is no current. So where does the magnetism come from?
It is entirely natural to view permanent magnets as some separate magical phenomenon. But the text explains that in materials like iron, the magnetism is generated by the electrons themselves.
Oh, really?
Yeah, not just electrons orbiting the nucleus like tiny planets, but the electrons intrinsically spinning on their own axis.
Oh, so each individual spinning electron acts like a microscopic loop of electrical current.
Precisely. The quantum mechanics of it are incredibly weird, but essentially, in a piece of iron, countless numbers of these spinning electrons spontaneously line up so their axes point in the exact same direction.
And their tiny individual circulating spin currents add together.
Right. They amplify each other until they create a permanent macroscopic magnetic field that you can feel with your hands.
So a magnet is just a batteryless electromagnet running on synchronized quantum spin. That is so cool.
It is.
But the text doesn't stop there. It sets up a scenario next that completely broke my brain. Let's say you have two electrical charges moving through space side by side, parallel to each other at the exact same speed.
Okay, and because they are moving charges, they act like parallel electrical currents. And the reals say parallel currents create magnetic fields that pull them toward each other. They experience a magnetic attraction.
Right. Here's where it gets really interesting, though. Imagine you get into a spaceship and fly alongside those charges at that exact same speed. You look out your window. From your perspective, those two charges are just hovering there.
They aren't moving at all relative to you. They are completely stationary.
Yes. If they are stationary relative to you, there is no current. And if there is no current,
There's no magnetic field.
how can a fundamental physical force of nature just vanish into thin air simply because you drove your car next to it? It makes no sense.
This is the ultimate aha moment of the entire chapter, and honestly, arguably one of the greatest realizations in physics. Magnetism is not a separate, standalone force.
It's not.
No, it is an illusion created by your perspective. Fundamentally, magnetism is just a relativistic effect of electricity.
Relativity, like Einstein's theory of relativity. I always thought relativity only mattered when you were dealing with black holes or flying at close to the speed of light.
Usual, yes.
But electrons moving through a standard copper wire are not moving fast.
They are incredibly slow. The text points out that the average drift speed of an electron moving down a wire to power a light bulb is about 0.01 centimeters per second.
That's nothing.
A common garden snail moves faster than the electrons in your power cords.
So relativity says we have to apply a tiny mathematical correction based on how fast the object is moving compared to the speed of light. If the electrons are moving at a snail's pace, that fraction must be impossibly, absurdly small.
It is practically microscopic. The relativistic correction for an electron in a wire is roughly 10 to the power of negative 25.
10 to the negative 25?
Yeah, that is a decimal point followed by 24 zeros before you get to a 1. It is a ghost of a fraction.
But that makes no sense, though. How can a force that is 10 to the negative 25th power of normal electricity be strong enough to physically yank a compass needle or, like, spin a massive industrial motor in a factory?
It all comes back to the cosmic tug-of-war we talked about at the very beginning of the deep dive.
The balancing act.
Exactly. The wire has the exact same number of positive protons as negative electrons. The incredibly violent, earth-lifting electrical forces we described earlier are actively balancing each other out to a degree of precision greater than 1 part in 10 to the 25th.
Oh my God, so what does this all mean? The scale of that cancellation is staggering.
They cancel each other out so flawlessly, so completely, that the normal electrical force effectively vanishes from our perspective, and when the massive electrical forces perfectly cancel out.
The only thing left over is that microscopic 10 to the negative 25 relativistic correction.
Exactly. That tiny mathematical remainder becomes the dominant force. The only reason we can feel magnetism at all is because the true, terrifying power of electricity is perfectly cloaked by its own balance.
That completely shifts how you view reality. Magnetism is just the tiny, relativistic exhaust of perfectly balanced electricity. Wow.
It's beautiful.
Zooming out to the historical scale, the text makes this incredible point about humanity's journey with these forces. You know, the ancient Greeks only knew about two highly specific, weird phenomena.
Right, rubbing amber to pick up scraps of paper and finding special lodestone rocks in the region of Magnesia that mysteriously attracted iron.
They were seeing electricity and magnetism, but they were completely blind to the connection. For thousands of years, that was the extent of human knowledge. Because the universe's perfect balancing act successfully hid the true power of these forces from us.
We were just observing the tiny, frayed edges of the balance.
But once we finally pierced that veil, once Maxwell combined flux, circulation, and his phantom-changing electric fields into a cohesive map, it changed the trajectory of our species almost overnight.
This raises an important question about how this knowledge changed humanity. We went from rubbing amber to designing massive power grids, connecting roaring waterfalls to 10,000 engines in 10,000 different factories hundreds of miles away.
It's unbelievable.
Today, we use antennas to detect the impossibly tiny, synchronized dances of electrons in a metal rod, allowing us to transmit high-definition information across the globe instantly. We've even realized that the biological processes of life itself are just complex electromagnetic interactions.
The author actually makes a massive historical claim at the end of this chapter. He states that if you look back from 10,000 years in the future, the most significant event of the 19th century won't be political or military.
Right.
He says the American Civil War will pale into provincial insignificance compared to Maxwell's discovery of the laws of electrodynamics.
When you measure history by how humanity interacts with the fundamental machinery of nature, it's a difficult claim to argue against. Maxwell gave us the source code to the universe.
It really is awe-inspiring, but before we wrap up this deep dive, the text leaves us with one final, unresolved mystery. A little something for you to chew on after you take your headphones off.
Oh, this is a good one. We spent all this time talking about how positive and negative charges balance each other out and how, charges violently repel.
Yeah.
But consider the electron itself.
Right. An electron is a single particle that is entirely 100% negative charge. And as we established, charges repel each other with terrifying, world-shattering force.
So if an electron is a physical object made of stuff, and all of that stuff is entirely negative, every single part of the electron should be violently repelling every other part of itself.
So what holds a single electron together?
Exactly.
Why doesn't it just instantly blast itself apart into a million tiny, negatively charged fragments? Does it even have physical parts, or is it just a perfectly dimensionless point in space?
As the author admits, this paradox has caused endless difficulties in trying to form a complete, cohesive theory of electromagnetism. It is a question that, to this day, fundamentally breaks our understanding and remains completely unanswered.
It's a humbling thought to leave on. We can map the invisible fields that propagate light. We can harness relativistic illusions to run our modern world.
You can do all of that.
But when we zoom all the way down to the tiniest, most fundamental building block of that entire system, the scaffolding disappears into a mystery we still haven't solved. Keep wondering about it, and we'll catch you on the next deep dive.
Welcome back, the learner, to another deep dive. Usually when we talk about physical reality, there's this underlying expectation of, tangibility.
Right, something you can actually touch.
Exactly. Think of architecture. You see a brick wall, you can measure its dimensions, you can drag your hand across it, and you just point and say, there it is.
Yeah, it's solid. It's measurable with standard, everyday tools.
But then you step into the world of advanced physics, and suddenly that solid wall it dissolves. Today, we're looking at a landscape that's completely invisible.
Which is always a fun shift in perspective.
Oh, totally. We're talking about fields, forces, and, flows of energy that literally shape our entire universe. But you can't actually hold any of them in your hand.
It's the hidden machinery of reality.
Yeah.
And to even begin to see it, you need a highly specific set of conceptual tools.
Which brings us to our mission today. We're exploring a famously dense yet totally fascinating chapter on the differential calculus of vector fields.
Ah.
Specifically, we're pulling from Volume 2, Chapter 2 of the Feynman Lectures on Physics. And our goal here is to decode the invisible mathematical language that physicists use to describe the universe.
It's a great challenge for this deep dive, because this material is essentially the bridge between pure mathematical theory and the messy, chaotic reality we actually live in.
Right, we're taking the leap from abstract, terrifying-looking equations to an intuitive picture of how heat, electricity, and motion actually work. And we are going to do it without drowning in unreadable jargon.
Good luck to us, eh?
Hey, we can do it. And if you're someone who loves those sudden aha moments, this material is an absolute goldmine, because once you grasp the grammar of this language, the physical world starts to look completely different.
It really does.
But before we even touch the math, we have to talk about the mindset. We have to start with the philosophy of physics itself. There's this incredibly powerful quote in the source material from the theoretical physicist Paul Dirac.
I love this quote.
It's so good. He said, "I understand what an equation means if I have a way of figuring out the characteristics of its solution without actually solving it."
What's fascinating here is the sharp contrast between how a mathematician thinks and how a physicist thinks. Yeah, mathematicians or people approaching this with strictly mathematical minds often fall into a trap when they study physics. They look at something like Maxwell's equations for electromagnetism and they think, well, the equations are all there is.
Right.
If I understand the equations inside out mathematically, I understand the physics inside out.
I mean, that sounds logical on paper. Why wouldn't that work?
Because the real world is far too messy. It's endlessly complex. Physicists absolutely need heuristic models. Things like drawing imaginary field lines or using concepts of capacitance and resistance.
They need pictures in their head.
Exactly. They rely on these to build a feel for the physical situation. A true physical understanding is actually quite unmathematical at its core. It's imprecise, it's inexact, but it is entirely necessary to get a grip on what's actually happening.
Wait. So the physicist is intentionally being imprecise. They're just guessing.
Well, not guessing exactly, but building an intuition. But here's the paradox of the physicist's mindset.
Right.
At the end of the day, those heuristic models aren't perfectly accurate for all situations.
Yeah.
There's only one precise way to present the laws of nature, and that's by means of differential equations. They are the fundamental truth.
So they have to live in both worlds.
Yes, the physicist lives a dual life. They use the intuitive models to feel out how a system behaves, but they ultimately rely on the differential equations to prove it.
Okay, let me try to frame it like a game of chess.
Sure.
If you approach chess purely like a mathematician, you memorize exactly how every piece moves. The knight moves in an L shape, the bishop moves diagonally. You know the rules, the equations.
Right.
But knowing the rules of chess doesn't mean you understand the flow of the game. A grandmaster, the physicist in this scenario, looks at the board and intuitively feels the tension. They feel the control of the center without calculating every single legal move.
That's a great way to put it.
But if a dispute arises, they still have to prove their move is legal based on those foundational rules.
That is a perfect analogy. The intuition guides you, but the equations are the bedrock. And to build that physicist intuition Dirac was talking about, we first need to define the basic playing field. Quite literally, we need to talk about fields.
Let's do it. The source defines a field simply as a quantity that depends on its position in space. And it breaks this down into two main types, starting with the simplest, which is scalar fields.
Right, the scalars.
A scalar field is characterized by a single number at every point in space. The text uses an example of a solid block of material that's been heated at some places and cooled at others.
So if you measure the temperature at any specific coordinate inside that block, x, y, z, you just get a single number, say 75 degrees. That's your scalar.
The temperature itself is the scalar field. And to visualize this, the text asks us to imagine drawing imaginary surfaces through all the points in the block that have the exact same temperature.
Like a 3D topographic map.
Exactly. Kind of like contour lines on a topographic map that show elevation. But here they show heat. They call these isothermal surfaces.
And that single number tells you the state of things right there at that exact point. But the universe isn't a static photograph.
No, things move around.
Right. Things move, energy flows. That requires our second type, which is vector fields. A vector isn't just a number. It has a magnitude, which is an amount, and it has a specific direction.
The text mentions the velocity of atoms in a rotating object as an example of a vector field. Every single point in that object is moving at a certain speed, but also in a very specific direction, depending on where it sits relative to the axis of rotation.
But the example that really brings this to life conceptually is heat flow. Let's go back to that solid block with the hot and cold spots.
Okay, the block.
We know intuitively that heat flows from the hot areas to the cold areas. That flow is a directional quantity. We call the heat flow vector h. And the definition the source gives is incredibly precise.
Let's hear it.
The magnitude of this vector h is the amount of thermal energy passing per unit time, per unit area, through an infinitesimal surface at right angles to the flow.
Okay, let's unpack this because
Yeah.
this is where the mental visualization is crucial. Temperature, the scalar is the, what is it right here? But the heat flow, the vector, is the where's it going and how fast.
Yes, exactly.
And to calculate that flow accurately, the angle of the surface you're measuring matters immensely. The source brings up this beautiful little geometry problem.
The tilted surface.
Yeah. Imagine a tiny imaginary surface, completely perpendicular to the flow of heat. All the heat blasts right through it. But what happens if you tilt that surface?
Well, if you tilt the surface, the exact same amount of heat is now spreading over a larger mathematical area.
Makes sense.
The text shows that if you have an angled surface, you calculate the flow through it using the cosine of the angle between the flow itself and the unit normal vector.
Wait, remind us what the unit normal vector is.
The unit normal is just an imaginary arrow pointing straight out of your tilted surface. So the heat flow through any surface element is exactly equal to the vector h dot produced with that surface's normal vector.
It's just pure geometry describing thermal energy. It's beautiful.
Yeah.
But this brings up a massive question.
What's that?
Now that we can visualize these fields, the static temperature sitting there and the dynamic heat actively flowing, how do we measure the way they change from one point to another? Like, if I move an inch to the left inside that block, how much hotter does it get?
This is where we hit a significant conceptual hurdle. Let's say you want to take the derivative of the temperature with respect to the x-axis. You want to see how fast the temperature changes as you move purely along x.
Right. Pretty standard calculus.
Mathematically, you can do that all day. But
Yeah.
physically, it's practically useless on its own.
Because the universe doesn't have an x-axis painted on it.
Precisely. The physical laws of the universe cannot depend on how we humans arbitrarily choose to orient our coordinate system. If you turn your head, your x-axis changes, but the physics of the heat flow remains exactly the same. The universe doesn't care about your graph paper.
I love that phrase. The universe doesn't care about your graph paper.
It really doesn't. So a derivative, like the partial change of t with respect to x, isn't a scalar, and it isn't a vector either. It's just a fragment of an idea.
But the text proves something amazing here. It shows that if you take the three spatial derivatives together, the change in x, the change in y, and the change in z, they transform together perfectly when you rotate your coordinate system.
Yeah, they follow the exact same geometric rules as a physical vector in space.
And this realization gives birth to a brand new, fundamentally important vector. We call it the gradient of the temperature, written as a little upside-down triangle followed by a t.
The symbol is called del, and the physical meaning of this gradient is deeply satisfying. The gradient vector points in the direction of the steepest uphill slope of the temperature.
So if you're standing inside that block of material, the gradient points exactly toward where it gets hotter the fastest.
But here is the true mathematical magic. The text asks, why does it have to be temperature? The transformation rules work no matter what scalar field we happen to be differentiating.
Right, it could be anything.
So we can strip the t away completely, we abstract the gradient away from the temperature, and we're left with just the upside-down triangle by itself, the del operator.
I love the quote from James Jeans in the text. He says, "We leave the operators hungry for something to differentiate."
A hungry operator.
Yeah, I picture del as this mathematical Pac-Man just floating around in the abstract realm. By itself, it means absolutely nothing. It's just an operator. But it's hungry. It's waiting to eat a scalar or a vector to suddenly gain physical meaning.
And we have to be incredibly careful with how we feed this hungry operator, because in operator algebra, the sequence matters immensely.
How so?
If you put the t in front of the del, so it reads t del, you haven't solved anything. You just have an operator multiplied by a scalar. It's still completely hungry.
I see.
But if you put the t to the right of the del, so del operates on t.
Chump. Exactly. The operator is satisfied, and it instantly becomes a physical vector, the gradient representing the spatial rate of change.
Okay, so we've mapped a static field. We've figured out how to find its slope using the gradient. But earlier we talked about moving fields, like heat flow. A static slope isn't enough anymore.
No, we need a way to measure the flow itself.
Right. What happens when we feed our hungry operator different mathematical meals? The text outlines three main combinations, the big three of vector calculus.
We already covered the first one. Combine del with the scalar field, and you get the gradient, which is a vector.
Right. But what if the operator eats a vector?
There are two ways to multiply vectors. First, you can take the dot product of del and a vector field, like our heat flow H. This produces a scalar field, a single number at each point. This operation is called divergence.
I need to pause here because this is where a lot of physics texts lose people. They just drop the word divergence and move on. What does the dot product of a derivative actually mean in real life? Think of it as measuring whether a specific point in space is acting as a source or a sink.
Okay, like water.
Exactly. Imagine a bathtub. If you place a point right at the faucet where water is blasting outward, that point has a positive divergence. It's a source of flow.
Makes sense.
If you place a point right over the open drain where water is rushing inward and disappearing, that point has a negative divergence. It's a sink.
That makes perfect sense. Positive divergence is an outward burst. Negative is an inward collapse. What's the second way to multiply vectors?
The cross product. If you take the cross product of Dirichlet and a vector field, it produces a brand new vector field. This combination is called the curl.
And again, let's ground this. What does the curl physically look like?
Imagine dropping a tiny microscopic paddle wheel into a flowing river. If the water flows perfectly uniformly, the paddle wheel just drifts along, it doesn't spin, the curl is zero. But if the water is flowing faster on the right side of the paddle wheel than on the left side, the wheel starts to spin. The curl measures exactly the rotation or the spin of the field at any given point.
Okay, so divergence is the faucet or the drain, and curl is the paddle wheel.
If we connect this to the bigger picture, the payoff of inventing this peculiar hungry operator is absolutely staggering. The text points out that using just these combinations, divergence and curl, you can write the entire classical theory of electromagnetism in 4 elegantly simple lines.
That is just wild to me.
It's Maxwell's equations, 4 equations that describe light, electricity, magnetism, radio waves, the Wi-Fi you're probably using to listen to this, all of it, and they're just del dot E, del cross E, del dot B, and del cross B.
Here's where it gets really interesting for me. This sophisticated vector notation using del, it completely strips away all the human scaffolding.
What do you mean?
Like, we don't need arbitrarily chosen X, Y, or Z coordinate systems clogging up the equations anymore. It reveals the pure physical truth underneath. The text also shows this with the differential equation for heat conduction.
Ah, yes. The equation is H equals negative kappa times the gradient of T.
Right, and kappa is just a number representing the thermal conductivity of the material. But what I absolutely love is the minus sign. Why is the minus sign there?
Because of the direction.
Exactly, because the gradient, mathematically, points up the temperature hill towards the hottest part. But heat physically flows down the hill from hot to cold. The math flawlessly aligns with the physical reality.
It does. And if doing this once yields Maxwell's equations and the fundamental law of heat conduction, it forces us to ask the next logical question.
Which is?
What happens if we let the hungry operator eat twice? What if we take second derivatives?
Oh, man. The source lists all the possible ways you can combine these operators twice. You can take the divergence of a gradient, the curl of a curl, and so on. But it zeroes in on 2 specific combinations that mathematically, universally, without fail, equals 0.
These are the magic zeros. The first one is that the curl of a gradient is always 0.
Wait, let me picture this physically based on the analogies we just built. A gradient is a slope, right? It's the steepest path uphill.
Right.
So if I'm walking continuously uphill, it's physically impossible to walk in a looping circle and end up exactly where I started while having only gone up. You can't have an endless staircase. So the curl, the spin, or the loop of a pure uphill gradient has to be 0.
That is a brilliant way to visualize it. If a field represents a pure slope, it cannot have a vortex. Now, the second magic zero is that the divergence of a curl is always 0.
So what's the analogy there?
Think of your paddle wheel again, or a whirlpool in the water. The water is purely spinning in continuous circles. It isn't radiating outward from the center like our faucet, and it isn't draining away like our sink.
It's just spinning.
Exactly. A pure spin has no outward burst or inward collapse. Therefore, the divergence, the outward flow of a pure curl, is always exactly 0.
So what does this all actually mean for the working physicist? Like, why do we care about equations that just equal 0?
Because these zeros act as ultimate cheat codes for understanding the universe. They give physicists profound shortcuts. Here's the first major theorem they derive from this.
Lay it on me.
If you're looking at a physical problem and you find a vector field whose curl is exactly zero everywhere, you know immediately, without doing any more math, that this field must be the gradient of some hidden scalar field.
Oh, wow. It's like finding a footprint and instantly knowing exactly what kind of animal made it. You don't even need to see the animal.
Exactly. And the second theorem is the mirror image. If you find a vector field whose divergence is zero everywhere, it absolutely must be the curl of some other vector field. You get to reverse engineer the physical system just by looking at the geometry of its changes.
That's wild.
Yeah.
You don't even need to know what the fields represent yet. The geometric rules dictate the physical possibilities. The source also brings up one more crucial second derivative before moving on. You take the divergence of a gradient, you get a new scalar operator called the Laplacian.
Represented by del squared, it's an absolute workhorse in physics. It shows up in everything from fluid dynamics to the Schrödinger equation in quantum mechanics.
But before we send you off to conquer the physics world with your new del operators, your paddle wheels, and your magic zeros, the text issues a very serious warning label. A couple of pitfalls that can completely wreck your math if you aren't careful.
Oh yeah, you have to be careful. The first pitfall involves crossing the del operator with itself. In normal, everyday vector algebra, if you take the cross product of any vector with itself, say vector A cross vector A, it is always zero, because they're perfectly parallel.
Right, so if I'm looking at an equation and I see the gradient of function psi crossed with the gradient of function phi, meaning del C cross del phi, I might instantly think, oh, it's del cross del, so they're parallel, it must be zero.
But it's not. And the reason goes all the way back to the concept of the Hungry operator.
The Pac-Man.
Yes, the two del operators are operating on different functions. One is eating psi, the other is eating phi. Therefore, the direction of the first gradient is dictated entirely by psi, and the direction of the second is dictated by phi.
So they aren't pointing the same way.
They are not parallel vectors, no. So their cross product is absolutely not zero.
Because the operator isn't a fixed, rigid arrow. It shapes itself to whatever it eats.
Precisely. This raises an important question about the second pitfall, which is coordinate systems. We said earlier that vector equations are beautiful because they're true no matter what coordinate system you use.
Which they are. We got rid of the arbitrary x-axis.
Yes, the equations themselves are invariant. But the components of the operators can behave very badly if you leave the comfortable world of rectangular x, y, and z axes. If you try to apply these operators component by component in polar coordinates using radius and angles, you'll fail miserably.
The source specifically gives the example of taking the radial component of a Laplacian.
Right. You can't just take the Laplacian of the radial component and expect the right answer. The reason is subtle but crucial. In rectangular coordinates, the x-axis always points in the exact same direction, no matter where you are in space.
Okay, sure.
But in polar coordinates, the radial direction points outward from the center, which means it changes depending on where you're standing. As you move from point to point, the direction of the basis vector itself is constantly twisting.
So if you try to take a spatial derivative, that twisting direction messes up the whole calculation.
It does.
The safest bet, the text warns, is to always stick to x, y, z coordinates when you are actually breaking these operators down into their components. It protects you from falling into these mathematical geometry traps.
It's a humbling reminder that while the fundamental laws of physics are independent of our coordinate systems, the mathematical tools we use to calculate them are not immune to geometry.
So to wrap up this incredible journey, we started with Paul Dirac's philosophy that a physicist needs an intuitive feel for an equation, not just a mathematical mastery of it.
A really important lesson.
We learned how to map the universe using scalars for things like a static temperature block and vectors for the active flow of heat. We invented a Hungry operator, del, that transforms perfectly with the geometry of space.
Pac-Man.
Yes, the Pac-Man. And we discovered how feeding that operator in different ways gives us the gradient, divergence our faucets and drains, and the curl our spinning paddle wheels. These are the exact tools needed to flawlessly describe the complexities of heat conduction and the entirety of electromagnetism in just a few lines of math.
And we found the magic zeros, those underlying geometric rules that act as cheat codes, letting physicists instantly understand how these invisible fields interact without having to solve the whole system.
It's an entirely new way to see the world around you, but it leaves me with one final thing to mull over, and I want you, the learner, to think about this too.
Oh, I like where this is going.
We look around, and physical reality is so undeniably messy. It's chaotic. The heat of your coffee cup dissipating unevenly, the invisible magnetic fields holding the electronics in your device together right now.
Yeah, it's everywhere.
All of it is chaotic. Yet every single bit of it can be perfectly, flawlessly described by abstract, hungry operators taking derivatives in space. So does that mean mathematics is just a highly convenient tool we invented to describe a messy universe? Or is the universe itself, beneath the solid walls and the everyday chaos, fundamentally built out of pure mathematics? Think about that next time you look at a solid brick wall. So, imagine taking a standard bar magnet, right? And you slice it perfectly in half.
Right, and your intuition just screams that you'd end up with a north half and a south half.
Exactly. But, well, the reality is the mathematical geometry of the universe explicitly forbids that from happening. You don't get two halves. You instantly get two new complete magnets, each with its own north and south pole.
It's wild. And today we're actually looking at the equations that dictate why space behaves this way. We are venturing into the absolute core of physics and mathematics.
Yeah, we're doing a deep dive into Chapter 3 of Volume 2 of the legendary Feynman lectures on physics. It's titled Vector Integral Calculus.
Which, I mean, to anyone outside the field looking at a physicist's blackboard covered in upside-down triangles and squiggly integration signs is, well, it's incredibly intimidating.
Oh, absolutely. It looks like some ancient dialect of alien hieroglyphics.
Right. But the mission of this deep dive is to crack that code for you. We're going to translate those dense, terrifying mathematical terms like divergence, gradient, and curl into, intuitive physical realities.
Because once you visualize the shapes and figures Richard Feynman provides in this chapter, I mean, these abstract concepts just transform. They go from impenetrable jargon to literal descriptions of how the universe moves and breathes.
Yeah, and the best place to start is with the simplest possible concept, right? Moving along a single line through a field. Feynman introduces this using a scalar field, which we can just call psi.
And just to clarify for everyone, a scalar field simply means every single point in a given space has just a single number associated with it.
Exactly. Temperature is a perfect everyday example of that. If
Yeah.
you walk through a room with a blazing fireplace on one side and, say, an open window on the other, every inch of that room has a specific temperature number.
Right. So say we're moving from point 1 in that room to point 2. Feynman's first theorem states that if you integrate the gradient of this scalar field along any curve from point 1 to point 2, you get the exact total difference in the field's value between those two locations.
I know integrating the gradient along a curve sounds super complex, but Feynman breaks it down beautifully in figures 3.1 and 3.2. A line integral is really just the mathematical limit of a sum.
Okay, so like chopping something up.
Yeah. Picture chopping your walking path from point 1 to point 2 into microscopic, perfectly straight little segments. At each tiny segment, you determine the gradient. And the gradient is just the maximum rate of change of the field.
But you only care about the component of that gradient that points in the exact direction you are stepping, right?
Exactly. You multiply that specific rate of change by the microscopic distance you stepped, which creates a running tally. You add up every single segment along your path.
It's basically the exact mechanics of hiking up a mountain. Like the scalar field is your altitude, and the gradient is the maximum steepness of the ground under your boots at any given step.
That is a brilliant way to picture it. Multiplying your step length by the steepness of that specific step, but taking only the incline in the direction you are actually walking, gives you your change in elevation for that one single step.
Right, and summing all those infinitesimal steps provides your total elevation change from the base to the summit, which reveals the profound truth of Theorem 1, which is path independence.
Path independence, yes.
Yeah.
It absolutely does not matter if you take a gentle 10-mile winding switchback trail or if you rock climb straight up a sheer cliff face for a single mile.
If you start at base camp and end at the summit, your total elevation change is identical. The math merely formalizes this exact physical logic.
And, path independence has massive implications. If you've ever wondered why lifting a heavy box straight up onto a high shelf requires the exact same total energy against gravity as pushing that same box up a long, winding ramp to the same height, this is the reason.
Wow, yeah. The gravitational field is a gradient field. The path you take through it does not change the total work done between point A and point B.
Right. But a 1D line is great for calculating the work of moving a box. If we want to understand how a light bulb radiates energy or how an explosion bursts outward, tracking a single path completely failed.
You need a mathematical tool that steps up a dimension.
Right.
Something that measures things pushing through a 2D surface that encloses a 3D volume.
Exactly. And Feynman introduces this dimensional leap in figure 3.3 with the concept of flux. Flux is defined as the surface integral of the normal component of a vector field.
Wait, I feel like we should clear up a historical misunderstanding built into that word. Because flux originally meant flow, like water rushing through a fishing net, or heat moving through a block of metal.
Oh, that's a really good point. Yeah.
But the math applies perfectly, even if nothing is physically flowing. I mean, you can calculate the flux of an electric field through an empty vacuum where absolutely nothing is moving.
Right, so flux is much better understood as a mathematical measure of how much a vector field is, like piercing outward through a surface.
Piercing outward. Got it. And the normal component part.
The normal component just dictates that we only count the part of the vector pointing dead straight out of the surface at a perfect 90-degree angle. If the field runs parallel to the surface, just skimming across it, it isn't piercing it.
So it contributes zero outward flux.
Precisely. If we have a closed box, the total flux is the measure of how much the field points out of the box minus how much points into it.
And Feynman illustrates a brilliant geometric trick for this in figure 3.4. Picture that closed volume, that box. Now take a knife and slice the volume cleanly into two separate pieces, creating piece A and piece B.
Yeah, and calculating the total flux out of piece A and adding it to the total flux out of piece B reveals something fascinating. The flux along the freshly cut shared internal surface perfectly cancels out.
Because the outward-pointing normal vector for piece A points in the exact opposite direction as the outward-pointing normal for piece B, right? What counts as out for one side is mathematically in for the other.
Exactly.
It's like slicing a melon in half. The flesh of the melon touching itself on the inside does not count as the outer skin. You press the two halves back together, and those internal boundaries just vanish from the equation entirely.
You are left only with the original outer skin of the whole melon. And since you can slice the volume in two, I mean, you can slice into a million pieces, Feynman takes this to its logical extreme in figure 3.5.
He shrinks it down.
Yeah, he shrinks the volume down, slicing it until we are left with a microscopic infinitesimal cube. Calculating the flux out of the 6 tiny faces of this cube gives us the divergence.
Divergence. So physically, the divergence is just the outgoing flux per unit volume at a single localized point.
Yes. It measures how much that specific spot acts as a source generating a field, or, a sink draining it.
So taking that microscopic divergence and zooming back out to our entire unbroken melon brings us to Gauss's theorem.
Bingo. Because all those internal faces perfectly cancel, the total flux out of any closed surface is exactly equal to the volume integral of the divergence inside that surface.
So you can measure the total field piercing the outer skin, or you can add up every single microscopic source inside. The results are mathematically identical.
And Gauss's theorem allows us to solve massive, complex problems using simple conservation laws. Feynman explores this in section 3.4 using the conservation of heat.
Right, because the fundamental law of our universe is that energy cannot simply vanish into the ether.
Exactly. If a block of material is losing heat over time, that thermal energy must be physically pushing out through the boundaries of that block. The internal loss perfectly matches the outward flux.
If you look at figure 3.6, you can picture a tiny point source generating heat inside a solid metal block. Physical intuition tells us that heat flows radially outward, forming a perfect expanding sphere.
And as that thermal energy travels outward, the surface area of the sphere it has to pass through grows. The area of a sphere expands based on the formula for pi r squared. Because the total heat energy is conserved, the intensity of the heat passing through any given patch of that expanding sphere has to decrease. It gets diluted over a larger and larger area.
Which is so cool because combining the conservation of energy with the geometry of a sphere mathematically proves why heat, gravity, and light all drop off following an inverse square law.
Yes. The further away you get, the larger the imaginary sphere and the more diluted the energy becomes. And we can actually take this a step further.
Okay, how so?
Well, heat naturally flows from hot to cold, meaning heat conduction is proportional to the temperature gradient. The steeper the temperature difference, the faster the heat flows.
Oh, I see.
Plugging this behavior into Gauss's theorem, the idea that outward flux equals internal loss generates the heat diffusion equation.
And the heat diffusion equation states that the rate of change of temperature over time is proportional to the Laplacian of the temperature, which I know the term Laplacian often confuses people.
It definitely does.
But physically, it is essentially a measurement of how out of sync a specific microscopic spot is compared to its immediate neighbors.
That's a great way to put it. If one tiny spot in our metal block is drastically hotter than the ring of atoms immediately surrounding it, the Laplacian is high, and heat rushes out of that spot to balance things out.
So the heat diffusion equation serves as the ultimate mathematical blueprint for how things spread out over time to reach equilibrium. Like, it models the diffusion of gases, the spread of neutrons in a nuclear reactor, even the dispersion of pollutants in a river.
It's universally applicable. But there is a catch. Gauss's theorem is perfect for fields that burst outward like heat radiating from a point source. But if we attempt to apply that to a hurricane or water going down a drain or a magnetic field, it completely fails.
Because those fields do not burst, they spin.
Right, they spin. So we require a totally new mathematical tool to measure swirl, bringing us to Feynman's concepts of circulation and curl.
Moving from fields that diverge to fields that rotate really requires shifting our perspective. Feynman introduces circulation in Figure 3.7. It is defined as the line integral of the tangential component of a vector field all the way around a closed loop.
Yeah, so with the gradient, we walked a line from point 1 to point 2. Here we are walking in a large circle, ending up exactly where we started.
And instead of looking at the outward-pointing normal vector used for flux, we look at the tangential vector. Like, this is the part of the field blowing perfectly along our walking path, basically acting as a tailwind.
Exactly. If you walk a loop and the field constantly pushes you from behind, that field has high circulation. And to deeply understand circulation, Feynman employs the exact same slicing method we used for volumes.
Right, in Figures 3.8 and 3.9.
He takes a large loop and chops it into a grid of tiny adjacent squares. And a familiar cancellation effect occurs. On the shared borders between any two adjacent squares, you traverse the line in opposite directions. The right side of the left square goes up, but the left side of the right square goes down.
I always picture a flat box packed tightly with tiny interlocking gears. Like, if every single gear is spinning counterclockwise, look at where any two gears touch. Their edges are moving in completely opposite directions.
Yeah, one edge grinds up, the adjacent edge grinds down, the internal movement perfectly cancels out.
The only movement that does not get canceled is the outer rim of the gears touching the edge of the box. The internal friction vanishes, leaving only the microscopic boundary.
Such a good analogy. And Feynman then isolates just one of those infinitesimal squares in Figure 3.10 to calculate the circulation per unit area. This microscopic localized spin is defined as the curl.
So divergence is localized outward burst, and curl is localized spin.
You got it. And this localized spin leads directly to Stokes' theorem, detailed in Figure 3.11. Stokes' theorem proves that the circulation around any boundary loop is exactly equal to the surface integral of the normal component of the curl over any surface bounded by that loop.
Wait, the phrase "any surface bounded by that loop" initially sounds like a magic trick.
I know it does. Think about a circular plastic wand used for blowing soap bubbles. The loop is the plastic ring. The surface is the soap film itself.
Oh, right. So Stokes' theorem states you can calculate the total circulation around the plastic ring by adding up all the microscopic curl, like all the tiny spinning gears across the soap film.
Yes, and it absolutely does not matter if the soap film is pulled tight and flat like a drum across the ring, or if the wind catches it, bulging it way out into a massive, wobbly balloon shape.
Because as long as its ultimate boundary remains that rigid plastic ring, the total sum of the curl across the entire distorted surface will remain exactly the same. That is wild.
It really is. But a critical question arises when dealing with these surfaces. When we calculated flux from a 3D box, normal simply meant pointing outward. A 2D soap bubble attached to a ring doesn't inherently have an inside or an outside.
Yeah, so defining which direction the normal component points, like which way is mathematically positive, requires a strict convention, right?
Right. Physicists use the right-hand rule.
Ah, the classic right-hand rule. So if you hold out your right hand and curl your fingers so they follow the path of the boundary loop in the direction you are walking, your thumb will stick straight out.
Yes, and your thumb points in the direction of the positive normal to the surface. It's so funny. The abstract mathematics are literally locked into consistency by the physical geometry of human hands.
That's amazing. So we now have three profound theorems operating together. The gradient handles 1D lines and path independence. Gauss's theorem handles 3D volumes, outward flux and divergence. And Stokes' theorem handles 2D surfaces, boundary loops, and curl.
And crashing these theorems into one another reveals the ultimate elegant consistency of the mathematical universe. If you look at figure 312, suppose we have a vector field where the curl is zero everywhere. There's absolutely no microscopic spin.
Okay, so according to Stokes' theorem, if the curl is zero across a surface, the total circulation around the boundary loop must be zero. Walking in a complete circle yields zero net change. The tailwinds perfectly equal the headwinds.
Exactly. And if traveling from point 1 out to point 2 and back to point 1 yields a net zero change, the specific route you take between point 1 and point 2 becomes completely irrelevant.
Oh, wow. Which brings us fully back to Theorem 1 and path independence. Any field with zero curl can always be represented as the gradient of a scalar potential.
Right. Returning to your mountain hiking analogy, because there are no spinning vortices in the field trapping you in an endless loop, you can define a steady absolute altitude at every point.
And crashing Gauss's theorem and Stokes' theorem together produces an even more profound result, visualized in figure 313. Picture a loop bounding a surface, like the wide-open rim of a deflated balloon.
Okay, I'm picturing it.
Now pull on a string to shrink that boundary loop. Shrink it smaller and smaller until the loop becomes a single microscopic point and disappears entirely. The open balloon has just become a completely sealed, closed sphere.
Wow. Following the mathematical logic there, because the loop's circumference shrank to zero, the circulation around it is indisputably zero.
Yes.
By Stokes' theorem, the surface integral of the curl over that now closed surface must be exactly zero.
And Gauss's theorem dictates that the surface integral of any vector over a closed surface equals the volume integral of its divergence. So if the surface integral of the curl is zero, the volume integral of the divergence of that curl must also be zero.
And because this holds true for literally any arbitrary volume you could possibly draw, the localized microscopic value itself must be zero. The divergence of a curl is always, everywhere, zero.
Grounding this in physical reality shows exactly why this must be true. Like if a field is pure spin, like water swirling in a whirlpool or the magnetic lines around a wire, there is no net outward burst from the center of that spin.
Right. If the divergence of a curl wasn't zero, it would mean a spinning vortex in a fluid could spontaneously generate brand new water from absolutely nothing, just bursting it outward into the universe. The geometry of space forbids it.
The curl of a gradient is always zero, and the divergence of a curl is always zero. The internal mathematics of our universe form a flawlessly closed system. Energy and fields do not glitch, they flow, they cancel, and they conserve in perfect harmony.
Yeah, the infinitesimal flat squares and perfectly canceling internal boundaries ensure perfect stability.
Well, we have journeyed from hiking up a gradient on a 1D line to demonstrate path independence, to slicing a 3D volume to prove that outward flux equals internal divergence.
We watched a box of interlocking gears cancel their internal friction to leave only the circulation around a boundary, proving Stokes' theorem. It's truly a masterclass in translating alien hieroglyphics into the literal mechanics of reality.
These laws act as the foundational conservation principles for fields moving through our standard, flat, three-dimensional space.
They absolutely do.
Which leaves a final, somewhat mind-bending question for you to consider. We just built this beautiful, perfect system of conservation laws based on flat squares and straight lines. But what happens when the fabric of space itself bends and warps, as Albert Einstein proved in his theory of general relativity?
Ooh, that's a good question.
Do these neat little infinitesimal cubes and perfectly canceling internal flat faces still hold true when the geometry of the universe is curved by the gravity of a black hole? Does the math still perfectly close its loops when space itself is bent? That is something for you to ponder until next time. You know, when you're watching a really chaotic action movie, right? Like cars flipping, explosions, people just running everywhere. It is completely impossible to focus on the fine details.
Oh, absolutely. Yeah.
Like if you want to understand how the complex engine of that flipping car is actually put together, you have to hit the pause button.
Right, you freeze the frame.
Exactly. Stop all the motion and just look at the pieces in total stillness.
Because as long as things are moving and changing, I mean, the complexity is just overwhelming. You really can't isolate the fundamental rules of a system when time is, constantly altering the variables.
It just muddies the waters.
Right. It does.
And that is exactly what we are doing to the universe today. So welcome to this deep dive. If you're here, you are that ultimate learner. The kind of person who wants to gain profound knowledge quickly, thoroughly, and without feeling crushed by information overload.
Which is really easy to do with physics. So easy. But today, our mission is taking us straight into the legendary Feynman lectures on physics. Specifically, we're looking at Volume 2, and we are focusing strictly on electrostatics.
Which is just a beautiful, deeply elegant corner of physics.
Mm.
But it does require us to sort of change how we see the world.
It really does. So our goal today is to extract the core insights about electric fields, potential energy, and how to model these invisible forces. And we're going to do it without getting bogged down by intense multivariable calculus.
Thankfully.
Yeah. We're going to unpack the big ideas, visualize the concepts, clear up some major common misunderstandings. And, setting the scene for us, as always, I am looking across the table at our expert, who is currently framed by this incredible digital backdrop of complex math equations and these glowing 3D geometric models. You look perfectly set up to connect the dots for us.
I am ready. And, your action movie metaphor is actually the perfect place to start. Because before we can understand how electric charges interact, we literally have to pause the universe. Okay, let's unpack this. Why do we need to freeze time to understand electricity?
Well, the source material starts with Maxwell's equations. And Maxwell's equations are the complete ultimate rulebook for electromagnetism.
Right.
But in their full form, they look incredibly complicated. And the reason they are so complex is because of time.
Because things are moving.
Exactly. When charges are moving and accelerating and changing over time, electricity and magnetism are just messy. They're tangled up together. A changing electric field creates a magnetic field, and then a changing magnetic field creates an electric field.
It's just an endless, chaotic feedback loop. Like the action movie.
Precisely that. But if we look at the static case, like electrostatics, we are looking at a universe where charges are perfectly still.
Or moving super steadily, right?
Right. At most moving as a perfectly steady, unchanging current. And when we do that, all the terms in Maxwell's equations that deal with time derivatives...
Yeah, moving parts.
Yeah, the moving parts, they just drop to zero.
They vanish.
They completely vanish.
So what happens to the underlying math when time is just taken out of the equation entirely?
If we connect this to the bigger picture, this is where a really profound simplification happens. In the static world, electricity and magnetism completely divorce.
Wow.
Yeah, they decouple entirely. So the electric field, which we call E, and the magnetic field, B, they no longer depend on each other. They act like two completely distinct phenomena.
So we get to just ignore magnetism for a minute.
Exactly. We get a neat, clean vector field for electricity that has zero curl.
Hold on. For anyone listening who isn't a vector calculus major, what does zero curl actually mean in the real world?
Okay, think of a field like a flowing river. If you drop a leaf onto the surface of the river, and the water pushes the leaf straight downstream without spinning it, that river has zero curl.
Okay.
But if the water catches the edges of the leaf and makes it spin like a top as it floats, that means the field has curl. It's swirling back on itself.
I see. So by freezing time and isolating stationary charges, we ensure our electric field only pushes straight out or pulls straight in.
Right, it doesn't swirl.
So by freezing the frame, we only have to deal with stationary charges interacting with other stationary charges in straight lines. We've simplified the rules.
Significantly.
So now that time is frozen, how do these charges actually interact? Because I know the foundational rule here is Coulomb's law.
Yeah, that's the bedrock.
Right.
Coulomb's law states that the force between two stationary charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them.
So that's the famous inverse square law.
Exactly. If you take two electrons and, say, double the distance between them, the repulsive force between them doesn't just cut in half.
It drops to 1/4.
Exactly right. Drops to 1/4.
And there's a specific constant that ties this all together, right? Like, the text makes a point to detail this. The constant of proportionality is written as 1/4 pi epsilon 0.
Yeah, and the value of that constant is a really fascinating little Easter egg hidden in the math.
Oh, I love Easter eggs.
In the standard metric system, it is defined as exactly 10 to the power of -7, multiplied by the speed of light squared.
Wait.
Which works out to about 9 billion Newton meters squared per Coulomb squared.
Wait. I need to pause you there.
Sure.
If we completely froze time and divorced electricity from magnetism, why is the speed of light, which is literally the ultimate speed limit of motion, hidden inside a formula specifically designed for stationary, non-moving charges?
I know, right? That is the genius of the universe shining through the math.
It's wild.
Even when we force the universe into a static state to study it, the underlying machinery of electromagnetism is still baked right into the foundation.
How does that even work?
Think of a guitar string. Even when that string is perfectly still, the tension inside it dictates exactly how fast a wave will travel if you eventually pluck it.
Oh, wow.
Right. The static electric field is the tension of space. Light is just an electromagnetic waves rippling through that field.
So the tension of stationary charges naturally contains the speed limit for how fast that ripple could ever move.
Exactly. The stillness implies the motion.
That is an incredible way to look at it. Okay, so Coulomb's law tells us the force between two charges. But the real world isn't just two charges in an empty void.
No, not at all.
If you're looking at a standard object, there are billions and billions of charges.
Which brings up the principle of superposition. This rule says that if you have multiple charges, the total force on any one specific charge is just the vector sum of the Coulomb forces from every single other charge.
Let me make sure I'm picturing this correctly.
Okay.
If I have a billion electrons, and I want to know the force on just one of them, I have to calculate the individual push and pull from the other 999 million.
Yep.
Taking into account their exact 3D distance and angle, and then combine all those tiny microscopic arrows.
You would have to do exactly that. And if you have a continuous smear of charge, what physicists call a charge density, which is represented by the Greek letter rho, you have to use calculus, you do integrals over the entire 3D volume to add up the field from every single microscopic sliver of space.
I have to be honest, that sounds completely insane from a practical standpoint.
It really does.
That is a mathematical nightmare. It sounds like brute force torture for anyone trying to actually solve a physics problem.
Feynman himself validates exactly what you're feeling here. He explicitly points out that doing three-dimensional integrals just to find an electric field is strictly a job for a computing machine.
Yeah, let a computer do it.
Right. If you know where all the charges are, you technically have the answer. You just have to do the grueling math.
But nobody wants to do that.
No. And what's fascinating here is that physics isn't just about grinding through endless calculations. It's about finding elegant, smarter ways to look at the same problem.
So if I'm a physicist, and I absolutely refuse to do a billion 3D geometry problems, what is the shortcut?
We look for energy shortcuts. Specifically, we stop looking directly at the force vectors, the pushes and pulls.
Yep.
And we start looking at the work required to move a charge through the field.
Okay, work. So instead of just looking at the stationary tension, we imagine bringing a tiny test charge into the area and seeing how much effort it takes to move it around.
Yes. Imagine moving that test charge along a path. If you move it perpendicularly to the electric force, like walking in a perfect circle around a central charge, you do zero work.
Because you aren't fighting the field.
Exactly, you're just coasting along it. But if you move radially, straight toward the central charge, you have to push against the field, and that takes work.
I want to try an analogy here, because I think I see where this is going.
Go for it.
If you're listening to this while you're out for a walk or like driving in your car, imagine your environment is the electric field. It's exactly like hiking a mountain, isn't it?
Walk me through it.
Okay, the mountain is the electric field. The gravitational pull you're fighting is the electrical force. If I want to hike from the base of the mountain to the summit, I have two choices. I can take the sheer, steep, direct path straight up the cliff face.
Yeah.
The short path, but I am fighting maximum gravity every single agonizing step.
That sounds awful.
Right. Or I can take the long, winding, gentle switchback trail that just sort of spirals around the mountain.
Okay.
Most of the time, I'm walking relatively flat, doing very little work, and only occasionally stepping up. But regardless of which path I take, once I reach the summit, my total change in altitude, my potential energy, is exactly the same.
That is a phenomenal analogy. The work done in an electrostatic field is completely path independent.
Path independent.
Yes. Whether you take the direct radial path or a jagged, winding zigzag path, the total work done is identical. The total energy you spent fighting the field depends only on your starting point and your ending point.
And because it's path independent, we don't have to track the exact route the charge took.
That path independence is the entire secret. Because the work only depends on the location, we can assign a single, simple number to any point in space.
Just one number.
Just one. We call that number the electric potential, and it's represented by the scalar field phi.
Okay, you used the term scalar field, and earlier we talked about vector fields. Help us visualize the difference and why finding a scalar field saves us from that computing machine nightmare.
Let's use your backyard as an example. If you want to describe the wind in your backyard, you need a vector field. At every single point, the wind has a speed, but it also has a direction.
North, south, up, down.
Right. To calculate a vector mathematically, you have to track three separate dimensions: x, y, and z. That means 3 complex integrals.
3 times the headache.
Exactly.
Hmm.
But now imagine you want to describe the temperature in your backyard.
Okay.
Temperature doesn't have a direction. It's just 72 degrees.
Right, just is.
It's a single number. That is a scalar field. The electric potential, phi, is like the temperature. It's a scalar. It has no direction. It just represents the energy level at that specific spot.
So to find it, you only have to do 1 integral instead of 3.
You got it.
That drastically cuts down the math.
Oh, massively.
But if potential is just a single number, like altitude on a mountain, how does that help me find the actual force? Because the force pushes in a specific direction.
Well, once you have that single scalar field, your topographic map of altitude, you can find the electric field, E, instantly by just taking what's called the negative gradient of the potential.
Okay, so the math is E equals negative del phi.
Right. And going back to your mountain analogy, if the potential phi is a map showing the altitude at every single point, taking the gradient just means asking one simple mathematical question.
Which is?
Which way is the steepest way downhill?
The steepest way down the mountain is the exact direction of the electric field.
Exactly.
You map the altitude instead of mapping every single rock, and then you just look for the slope.
It's vastly easier to calculate the scalar potential and take the gradient than it is to grind out 3 separate vector integrals.
Okay, so the math is simplified. That makes sense. But if I want to actually picture this field in my head, how do I visualize an invisible force in 3D space? Let's say I want to see what a clump of positive charges is doing to the space around it.
This brings us to a concept called flux.
Flux.
Flux is a way of measuring the net flow of the electric field through an imaginary surface. To visualize it, think of an invisible, empty cardboard box floating in space near our clump of positive charge.
Okay, I have my invisible empty box.
The electric field is radiating outward from the charge. As it passes through our empty, invisible box, the field lines enter one side of the box and they exit out the other side.
Right.
Because there is no charge inside the box itself, the net flux, which is the total flow out of the box minus the flow in, is exactly 0. What goes in must come out.
It just passes right through.
Yeah, it doesn't even matter if the sides of the box are tilted at a weird angle or if the box is completely crumpled. The geometry perfectly cancels out.
But what if we put the clump of charges inside the box?
Well, that changes everything. If the surface encloses the point charge, the field is radiating outward through every side of the box.
So nothing is coming in to cancel it out.
Right. And the text shows a brilliant mathematical trick here. Imagine wrapping the charge in a tiny, perfect sphere. The flux through a perfect sphere is incredibly easy to calculate because everything is completely symmetrical.
Right.
And because whatever passes through that tiny sphere must also eventually pass through the larger, weirdly shaped cardboard box surrounding it, we discover a universal rule.
And this is Gauss's law, correct?
Yes. Gauss's law states that the total flux out of any closed surface, no matter how strange, warped, or jagged its shape, is exactly equal to the total charge enclosed inside that surface, divided by our constant epsilon 0.
Here's where it gets really interesting. I've heard an analogy used to explain this, the bullet analogy.
Oh, right.
The idea is, if the charge is machine gun, the electric field is like a steady stream of invisible, conserved bullets shooting out in all directions. If you put a box over the gun, the number of bullets punching through the cardboard is always going to equal the rate the gun is firing, no matter what shape the box is.
Right.
So is the electric field literally made of tiny, invisible bullets of energy shooting through space?
Now, this raises an important question, and the answer is a firm, absolute no.
No bullets.
No bullets. The bullet model is nothing more than a temporary mental crutch. It helps us intuitively grasp the geometry of the inverse square law and Gauss's law, but the text gives a very stern warning here.
What's the warning?
If you try to make the electric field act like literal physical bullets or literal flowing fluid, you will inevitably produce errors in your understanding.
Really? Why? It seems like such an easy way to picture it.
Because the field doesn't have mass. It isn't composed of little projectiles that bounce off each other. No one has ever succeeded in making a bullet or fluid model that explains anything beyond this one specific geometrical law.
Oh, I see.
To truly understand electromagnetism, we must be comfortable representing the field purely abstractly, as mathematical properties of space itself. It is not a fluid. It is not tiny projectiles. It is a field.
It's purely abstract mathematics. Got it. So now that we have this incredibly powerful abstract tool, Gauss's law, what can we actually do with it? Like, what impossible problems does it solve?
Well, it solves problems that used to give the greatest minds in history absolute nightmares. Take Isaac Newton, for example.
Okay.
When he developed his theory of gravitation, he faced a massive obstacle. He knew how two tiny point-like masses attracted each other. But the Earth isn't a point. It's a massive solid sphere.
Right. So to figure out the gravity of the Earth pulling on an apple, he couldn't just measure from the apple to the dirt.
No.
He had to mathematically chop the Earth up into tiny imaginary cubes, calculate the pull of every single grain of sand, every rock, every drop of ocean from completely different distances and angles. It's that computing machine nightmare all over again.
It was so mathematically daunting that Newton actually delayed publishing his theory of gravitation for years.
Wow.
Yeah, he struggled to rigorously prove that a solid sphere of uniform matter acts exactly like a single point mass located dead at its center.
He had to do it the hard way.
He did. But with Gauss's law, we don't have to do the calculus.
Really?
We don't. And since electrostatics obeys the exact same inverse square math as gravity, the solution applies perfectly.
So how does Gauss's law bypass it?
You just draw an imaginary spherical surface around a physical sphere of charge. Because of perfect symmetry, the electric field must be pointing straight out uniformly everywhere.
Okay.
Gauss's law tells us the flux is just the field strength times the area of our imaginary sphere, and that must equal the total charge inside divided by epsilon 0.
That's it.
That's it. In literally one line of simple algebra, you prove that a solid sphere behaves perfectly as if all its charge were concentrated at the center. What took Newton years of agonizing calculus, Gauss's law solves almost instantly.
That is the ultimate working smarter, not harder moment. It almost feels like cheating.
It's the reward for understanding the deep symmetry of nature.
Okay, we have one final set of visual tools to decode before we wrap up. Field lines and equipotential surfaces.
Right. To sketch what the field looks like without doing all the math, we draw continuous field lines. They start at positive charges and they end at negative charges.
Okay.
The density of the lines, like how close together they are, tells you the strength of the field, and then we draw equipotential surfaces.
Going back to the mountain analogy, the equipotential surfaces are the topographic contour lines. They show the lines of equal altitude on the mountain.
Exactly. And mathematically, because the electric field is the gradient, the steepest path down the mountain,
Right.
the equipotential surfaces must always cross the field lines at exactly a 90-degree angle. They are always perpendicular.
Okay, so for a single positive charge, you get radial field lines pointing out like a sunburst, crossed by perfectly spherical equipotential shells. But what happens when we have multiple charges? Let's say a positive charge and a negative charge, sitting right next to each other.
Things get more complex.
The field lines curve and bow outward from the positive and swoop into the negative. The equipotential lines look like warped, squashed balloons.
Yes.
So my question is, since we have the principle of superposition, which says we can just add fields together,
Right.
can't I just take the simple sunburst drawing for charge A, take the sunburst drawing for charge B, lay them on top of each other, and trace the combined result?
No, absolutely not.
Oh.
That is another major trap that trips up a lot of students. If you superimpose the visual drawings, the field lines from charge A will cross over the field lines from charge B.
And why is that a problem? If the forces overlap in real life, why can't the lines overlap on paper?
Because the electric field line represents the single net vector at any given point in space. It represents the actual final direction a real test charge would be pushed.
Oh, I see.
If two lines cross, it implies that at that specific intersection, a charge would be pushed in two different directions at the exact same time.
Which is physically impossible.
Exactly. Therefore, field lines can never, ever cross.
Ah, that makes perfect sense. The charge has to pick a path.
The principle of superposition applies to the underlying mathematics. You add the numerical vectors together to find the new single net force. But the geometry of the resulting drawing is incredibly complex. You cannot just overlap the pictures.
Because the field line picture fundamentally hides the mathematical simplicity of superposition.
Right. You have to do the math first to draw the combined field correctly.
So what does this all mean for us? If we zoom out from the math and look at the journey we've taken today, we started with Maxwell's equations, which looked terrifying.
Very.
We stared down the barrel of brute force 3D integrals that would break a normal person's spirit.
Absolutely.
But we discovered that by shifting our perspective, by looking at the path independence of work to find the scalar potential, or leveraging the pure geometric symmetry of Gauss's law,
We bypass it all.
yeah, we completely bypass the hardest math. We uncover the elegant underlying rules governing the universe.
Yeah.
It really is a masterclass in shifting your perspective to let the geometry do the heavy lifting for you.
It is. But I want to leave you with one final thought, something hidden deep in the text that is absolutely critical to ponder.
What's that?
All of these elegant shortcuts, specifically Gauss's law, they only work for one very specific reason. They only work because Coulomb's law relies on an exponent of exactly 2, the inverse score law.
Meaning the force drops off by 1 over r squared.
Yes. If the electric field dropped off at 1 over r to the power of 2.00011, or if it dropped off at 1 over r cubed, Gauss's law would completely fall apart.
Really?
The flux would not be conserved through an imaginary sphere. The math would shatter. Imagine what a universe would look like if the 3D geometry of space didn't perfectly align with the invisible forces radiating inside it.
Wow.
If this flux wasn't perfectly balanced by the exact geometry of a sphere, would anything, even the electrons holding together the atoms in your own body, be able to maintain their structure?
That is a terrifying and beautiful thought. The universe works because the math is exactly perfectly a 2.
Exactly a 2.
Something to mull over as you go about your day. And with that, I think we have fully explored the static frame. It's time to hit play, unpause the action movie, and let the universe start moving again. Thanks for taking this deep dive with us.
So have you ever wondered why it is perfectly safe to just sit inside the high voltage terminal of one of those 1,000,000-volt Van de Graaff generators?
Oh yeah, the giant metal spheres you see in science museums.
Right. The ones that are mounted on pedestals and like shoot these massive bolts of artificial lightning across the room. I mean, common sense just screams that sitting inside one of those while it's turned on should be instantly lethal.
Oh, absolutely.
But surprisingly, you wouldn't feel a thing. Like you could literally drink a cup of tea in there while 1,000,000 volts are just raging on the outside surface.
It really is one of the most, well, it's one of the most stunning paradoxes in physics, I think. Because we are taught to be incredibly cautious around high voltage, and, for good reason.
Yeah, obviously.
But under the right geometric conditions, you can be completely engulfed by those 1,000,000 volts and just remain in this perfectly calm, insulated environment.
And to understand how that's physically possible, we are dedicating this deep dive to unpacking Chapter 5 of Volume 2 of the legendary Feynman Lectures on Physics. So today, we're basically translating all that heavy electrostatics math into physical reality.
Exactly. We're looking at how our universe balances itself out. And to set the stage, electrostatics, which is just the study of stationary electric charges, is built on 2 foundational rules.
Okay, let's lay those out for everyone listening.
Right. So the first is Gauss's law. This law basically states that the total outward flow or flux of an electric field through any closed imaginary surface is directly proportional to the total electric charge trapped inside that surface.
Okay, so just to make sure I'm getting this, if I imagine like a bubble floating in space and there's no charge inside the bubble at all, then whatever electric field flows into one side of the bubble has to flow right out the other side.
Yep.
So the net flow is 0.
Exactly. Net flow is 0.
Oh.
And the second rule is that the circulation of an electrostatic field is always 0. The source text describes this by saying the electric field is a gradient of a potential.
Right, which sounds very technical.
It does. But in simpler terms, moving a charge against an electric field is a lot like pushing a heavy boulder up a hill. Like, it requires actual physical work.
Okay, makes sense.
But if you push that boulder up the hill, roll it along a ridge, and bring it back down to the exact spot where you started, the total net work you've done against gravity is 0.
Because you're back where you started.
Exactly. You can't get free infinite energy by just moving a charge in a circle.
Okay, so those seem like 2 incredibly solid, very straightforward rules. But, and this is where we get into the meat of it, things get complicated really fast when we try to use those rules to do something that sounds incredibly simple.
Like trying to hold a single positive charge completely still in midair using only other static charges.
Right. Because you'd naturally assume that's possible. I mean, we balance physical objects all the time. If I just set up a perfect ring of positive charges and they're all pushing equally inward on my single positive charge in the center, wouldn't it just float there?
You'd think so, but no. The mathematics of those 2 rules we just talked about reveals that static equilibrium in empty space is completely impossible.
Wait, completely impossible.
Totally impossible. You cannot place a point charge in a stable mechanical equilibrium using only the forces of other static electric charges. Because think about what true stability actually requires.
Okay.
For your central charge to be perfectly stable, if a slight breeze bumps it even a millimeter in any direction, there has to be a restoring force ready to push it right back to dead center.
Right, like a bowl. Like if a marble rolls up the side of a physical bowl, gravity just pushes it back down to the lowest point.
Exactly. So that means the electric field at every single point immediately surrounding your center spot would have to be pointing inward.
To create that electric bowl.
Right. But now apply Gauss's law to that bowl. If you draw a tiny invisible sphere, they call it a Gaussian surface, enclosing your center point, and the electric field everywhere on that tiny surface is pointing inward, well, the net flow is negative.
Ah, because it's all flowing in and nothing is flowing out.
Right. But Gauss's law strictly demands that an inward flow requires a negative charge inside that space to essentially, soak up the field.
But there is no negative charge there. We just said it's empty space surrounding our positive charge.
Exactly. So an inward pointing field in empty space violates the fundamental law of electrostatics.
Okay, so it's like trying to balance a perfectly round marble on like a saddle-shaped potato chip.
Oh, that's a great analogy.
Right, because in one direction it might look stable because the chip slopes up, but in the other direction the chip slopes down, so the marble will inevitably just roll off the side.
It will always roll off. The math literally proves we can't ever build an invisible bowl out of electric fields. It will always be a saddle.
So is there any physical way to cheat the system? Like what if we literally block the charge from moving sideways? Can we use physical constraints?
Yeah, actually, the source material addresses that exact loophole. There's a great illustration in the text, figure 5.2. If you introduce mechanical constraints, so like putting your positive charge inside a tiny glass tube so it physically just cannot move sideways,
Okay.
then you can create an electric field that points inward at both ends of the tube to keep it from flying out.
Because the glass handles the sideways problem.
Right. The electric field is allowed to flow laterally outward near the center, just passing right through the glass walls. So the net flow balances out to zero, which satisfies the math, while the physical glass tube stops the charge from slipping out the sides.
Okay, but what if we use metals instead of glass? Because in a piece of metal or, any conductor, the charges can move around freely. Couldn't we arrange a bunch of charged metal spheres around our central charge? And if it drifts, the metal charges shift and push it back?
It's a really logical thought process, but conductors actually make the situation worse.
Wait, really? How?
Well, when charges redistribute themselves on a metal surface, they always do so to lower their total potential energy.
Yeah.
So if your trapped charge drifts slightly off-center, the charges on the metal spheres shift in a way that actively lowers the system's energy.
Oh, no. So it pulls it.
Yes. This shifting ends up increasing the pull away from the center. It just pulls your charge harder into the wall. So static electric fields, no matter how clever your setup is, simply cannot trap a charge stably in empty space.
Wait, okay. If the math proves nothing can be perfectly balanced statically, how are we even sitting here?
I know, right?
I mean, atoms are fundamentally just positive protons and negative electrons. If static balancing acts are mathematically impossible, shouldn't every atom in our bodies just, fly apart or collapse instantly?
Yeah, and this is actually a massive existential crisis in early 20th century physics. I mean, our fundamental understanding of what matter was made of was seemingly at war with the established laws of electricity.
So how did physicists try to reconcile that? Did they try to change the rules of electricity?
No, instead of changing the rules of electricity, they tried changing the structure of the atom.
Yeah.
So the first major attempt was J.J. Thomson's model, which is often called the plum pudding model.
Right, like the dessert.
Exactly.
Mm-hmm.
He proposed that the positive charge of an atom wasn't a tiny point, but rather this uniform, smeared-out cloud of positive charge. And the negative electrons just sort of sat inside this cloud like plums resting in a pudding.
So because the positive charge was a distributed cloud, rather than just empty space, the electrons could find stable resting places inside it without violating Gauss's law.
You got it. But as we know, the plum pudding model didn't last.
Right, because of Ernest Rutherford. He did those gold foil experiments and eventually proved that the positive charge isn't smeared out at all. It's incredibly concentrated in this tiny, ultra-dense nucleus at the center.
Yes. Rutherford proved the positive charge was essentially a microscopic point. And with that discovery, physics was thrown right back into the fire. The impossibility of static equilibrium was back.
Because the electrons couldn't just sit still around a point nucleus.
Right.
So if they can't sit still, why not have them orbit the nucleus, like planets around the sun? I mean, the Earth doesn't fall into the sun because its forward momentum keeps it in a dynamic equilibrium. Couldn't electrons just do the same thing?
That was definitely the next logical step. That's the Rutherford-Bohr model. But there is a fatal flaw in applying planetary mechanics to electromagnetism.
Well, because of radiation.
Exactly. According to the laws of electricity, any accelerating charge has to radiate energy, usually in the form of light or radio waves. And moving in a circular orbit requires constant acceleration toward the center.
Ah. So an orbiting electron would be constantly broadcasting energy out into space. And as it loses that energy, it would slow down, its orbit would decay, and it would just crash right into the nucleus.
It would spiral into the nucleus in a fraction of a second. So the orbit model is fundamentally unstable under classical physics. The true stability of atoms relies on an entirely different set of rules that had to emerge later quantum mechanics.
Okay, so how does quantum mechanics fix it?
Specifically, it's the uncertainty principle. If the electrical force pulls an electron too close to the nucleus, squeezing it into a tiny, highly confined space, its location becomes very certain.
Right, Heisenberg. You can't know both position and momentum.
Exactly. Since you cannot know both the precise position and the precise momentum of a particle at the same time, when its position is tightly constrained, its uncertainty and momentum just skyrockets.
Meaning the electron suddenly gains a massive amount of kinetic energy just by being squeezed?
Yes. That quantum mechanical kinetic energy violently pushes back against the electrical attraction. It creates this dynamic, probabilistic equilibrium.
Yeah.
Ironically, it ends up looking a bit like Thomson's plum pudding, but inverted.
Oh, how sad.
Instead of the positive charge being a smeared-out cloud, it is the negative electron that exists as a smeared-out probability cloud around the dense positive nucleus.
That is just mind-bending. So the only reason we don't collapse into microscopic black holes of charge is because the universe physically refuses to let us know exactly where an electron is.
Pretty much.
But, okay, if balancing single-point charges is so impossibly fragile and requires quantum mechanics, does the math actually get easier when we look at, like, billions of them smeared together into everyday objects?
Oh, it gets beautifully elegant. The source material spends a lot of time analyzing continuous shapes of charged things like long lines, flat sheets, and solid spheres. And this is where Gauss's law really shows off its true predictive power.
Because of those Gaussian surfaces.
Right. By imagining those invisible boundaries, drawing imaginary cylinders, boxes, or spheres around these objects, you can calculate their electric fields almost instantly, skipping just pages and pages of torturous calculus.
Let's visualize a few of these for the listener. First, a uniformly charged rod, something like an endlessly long, glowing fluorescent tube. Gauss's law proves that the electric field shoots straight out from the sides, and its strength weakens as the inverse of the distance.
Yep, good dollars.
Right. So if you move twice as far away, the pull is half as strong. That completely tracks with everyday experience. But the next shape, the infinite flat sheet of uniform charge, that one is completely counterintuitive.
It really is. If you draw an imaginary Gaussian box cutting right through an endlessly flat sheet of charge, the math dictates that the electric field is perfectly constant everywhere.
Wait, everywhere?
Everywhere. No matter how far away you move from that sheet, the electrical push or pull remains exactly the same strength.
That is wild. Let me try an analogy here. Imagine looking at an endless, brightly painted red wall. If that wall truly goes on forever in every direction, taking 3 steps back doesn't actually change how much of your field of vision the wall takes up. Because it's infinite, it always fills your vision entirely. So the redness never fades, whether you are 1 foot away or a mile away. Is it like that?
That's a perfect way to think about it, because as you step back, the wall directly in front of you is further away, yes, but vast new expanses of the wall's distant edges enter your peripheral vision.
Oh, I see.
And those newly visible distant charges pull at an angle, and they perfectly compensate for the distance you just put between yourself and the center. The sum total of the field remains completely unchanged.
So what happens if we take 2 of these endless sheets, give one a positive charge, give the other a negative charge, and put them exactly parallel to each other?
Well, this brings us to figure 5.7 in the text, which is essentially explaining the mechanics of a capacitor. On the outside of the 2 sheets, the positive push of one sheet perfectly cancels the negative pull of the other, so the electric field outside is exactly 0.
Like acoustic noise cancellation.
Basically.
Mm-hmm.
But in the space sandwiched between them, the forces combine. The field between them is exactly double what it would be for a single sheet.
That is so cool. Okay, but the most important shape in this chapter is the sphere. Now, a solid charged sphere's field grows as you move from a center to the edge. But what happens if the sphere is completely hollow? Like, imagine a ping pong ball made entirely of static charge.
Okay, if you draw a Gaussian surface Anywhere inside a hollow, uniformly charged spherical shell, there is zero charge enclosed in your imaginary boundary.
Because it's hollow?
Because it's hollow. And because of the perfect symmetry of the sphere, Gauss's law guarantees that the electric field is zero everywhere inside that hollow space.
Zero everywhere, not just in the dead center, but even floating like a millimeter from the inside wall. You would feel absolutely no electrical force.
None at all.
That feels like a mathematical parlor trick. Like, does that actually hold up in reality?
It does. And that cancellation is the ultimate test of physical reality. But, and this is crucial, it only works if the fundamental rule of electrostatics is flawlessly true.
Which rule?
The rule that electrical force diminishes by the exact square of the distance, written as 102 to 2. Imagine floating off-center inside that hollow shell.
Yeah.
You're very close to the left wall, so it pulls you strongly. But it is a very small section of wall pulling you.
Okay, yeah.
Now look to the right. The right wall is much further away, so its individual pull is weaker, but there is vastly more surface area pulling on you from that side.
Oh, right. The source material illustrates this using cones. Like, if you draw two opposite cones expanding outward from your off-center point, the surface area of the shell cut out by the far cone grows exactly with the square of the distance.
Yes, the surface area of the far wall grows by $2 a 2, and the force weakens by 2 of all. The two effects perfectly mathematically cancel each other out. A large area with a weak pull exactly counters a small area with a strong pull.
But that perfect balance only happens if the exponent for the distance is exactly 2, not like 2.00001.
Exactly 2. If it was 2.00001, the inside of the sphere would have a residual electric field.
Okay, I follow the geometry, but why rely on this elaborate hollow shell setup to test the rule? Why not just put two highly charged metal balls on a table, pull out a highly precise microscopic ruler, and measure the force directly as you pull them apart?
Well, measuring absolute forces directly to high precision is just a nightmare in experimental physics.
Really? Why?
Because there's always friction or calibration errors in your instruments or just environmental noise. But measuring the absence of something, what physicists call a null result, is phenomenally accurate. If you test for an electric field inside a hollow sphere and the needle on your meter simply does not move, you know the cancellation is absolute.
Ah, I see. So how did they actually manage to measure that absence accurately back in the day?
James Clerk Maxwell actually performed this test in the 1800s. He suspended a smaller sphere inside a larger hollow sphere. He applied a massive charge to the outer sphere and then carefully lowered a wire to connect the two spheres.
Okay, so if there was any electric field pushing inward, charge would flow to the inner sphere.
Exactly. Then he disconnected it, pulled the inner sphere out, and tested it with an electrometer. He found no charge at all. And that proved the exponent was exactly 2 around, down to an accuracy of 1 part in 10,000.
Which is an incredible feat for Victorian-era technology, honestly.
Oh, it was brilliant. But then, in 1936, researchers named Plimpton and Lawton took it to another level. They essentially built a sphere within a sphere, suspended by a silk string.
Okay.
And to ensure no charge could leak in from outside measurement wires, they sealed their amplifier and a highly sensitive galvanometer completely inside the inner sphere.
Wait, if the measurement tools were completely sealed inside metal spheres, how did they even read the results?
They observed the needle of the galvanometer through this tiny glass window that they filled with salt water.
Salt water, why?
To maintain the electrical conductivity of the shell. They pumped thousands of volts at low frequencies into the outer shell, and the needle inside never twitched.
Wow.
Through that, they proved that Coulomb's exponent differs from exactly 2 by less than 1 part in a billion.
1 part in a billion. That is like measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair.
It's astounding.
So does this perfect mathematical rule still hold up when we shrink things down to the microscopic level?
It does, but only down to a certain boundary. Researchers Lamb and Rutherford tested it at the atomic scale, roughly 10 to 8 centimeters, by observing the energy levels of hydrogen. If the exponent was off by even 1 part in a billion, the light emitted by hydrogen atoms would literally be the wrong color.
But the colors matched perfectly.
They matched perfectly.
So it works for atoms. Where does the math finally break down?
When you zoom in, far past the electrons, right into the nuclear scale, about 10-14 centimeters, deep inside the heart of an atom. When physicists shoot high-energy electrons incredibly close to protons, the electrical force seems about 10 times too weak.
Wait, so does the fundamental law of the universe actually break there, or is something else happening?
The current understanding is that the math of the inverse square law likely still holds perfectly, but our assumption about the proton is flawed.
Ah, okay.
The proton isn't a perfect dimensionless point charge. It interacts with short-lived subatomic particles called mesons. And this interaction creates a tiny, smeared-out cloud of positive charge.
Oh, just like the solid sphere we discussed earlier.
Precisely. Once your electron actually penetrates the outer edge of that charge cloud, the field stops following the standard 122 rule because you're now inside the charge distribution.
That is just fascinating. So the rule is perfect. It's the shape of the matter that changes.
Yep.
Okay, let's bring this vast cosmic physics all the way back to our human-sized world and that Van de Graaff generator from the introduction. The perfection of this inverse square law is what explains the behavior of everyday electrical conductors, like metals.
It really is.
Okay.
So a conductor is simply a solid material that contains free electrons. These electrons aren't bound to single atoms. They can move anywhere inside the material. When you expose a piece of metal to an electric field, those free electrons instantly rush around, shifting their positions until they completely cancel out any internal electric field. The interior field becomes exactly zero.
And because the internal field is zero, it takes no work to move around inside the metal. There are no invisible hills to push boulders up.
Right, physicists call this an equipotential region. The entire interior of the metal is at the exact same electrical voltage.
It makes me think of, like, a team of hyper-vigilant bouncers at an exclusive club.
Ooh, like that.
Right. The moment a rowdy, high-voltage electric field tries to enter the building, the bouncers instantly rush all the trouble to the outer walls. They absorb all the impact on the perimeter, so the VIP lounge in the middle stays perfectly calm and quiet.
That's a perfect analogy. And because the internal field is zero, Gauss's law dictates there can be no net charge anywhere in the interior of a solid conductor. All the excess charge just rushes to the absolute outer surface. It is entirely restricted to the skin of the metal.
Which the text highlights in Figure 511, showing the field pushing outward from a solid metal object. It points out that the field just off the surface of a solid metal is exactly twice as strong as the field of a floating sheet of charge in midair. But why double?
Think back to your bouncers. The local charges right on the surface push outward, but all the other charges distributed across the entirety of the metal object conspire to cancel the field entirely on the inside. To achieve that perfect mathematical zero on the interior, they have to push with equal force to the outside, doubling the effect on the exterior surface.
Which brings us to Figure 512, the empty cavity. If I take a solid chunk of metal, let's say it's shaped like a lumpy, irregular asteroid, and I carve out a hollow cave deep inside it, what is the electric field inside that cave?
As long as the cave is truly empty, with no separate charges suspended inside it, the field is absolutely zero. The outer shape of the conductor doesn't matter at all, and the shape of the cavity doesn't matter.
Well,
Because the electric field is zero everywhere inside the metal walls, the circulation of the field along those walls is zero. No positive and negative charges can hide on the inner walls, trying to shoot field lines across the empty space.
and this is the ultimate payoff of the entire chapter, isn't it? Shielding. This is exactly why a metal box perfectly shields delicate electrical equipment. Outside charges cannot reach the inside, and any charges inside a grounded shell cannot affect the outside. It's basically a two-way mirror for electricity.
Exactly. And it explains why Plimpton and Lawton could check Coulomb's law to such extreme precision. The hollow shell they used didn't even need to be a geometrically perfect sphere. If Gauss's law is exact, the field inside an empty conducting cavity of any shape is always exactly zero.
And that is why it is perfectly safe to sit inside the high-voltage terminal of a million-volt Van de Graaff generator. As long as you are surrounded by that conducting metal shell, the millions of volts stay entirely on the outer skin. The free electrons just keep the interior completely insulated from all the chaos outside.
Yeah, Gauss's law is so much more than an abstract equation. It is the dynamic reason your atoms hold together rather than statically collapsing. It's the reason hollow spaces inside metals are impenetrable safe zones from raw electricity. And it is the mathematical scalpel that allowed scientists to prove a fundamental law of the universe to 1 part in a billion.
We have covered incredible ground today, from the existential crisis of how matter exists, to infinite walls of red paint, to why you can survive artificial lightning. But as we wrap up this deep dive, I want you to think back to that microscopic boundary we discussed, that 10-14 centimeter line deep inside the nucleus where the proton smears out and the math seems to change its rules. It really leaves you wondering if the rigid, mathematically perfect laws that govern giant lightning-proof cages start to blur and bend when you look closely enough at the heart of matter. What other laws of our everyday reality are just waiting for us to zoom in close enough to see them break? Imagine standing on a beach, just looking out at all the sand. Now, try to calculate the exact gravitational pull of every single grain of sand on that beach. And you have to do it all at exactly the same time while they're all interacting with each other.
Right, which is, I mean, you wouldn't even know where to start. It's completely impossible.
Exactly. It's a total computational nightmare. But physicists actually face this exact kind of nightmare when they have to calculate the electric fields created by, millions upon millions of tiny charges.
Yeah, and they can't just throw their hands up and quit. They have to figure it out.
And today, we're uncovering the brilliantly clever cheats they invented to bypass that impossible math so they can actually map the invisible electric forces that shape our world. Welcome to today's deep dive.
Glad to be here.
We are exploring Chapter 6 from Volume 2 of the legendary Feynman Lectures on Physics. It's titled The Electric Field in Various Circumstances. And our mission for you today is to trace how we actually understand these fields.
Right, going from things as small as the water molecules inside your own body, all the way to the very first tools we used to literally see individual atoms.
Because it really is the ultimate puzzle. I mean, you aren't just measuring one static thing sitting on a table.
No, not at all. You're dealing with forces that interact with every other force simultaneously.
Right.
Every electron pushes on every other electron.
Right.
Which then moves, which then changes the field for everything else.
Yeah.
Which means they all move again.
It's just endless.
Yeah. Doing the math the hard way, tracking every grain of sand means you never, ever finish.
So we need to figure out the workarounds. And looking closely at the source material, the foundation of understanding this starts with acknowledging that isolated, completely, perfectly still single-point charges almost never exist in nature.
Right. Nature doesn't give us the easy math. In the real world, most matter we interact with is neutral overall.
But neutral doesn't mean boring, right?
Exactly. Not electrically boring anyway.
Right.
The text uses water, just good old H2O. It's a perfect example of this.
Because a whole water molecule is neutral, but the atoms inside it do not share their electrons equally.
Right, they really don't. The single oxygen atom acts like basically a charge hoarder. It pulls the negative electron cloud slightly toward itself.
Which leaves the two hydrogen atoms kind of exposed, right? With a slight positive charge.
Yeah, exactly. And that physical separation of charge within an otherwise totally neutral molecule, that creates what we call a microscopic dipole.
You have a distinct negative pole on one side and a positive pole on the other.
Right. And a glass of water is just packed with these microscopic dipoles all constantly sloshing around, interacting.
Okay, but calculating the total electric field of a messy cup of millions of water dipoles still sounds exactly like counting sand grains. How do physicists actually solve a system that complex?
Well, they use a technique called the large distance approximation.
Okay.
Which is really just a fancy way of saying you zoom out.
Zoom out.
Yeah. If you are trying to calculate the electric field of a complex arrangement of charges from far away, meaning a distance that is much, much larger than the tiny microscopic separation between the positive and negative ends.
Right. The fine details start to blur.
Exactly. All those fine details blur out completely. You no longer have to track every single proton and electron. The entire complex object just mathematically behaves like one simple, uniform dipole.
Oh, that makes sense. It reminds me of looking at a pointillist painting in an art museum.
Oh, yeah. Great analogy.
Like if you press your nose right up against the canvas, it's just this chaotic, overwhelming mess of individual dots of paint. It makes absolutely no sense at all.
Just noise.
Right. But the moment you step back to the other side of the room, those thousands of chaotic dots seamlessly resolve into a single, clear image. You can actually see the picture.
And the math reflects that visual blurring perfectly. Think about how forces behave as you move away from them. For a single, isolated point charge, the electric potential drops off steadily as you get further away.
Inversely with the distance, right?
Exactly. You double the distance, you have the potential. It's a very steady drop. But a dipole is different. A dipole has a positive end and a negative end, and they are constantly fighting each other.
Because they have opposite charges, they're pushing and pulling in opposite directions at the exact same time.
Right. Up close, If you are really near the positive hydrogen side of that water molecule, you feel that positive push much more strongly.
Because you're right next to it.
Exactly. But as you step back, as you zoom out, the distance to the positive end and the distance to the negative end, they become roughly the same from your perspective.
Oh, I see.
So their opposite poles start to almost perfectly cancel each other out.
So the field just vanishes?
Well, it fades out incredibly fast. Because of this cancellation, the electric potential of a dipole drops off inversely as the square of the distance.
Wow, okay.
And the electric field itself drops off even faster, inversely as the cube of the distance.
So just by taking a few steps back, mathematically speaking, the forces become so much easier to handle.
Yeah, the text actually mentions you can calculate the strength of this field using just a single value called the dipole moment.
Which is what, exactly?
You just multiply the amount of charge by the tiny distance separating the positive and negative ends. That's it.
Oh, wow. So you trade this totally impossible calculus for basic multiplication. That is quite the cheat code.
It is. But zooming out works beautifully for tiny, relatively rigid molecules like water. It completely falls apart when we scale up to solid metal conductors.
Right, because metals are different. Inside a piece of copper or steel, the charges aren't locked into little molecules.
No, the electrons in a metal can flow around completely freely.
So we can't just step back and blur our eyes because the painting itself is constantly rearranging.
Exactly. If you put a positive charge near a flat piece of metal, the free electrons in the metal will instantly feel that pull.
And they just start scrambling toward it.
Yeah, they scramble, they push, they pull on each other until they settle on the surface in a very specific locked arrangement. They naturally arrange themselves perfectly, so that the entire surface of the metal reaches a constant, uniform electrical pressure. Physicists call this an equipotential.
Equipotential. Equal potential everywhere on the surface.
Right, and nature calculates this instantly. The electrons just go to the path of least resistance until the internal field is zero.
But mathematically modeling exactly where all those millions of free electrons ended up, that would require endless guessing and checking.
It's agonizing,
Yeah.
which is why the source material outlines this famous bypass for it, called the method of images.
Okay, this part was wild to me. So let's say you have a single, real, positive point charge sitting in front of a flat, grounded metal plate. To figure out the electric field, you are supposed to pretend the metal plate is a mirror.
Yeah, a literal mirror. You ignore the millions of complicated surface electrons on the metal entirely. Just forget they exist.
Just ignore reality. Got it.
Sort of, yeah. Instead, you imagine a fake, equal but opposite image charge. Because your real charge is positive, you create a fake negative charge. And you place this fake negative charge the exact same distance behind the metal plate, right where its reflection would be if the metal were a mirror.
Wait, I have to stop you here. How does making up a ghost charge, putting it in a fake location behind a solid wall, solve a real-world physics problem? Like, how does a fake charge give you the right answer for the real forces involved?
I know, it sounds like we're just making things up, but think about the physical geometry of the scenario you just set up. You have a real positive charge on the left and your fake negative charge on the right.
Okay, I'm picturing it.
Because they are equal and opposite, there is an invisible, perfectly flat plane exactly halfway between them where their pushes and pulls perfectly balance out to zero. That halfway point is a zero potential surface.
And the flat metal plate we were dealing with is also a zero potential surface because it's grounded.
Exactly. Slipping a flat piece of metal exactly onto that halfway line doesn't change the physics on the outside at all.
So mathematically, it doesn't matter if it's millions of scrambling electrons or one fake mirror charge.
Right. The electric field outside the conductor, the one created by the real charge and all those complicated surface electrons, is mathematically identical to the field that would be created by just the real charge and your one fake mirror charge.
That is genuinely brilliant. You don't calculate the metal at all. You just engineer a fake scenario that creates the exact same empty space conditions.
It perfectly calculates the force of attraction, the real charge feels, pulling it toward the plate. It is one of the most elegant cheats in physics.
And it gets even more fascinating when you apply it to curved surfaces, right? Like placing a point charge near a conducting metal sphere.
Oh yeah, spheres make it tricky. A flat mirror won't work to simulate a curved equipotential surface.
Because it's curved.
Right. You still use a fake image charge, but you have to place it at a very specific mathematical point inside the sphere. And you actually have to shrink its strength relative to the real charge just to make the mathematical forces balance out into a spherical shape.
And the text mentions applying this to two charged spheres facing each other. And the complexity of that just explodes.
It really does. Because if you place an image charge inside the first sphere to balance the potential, that fake charge now acts like a real charge from the perspective of the second sphere.
Oh no, so it reflects into the second sphere, creating a new, smaller image charge over there.
Which then messes up the balance of the first sphere again.
Right.
So that second fake charge reflects back into the first sphere, requiring a third, even smaller fake charge.
Feynman compares this to the label on an old baking powder box. Like, the label has a picture of the baking powder box, and on that picture is a tiny picture of the box just going on forever.
Exactly. To solve the physics of two simple metal balls, you effectively have to calculate an infinite shrinking tunnel of Gauss charges bouncing back and forth.
That is mind-bending. Does it literally take forever to calculate?
Well, practically no. The math converges quickly because the charges get smaller each time, so you don't literally calculate to infinity.
Yeah.
But conceptually, yeah, you are building an infinite house of mirrors just to avoid calculating the actual free electrons.
Wow. Well, now that we know charges naturally arrange themselves on flat metal surfaces to cancel out fields, we can actually exploit that behavior, right? To store those forces. Which brings us to the parallel plate condenser, or what modern electronics call a capacitor.
Storing charge is a massive physical challenge. If you attempt to pump electrical charge onto a single piece of metal like just a standalone sphere, the voltage skyrockets rapidly.
And voltage is basically the electrical pressure, right?
Exactly,
Wow.
because you are packing all these identical charges into one space, and they fiercely repel each other. The more you add, the harder they push back.
They want to get away from each other.
Right. And eventually, the pressure gets so high that the charge violently bursts off the sphere into the surrounding air as a spark.
Okay, so it's a lot like pouring water into a tall, incredibly narrow glass. You add just a little bit of water, which is our electrical charge here, and the water level or voltage shoots straight up to the brim, ready to spill over.
That's a really good way to visualize it.
But a condenser completely alters the physical geometry to prevent that spillover. Instead of a narrow glass, a condenser acts like a massive, wide, shallow reservoir. You can pump huge amounts of water into it, and the level barely rises at all.
And physically, a parallel plate condenser achieves this by placing two large, flat metal plates extremely close to each other, just separated by a tiny gap of air or insulation.
Okay.
You put positive charge on one plate and an equal negative charge on the other. Because the plates are so incredibly close, the positive and negative charges strongly attract each other right across that gap.
They pull on each other so hard across the divide that they essentially just hold each other in place on the inner surfaces of the plates.
Exactly. They are so distracted by the opposite charges across the gap that they basically ignore the fact that they are packed in tightly next to repelling charges on their own plate.
They're too busy looking across the street.
Yeah, exactly. And this physical distraction allows you to store a massive amount of total charge while keeping the voltage. That outward pressure to spark and escape very, very low.
And the capacity to store this charge is measured in units called farads, right?
And in a pure mathematical model, this capacity relies entirely on two simple geometric factors, the total surface area of the plates and the distance separating them.
The source gives a great intuitive benchmark for this scale, too. If you build a condenser with plates that are exactly 1 square centimeter in area and separate them by just a 1 millimeter gap, you get a capacity of about 1 picofarad.
Or, as the text affectionately calls it, the older term, a microfarad.
Microfarad. I kind of love that. But of course, real-world engineering always introduces wrinkles into perfect math.
Always. In a purely theoretical parallel plate condenser, the electric field is totally uniform. It's completely contained, perfectly straight between the plates, and it drops to absolute zero everywhere outside.
But nature absolutely hates sharp corners.
It really does.
This is the edge effect, right?
Yep.
The math assumes the field lines just cleanly stop at the exact edge of the metal.
Right. But physically, at the very edges of the plates, the electric field lines bulge outward into the surrounding space before curving back to the other plate.
They kind of spill over the sides.
Yeah. And because the field occupies this extra space at the fringes, the actual physical capacity of the plates to store charge is always slightly higher than the basic formulas predict.
So smooth. Flat plates are clearly the ideal environment for keeping massive amounts of charge calm and contained.
Definitely.
But what happens if we intentionally disrupt that calm? Like, what if we introduce a sharp point to a charged piece of metal?
Well, a sharp point is the absolute enemy of safely storing charge. We established that charges of the same sign on a conductor desperately want to get as far away from each other as geometrically possible.
Right.
So if you introduce a sharp point or a needle on a charged object, a disproportionately massive amount of charge rushes to the very tip of that
Well,
needle.
why do they all crowd onto the tip to get away from the crowd? That seems counterintuitive.
It does, but think about it geometrically. The tip of a sharp point is technically protruding as far away as possible from the vast majority of the bulk surface area.
Oh, I see. It's the furthest point out.
Right. They push each other outward, and millions of them end up trapped at the very end of the needle. And because so much charge is jammed into such a microscopic, tightly curved area, the electric field radiating just outside that point becomes intensely magnified.
So the sharper the needle, the tighter the curve, and the higher the electric field becomes.
Exactly. And if that microscopic field gets too high, we encounter what the text calls a high voltage breakdown.
Which is bad.
Very bad if you don't want a spark. The concentrated electric field at the tip becomes so powerful it actually reaches out into the surrounding air, grabs a stray loose electron, and accelerates it to terrifying speeds.
And when that hyperaccelerated electron inevitably smashes into a neutral air atom.
It hits with so much kinetic force that it knocks another electron loose from that atom.
Oh, wow. So now you have two fast electrons.
Right. They accelerate, they smash into two more atoms, knocking loose two more electrons, and it just cascades. It creates a violent exponential chain reaction.
An avalanche of electrons.
Precisely. And in the macro world, we perceive this microscopic avalanche as a visible spark, or basically miniature lightning.
And for decades, engineers just viewed this phenomenon as a dangerous, destructive nuisance. Like, high-voltage equipment had to be perfectly smooth and rounded specifically to avoid these breakdowns.
Yeah, sharp edges were a huge design flaw.
But then, in 1936, a physicist named Erwin W. Muller realized he could weaponize this terrifying, highly concentrated electric field at a sharp point.
This is one of my favorite parts of the whole volume.
He used it to invent the field emission microscope.
The elegance of Miller's instrument is staggering, especially when you consider how simple the physical setup is compared to the monumental thing it achieved.
It really is. So Miller took a tungsten needle and etched it down until the tip was microscopic. The text notes the tip was just 1,000 angstroms wide.
Which means the point was only a few thousand atoms across, just unimaginably sharp.
Right. And he placed this incredibly sharp needle dead center inside a hollow glass sphere. He pumped all the air out to create a hard vacuum and then coated the inside of the glass with fluorescent paint.
Sort of similar to how old fixed CRT television screens worked.
Exactly. And then he applied an absolutely massive voltage difference between the needle and the screen. He drove the field up to 40 million volts per centimeter.
40 million.
Yeah.
It's almost hard to fathom. The electric field packed onto the microscopic tip of that tungsten needle became so incredibly intense that it actually overpowered the atomic forces holding the solid metal together.
It literally ripped electrons right out of the surface of the solid tungsten.
It yanked them straight out into the vacuum chamber.
And because electric field lines radiate perfectly straight outward from a sharp, rounded tip, the ripped electrons shoot in perfectly straight lines across the vacuum.
Right. They fly across, hit the fluorescent paint on the glass, and light it up.
You are effectively projecting a vastly magnified, glowing shadow of the needle's tip directly onto the inside of the glass sphere.
You are. But the problem with the early versions of this device was clarity.
It was too blurry, right?
Yeah. Electrons are incredibly light, fast particles. And according to the laws of quantum mechanics, extremely light particles traveling through space behave a lot like spreading waves.
Okay, wave behavior.
This wave-like behavior causes diffraction, which basically means the electrons smear out as they travel across the vacuum.
They don't stay in a perfectly tight line.
Exactly. And on top of that, electrons bouncing around inside the hot metal have a little bit of random sideways motion when they get ripped out. So the final image on the glass was always going to be blurry. You could see the rough shape of the tip, sure, but the individual atoms remained hidden in this smear of light.
But Miller didn't stop there. He made a brilliant final tweak to his own invention, what we can call the helium upgrade.
This is the genius move.
He reversed the polarity of the voltage, and he pumped a tiny amount of neutral helium gas into the vacuum chamber.
Reversing the polarity changes everything. The intense electric field at the tip no longer rips negative electrons out of the metal. Instead, it turns the needle highly positive.
Okay, so it just sits there.
It sits there, highly positive, waiting for a neutral helium atom drifting around the chamber to randomly wander too close to the sharp tip.
And when the helium atom hits that 40 million volt field,
The field is so viciously strong it rips an electron right off the helium atom.
wow. And stripping that electron turns the neutral helium atom into a positively charged helium ion.
Right. And because the needle is also highly positive, they repel. It instantly and violently repels that positive helium ion, shooting it outward in a perfectly straight line to smash into the fluorescent screen.
But why does swapping electrons for helium ions fix the blurry image? I mean, they're both just charged particles flying at a screen.
It entirely comes down to mass. A helium ion is thousands of times heavier than a tiny electron.
Oh, of course.
Because it is so massive, its quantum wave-like properties are drastically reduced. It doesn't spread out like a wave anymore. It travels like a heavy, solid bullet.
So there's virtually no diffraction.
None. Furthermore, its heavy mass means it completely shrugs off any random sideways thermal motions. The quantum smearing effect disappears entirely.
It just barrels straight ahead, and the result is one of the most stunning visuals in the history of physics. Figure 617 in the source material actually shows a photograph taken with this technique.
It's beautiful to look at.
It achieves a magnification of 2 million times, which at the time was 10 times better than the most advanced electron microscopes of that era.
It's just incredible.
By using a sharp needle, a glass bulb, and a wisp of helium, humans were able to literally look at the individual atoms of a piece of metal for the very first time.
And what makes that image so profoundly important, and Feynman points this out beautifully in the text, is the undeniable geometry of the pattern you see.
Right, it's not just random.
Exactly. You don't just see a random scattering of glowing dots. You see distinct bright spots arranged in perfect, symmetrical, concentric rings.
Like a target.
Yeah. Imagine a box perfectly packed with identical spherical bowls sitting in neat rows. If you conceptualize cutting a curved, spherical section out of that tight arrangement, the exposed balls on the surface will form exactly those step-like concentric rings.
Wow. So seeing that glowing pattern proved visually, without any doubt, the highly ordered crystal lattice structure of solid matter.
It proved they were there and exactly how they were stacked.
We started this deep dive looking at an impossible computational nightmare, trying to calculate the gravitational pull of every single grain of sand on a beach at once.
Right.
But by zooming out to understand how dipoles naturally cancel each other out, and by using the mathematically brilliant mirror trick of image charges to bypass complex conductors.
Physicists found ways to navigate the noise. They tamed the impossible math to understand the physical mechanisms of the real world.
We saw how exploiting flat metal plates allows us to safely store incredible amounts of charge in condensers.
And ultimately, how weaponizing the immense, highly concentrated, and honestly dangerous fields at the tip of a sharp needle allowed us to pierce the veil of the microscopic world.
Which brings us to a final thought for you to ponder. The exact same invisible electric fields we've been exploring today, the forces that pull water molecules into sloshing dipoles, the forces that balance perfectly on the surface of flat metal plates, and the forces that violently jump as a spark off a sharp point.
These are the exact same forces holding your entire life together right now.
The water in your cells, the screen you were looking at, the floor beneath your feet, it's all just an intricate microscopic balancing act of electric charges pushing and pulling in the dark.
And if all the physical matter in the universe is really just a complex web of these invisible electric fields constantly fighting and balancing against each other across mostly empty space, how solid are you really?
Something to keep in mind the next time you lean against a wall and expect it to hold you up. Thank you for joining us on this deep dive into the invisible forces that shape our reality. We'll see you next time.
So if you zoom in close enough, the very device you are using to listen to this right now is literally ringing like a bell. It's vibrating with these invisible quantum waves of dense, solid plasma.
Yeah, which is wild to think about.
Right. I mean, we usually think of solid metal as, well, solid. But beneath the surface, it's just this chaotic ocean of charge. Today, we are opening up some of the most fascinating pages of physics history to find out why. Welcome to the Deep Dive.
Glad to be here.
Our mission for this session is to wade directly into that messy reality. We're pulling out a stack of incredibly intense notes. Specifically, we're looking at Chapter 7 from Volume 2 of Richard Feynman's classic lectures, and we're unpacking the hidden rules of how electric fields behave in the real world.
Yeah, and we are moving way beyond those, idealized textbook scenarios, the ones where electrical charges just sit perfectly still in a pristine vacuum.
Right, the easy stuff.
Exactly. The situations Feynman tackles in this chapter, they involve charge distributions that actively react to the very fields they create. We're looking at moving electrons, boiling fluids full of thermal energy, and some deeply elegant mathematical workarounds to map it all out.
And by the time we finish this deep dive, you'll see how a completely bizarre mathematical miracle allows engineers to focus beams of subatomic particles flying at the speed of light.
It really is a miracle, mathematically speaking.
It's so cool. We'll also look at why AM radio waves bounce off the sky while, satellite signals punch straight through it, how a sudden shift in invisible electrical shielding causes vital protein chains in your body to violently snap and coil up.
That biological connection is just, it's fascinating.
Oh, absolutely. And finally, we'll see why a simple mesh screen can trick the universe into treating it like a solid vault of heavy metal. Now, Feynman's text here is pretty dense, right? It's packed with complex variables and intricate diagrams, but we are going to tear down the formulas and really look at the physical gears turning underneath.
I think the best place to start is with the fundamental problem of plotting an electric field around a conductor. I mean, to calculate the field, you generally need to solve Laplace's equation to find the equipotential surfaces.
Those are the regions where the electrical pressure is balanced, right?
Yeah, exactly. But here's the catch. You can't map the field without knowing exactly where the charges are.
And because it's a conductor, those charges are allowed to move freely. They instantly scatter to repel one another, and they're constantly shifting until they reach equilibrium.
Right. It's a total chicken and egg problem. You don't know the final charge distribution until the field is balanced, but you can't balance the field without knowing the charge distribution.
And trying to solve that in 3 dimensions using Laplace's equation directly is, well, it's a nightmare of differential calculus.
Oh, it's brutal. It generally requires immense computational power. However, Feynman highlights this brilliant backdoor for 2-dimensional problems.
Scenarios like infinitely long wires or cylinders, right? Where we can just ignore the ends entirely.
Exactly. You just look at the cross-section on an XY plane. The workaround relies entirely on complex variables. We basically take the coordinates of our plane and combine them into a single complex variable, z equals x plus iy.
So instead of grinding through Laplace's equation the hard way, we can use the Cauchy-Riemann equations.
Yes. If you take any analytic mathematical function, let's just call it f of z, and plug that complex variable into it, the function will inevitably spit out a result that can be cleanly separated.
Separated into a real part, which we call u, and an imaginary part, which we call v.
Right, and the underlying math here dictates something practically miraculous. Because f of z is analytic, both the u component and the v component will automatically perfectly satisfy Laplace's equation.
Wow, so you don't even have to prove it or force it to work.
Nope, the geometry of complex functions just guarantees it. Furthermore, the curves plotted by u and the curves plotted by v, they will always be perfectly orthogonal.
Meaning they cross each other at exactly right angles everywhere on the plane, which maps flawlessly onto physical reality. Because in electrostatic physics, electric field lines always intersect equipotential surfaces at exactly 90 degrees.
They do. So this math trick basically flips the entire engineering process upside down.
I like to think of it like playing a game of mathematical Jeopardy.
Oh, how so?
Well, you don't start with a wildly complicated physical shape and torture yourself trying to derive the math for it. You just start with this simple, arbitrary math function-like. That is your answer. And then you graph it to see what physical shape it creates. That physical shape is the question.
That's a great way to put it. You get the field lines and the equipotential surfaces in one stroke. Let's look at the first major example Feynman provides, which is simply squaring the complex variable. The function is f of z equals z squared.
Okay, so when you separate the u and v components there and graph them, like he does in figures 7.1 and 7.2, the math draws this series of sweeping hyperbolas.
Right, and the geometry of those hyperbolas solves a massive problem in particle physics.
Oh, the particle accelerator stuff.
Yeah. In a particle accelerator, you have a beam of protons traveling at nearly the speed of light, and their natural tendency is to repel each other and drift away from the center axis.
Because they're all positively charged.
Exactly. You need a way to funnel them back to the center continuously. And it turns out the electric field generated by hyperbolic electrodes has a very specific proportional characteristic.
The intensity of the field grows linearly the further you move from the center, right? It acts as a perfect harmonic oscillator.
Right, right.
So if a proton drifts just a millimeter off-center, it feels a gentle nudge pushing it back. But if it drifts heavily off-center, it slams into a proportionally massive field that violently shoves it back into alignment.
Exactly, which is the quadrupole lens shown in figure 7.3. By shaping 4 metal electrodes into the exact hyperbolas spat out by our z-squared function, we create an absolutely perfect, self-correcting magnetic funnel for the beam.
It's incredibly elegant.
Yeah.
You really get a 2-for-1 deal with the math.
You do, but you have to interpret the graphs carefully. Because U and V both satisfy Laplace's equation, you actually get 2 entirely different physical realities from a single function, depending on how you assign the variables.
Right, and Feynman illustrates this beautifully with the square root function. F of z equals the square root of z.
Yeah, if you look at figures 7.4 and 7.5, the curves generated by the square root wrap tightly around the origin point.
So if you decide that the U curve represents your solid piece of metal, the resulting field lines describe the electrical environment around a sharp 90-degree bend, like the outside corner of a metal box.
But, and this is the cool part, if you simply flip your interpretation and say the V curve represents the solid metal, the exact same graph suddenly describes the electric field wrapping around the microscopic razor-thin edge of a flat conducting plate.
The mass doesn't change at all, but the physical boundary conditions you extract from it are entirely distinct. It's wild.
It really is.
But, this complex variable trick is a massive shortcut. But it still assumes our environment is perfectly static. We are plotting solid, unmoving metal shapes.
Right, which isn't always how the real world works.
Exactly. The reality of the universe is far more chaotic.
Yeah.
If we want to understand how fields behave in the wild, we have to look at environments where the charges themselves are the fluid. We have to look at plasmas.
And the classic example here is the Earth's ionosphere. High-energy ultraviolet radiation from the sun essentially strips electrons away from gas molecules in the upper atmosphere.
Leaving a massive soup of heavy, positively charged ions and incredibly light, unattached, negatively charged electrons.
Right. And because the ions are thousands of times more massive than the electrons, their inertia keeps them relatively locked in place. They act as the background scaffolding.
But the free electrons are highly mobile. So if some disturbance, say a passing electromagnetic wave, pushes a cluster of electrons closer together, their immense mutual repulsion violently drives them apart again to restore equilibrium.
But they don't just casually return to their original positions and stop. That's the key. The electrons possess mass.
Oh, right. So as they accelerate away from each other, they gain kinetic energy.
Exactly. They completely overshoot the point of equilibrium, build up pressure in the opposite direction, mutually repel again, and snap back.
It's pure inertia. It really reminds me of pushing a heavy, fast-swinging saloon door.
The saloon door.
Yeah, like you shove it open, it swings back, overshoots the door frame, swings out the other way, and just oscillates back and forth until the energy dissipates.
That's actually a great analogy. That exact oscillation of charge creates an electrical wave, and the speed of that bouncing is what physicists call the plasma frequency, denoted as omega sub p.
And that plasma frequency is heavily dependent on the density of the electrons, right?
Very much so. The more densely packed the electrons are, the stronger the repulsive force and the faster the system oscillates. It acts like a much stiffer spring.
And this invisible frequency actually dictates our global communications.
It does.
Because that layer of plasma acts like a selective filter for electromagnetic waves. If you want to communicate with the GPS satellite out in orbit, your radio wave must oscillate at a frequency strictly higher than the ionosphere's plasma frequency.
Right. To stick with your analogy, it's like firing a bullet through those swinging saloon doors. The wave moves so fast that the plasma electrons literally don't have the time to react and bounce back, which allows the signal to punch straight through into space.
Wow. But conversely, AM radio broadcasts use frequencies lower than the plasma frequency.
Exactly. When a low-frequency radio wave hits the ionosphere, it's like trying to slowly push that saloon door. The electrons have plenty of time to react, oscillate, and push back.
So the ionosphere effectively acts as a solid, conductive mirror.
Yes, reflecting the radio signal back down to Earth, which is exactly how you can tune into a station broadcasting from hundreds of miles beyond the horizon.
It's just staggering to think about the sky acting as a tuned electrical mirror. But it gets even stranger because these plasma dynamics aren't just happening in the upper atmosphere, are they?
Nope. They are happening in the device playing this audio right now. This is where we get back to that quantum ringing you mentioned at the start of the deep dive.
Right. Solid metals.
Yeah. Solid conductors like blocks of aluminum or copper are structurally just extremely dense plasmas. The positive atomic nuclei form a rigid crystal lattice, but the outer valence electrons are completely detached, roaming freely throughout the metal.
And the density of those free electrons in a solid metal is astronomically high, which means the spring is incredibly stiff and the internal plasma frequency is wildly fast.
Super fast. But for a long time, observing that internal oscillation was pretty difficult.
Until 1953, right? When physicists David Bohm and David Pines provided definitive proof.
Yes. They shot high-energy electrons completely through thin films of solid aluminum. Now, if the metal were just a passive medium, the incoming electron would just scatter and lose its kinetic energy in a smooth, continuous spectrum as it bumped into things.
But that's not what happened. The electrons emerged on the other side, having lost energy in highly specific, discrete quantum jumps. An electron would drop exactly 15 electron volts of energy all at once.
And that 15 electron volt drop corresponds flawlessly to the exact amount of energy required to excite the internal plasma frequency of aluminum.
That is wild. The passing electron physically plucks the internal plasma like a guitar string, leaving a wake of resonating, oscillating charge behind it as it exits the material.
That's exactly what's happening.
Okay, so we have pure inertia driving high-speed oscillations in vacuum-like plasmas. But let's change the physical medium again. What happens when we introduce a dense thermal environment?
Ah, right. If we look at charged particles suspended in a colloidal suspension, we introduce the chaotic boiling energy of temperature into the mix.
And a colloid is basically just microscopic particles evenly dispersed throughout a liquid like water.
Wow.
Normally, gravity would pull these particles down into a sludge at the bottom.
But in a stable colloid, all the particles carry the same electrical charge. Let's say they're all positive. Their mutual electrostatic repulsion is strong enough to fight off gravity, keeping them suspended and equidistant from one another.
The environment is stable because every particle can feel the repulsive field of its neighbors.
Right, but Feynman introduces a phenomenal wrinkle here. What happens when you dissolve an electrolyte, like ordinary salt, into that water?
Okay, so the salt crystals dissociate into millions of free-floating positive and negative ions.
Yes. And this triggers a really complex tug-of-war governed by statistical mechanics. The heavy, positively charged colloidal particle is going to strongly attract the small, negative salt ions, while violently repelling the positive salt ions.
So the negative ions physically swarm the colloidal particle. I love this part. It's exactly like a mega celebrity walking into an incredibly chaotic party.
A celebrity?
Yeah, so the positively charged particle is the celebrity, and the negative salt ions act as this aggressively tight security detail swarming around them. From across the room, the rest of the partygoers can't even tell the celebrity is there because the security detail completely obstructs the view.
Oh, I see. That's very accurate. The swarm of negative ions mathematically cancels out the electric field of the positive particle. If you measure the potential directly at the surface of the particle, the field is intense.
But as you move away through the ion cloud, the electric field strength doesn't just fade linearly, it decays exponentially, right? Feynman graphs this in figure 7-7.
Exactly. The field just drops off a cliff, and physics assigns a specific variable to the thickness of that security detail. It's called the W length, represented by D.
The W length.
Right. It tells us exactly how far away from the particle you have to be before the electric field is effectively zero.
And it represents a kind of competition, doesn't it?
It does. It's fundamentally a ratio. It represents the competition between the thermal energy of the water, which is violently bumping into the ions and trying to disperse the swarm, and the electrostatic attraction, which is trying to pull the swarm tighter.
So if you add more salt to the water, you increase the density of available ions, the electrostatic attraction wins out, and the dV length shrinks rapidly.
The security detail gets much tighter and denser, and the physical consequence of this is dramatic. If you keep adding salt, the dV length becomes smaller than the physical distance between the colloidal particles.
Suddenly, the particles are completely blind to each other. Their fields are entirely masked.
Exactly. And without that long-range repulsion keeping them apart, the random thermal agitation of the water violently smashes them together.
Wow.
Once they touch, short-range attractive forces take over. They clump into massive aggregates and precipitate out of the solution, falling to the bottom as sludge.
And in chemistry, this phenomenon is literally known as salting out of solution.
Yes, it is.
But the mechanism of salting out isn't just a quirk of muddy water. It is a foundational principle of human biology.
This is where it gets really important.
A protein is essentially a massive, complex chain of amino acids, right? And for a protein to function, it often has to remain stretched out and unspooled. It maintains this structure because there are negative charges spaced out along the chain, and their mutual repulsion keeps the protein taut.
Exactly. And the surrounding cellular fluid naturally contains a specific concentration of salt ions, which gives the fluid a specific Debye length.
So if that salt concentration spikes, the Debye length drops instantly. The negative ions in the fluid aggressively swarm the charges on the amino acid chain, and the electrostatic repulsion masking vanishes.
Right. And without the internal tension holding it open, the complex protein chain instantly collapses. It folds and coils up into a completely useless knot.
It's mind-blowing. A subtle shift in the invisible ionic shielding physically rewrites the shape of the building blocks of life.
It demonstrates profound continuity in physics. I mean, the exact same electrostatic principles managing the behavior of a block of aluminum dictate the folding of biological tissue.
Which perfectly leads us to the final piece of the puzzle. We just explored how a fluid cloud of random thermal ions can perfectly mask an electric field in water. The obvious engineering question is, can we construct a rigid macroscopic structure to perform that exact same masking trick in the air?
Yes, we absolutely can, and the solution is incredibly ubiquitous. Instead of an ion cloud, engineers use a grid of uniformly spaced, parallel conducting wires.
Think of a standard copper window screen, or the mesh panel on the front of a microwave oven.
Exactly. Feynman diagrams the cross-section of this in figure 7 through 8. It looks like a row of charged dots. Now, if you take a microscopic probe and measure the equipotential surfaces right next to the wires, the field is wildly complex.
Because the lines of force wrap tightly around each individual wire and bulge deeply into the empty gaps between them.
Right. However, mathematically, we can analyze that complex field using Fourier's theorem.
Fourier analysis.
Yeah. It allows us to break the lumpy, uneven field down into a superposition of different harmonic waves. You have the base average field, which is the n equals 0 term, and then a series of higher harmonics representing the spatial bumpiness caused by the alternating wires and gaps.
And because the overall field must still satisfy Laplace's equation, those alternating pushes and pulls in the physical geometry force a specific mathematical outcome, don't they?
They do. The spatial variations decay exponentially as you move outward along the z-axis. The opposing vectors physically cancel each other out.
So the characteristic distance for this drop-off, z sub 0, is simply the spacing between the wires divided by 2 pi n.
Right. And because the decay is exponential, within a distance of just 2 or 3 wire spacings away from the grid, the higher harmonics vanish entirely.
It's the exact same principle as looking at a highly pixelated digital image, or the weave of a fabric. Like, if your eye is pressed directly against the screen, you see every harsh, jagged pixel and the dark gaps between them.
But if you take just a few steps back,
the alternating light and dark spaces blend together, and your eye perceives a perfectly smooth, solid color. The electric field smooths itself out identically.
Exactly. If your wire mesh has holes that are 1 millimeter wide, you only have to move a few millimeters away before the electric field is utterly indistinguishable from the field generated by a solid, continuous plate of heavy metal.
And this mathematical reality saves billions of dollars in engineering. I mean, when hospitals build rooms for MRI machines or laboratories need to shield highly sensitive quantum electronics from outside interference, they don't entomb the rooms in solid, enormously expensive, multi-ton copper vaults.
No, they just line the walls with lightweight, cheap copper mesh.
As long as the sensitive equipment is sitting just a few millimeters away from the wall, the grid effectively tricks the surrounding universe into treating it like an impenetrable solid shield.
It really is the ultimate application of mapping the field geometry. By understanding how the wavy variations exponentially cancel themselves out, we can manipulate the boundary conditions of reality with minimal material.
Well, we've covered an immense amount of ground today. We started by bypassing Laplace's equation entirely, using complex variables to sculpt the perfect harmonic fields for focusing particle accelerators.
We covered a lot, yeah.
We mapped the literal inertia of electrons to understand how plasma frequencies allow AM radio waves to bounce over the horizon, and how high-speed electrons ring the solid plasma inside heavy metals.
And we saw how the statistical mechanics of the Debye length dictates whether a protein chain remains viable or collapses into a knot.
Right. And we finish by proving how a simple chain link pattern flawlessly mimics a solid vault.
You know, the interconnectedness of all these concepts leaves us with a truly compelling thought to mull over.
Oh, what's that?
Well, if we possess the mathematical tools to understand these mechanics so precisely, what does the next generation of materials science actually look like? I mean, if we can manipulate the W length in biological fluids, could we develop therapies that force misfolded proteins to uncoil on command?
Wow, that would change medicine entirely.
Right. Or could manipulating localized plasma frequencies in solid metals allow us to engineer programmable matter that actively tunes its own structural properties in real time?
That is something to think about. You know, the textbook environment where charges sit quietly on flat planes is crucial for learning the basics. But it's really only when you step into the messy, chaotic, dynamic reality of thermal fluids and quantum inertia that the true power of physics reveals itself. Thank you for joining us on this deep dive. Keep questioning the mechanics behind the curtain, and we will see you next time. Imagine holding your hands apart and you're trying to assemble a physical object, right? But completely out of pure invisible force.
Like no physical material at all, just force.
Exactly. Not clay, not wood, just sheer invisible repulsion pushing back, fighting your hands every single millimeter of the way.
It would be exhausting, honestly.
It really would. And today, our mission in this deep dive is to explore exactly that, electrostatic energy. We're going to look at how calculating the energy of, interacting charges lets us understand pretty much everything.
Right. From the literal crunch of a salt crystal in your food all the way down to the microscopic size of an atomic nucleus.
Yeah. And spoiler alert for you listening, we're also going to see how it eventually leads to a mathematical crisis that just completely breaks classical physics.
It really does. It's a fundamental problem.
Okay, let's unpack this. To start, to build anything out of a resisting force, you have to do work, right?
Exactly. And the foundational concept we are pulling from Chapter 8 of the Feynman Lectures on Physics is stunningly simple. The total energy of any system of charges is really just, well, it's nothing more than the sum of the work required to bring each pair of those charges together.
From an infinite distance apart.
Right. We're taking a concept you probably already know from mechanical systems, like the physical work it takes to lift a heavy weight against gravity and applying it directly to electrical systems.
Which makes sense. Force is force.
Yeah, and the single idea, which is given as equation 8.3 in the text, is the masterpiece for our entire discussion today.
But before we can tackle real-world atoms, we have to start conceptually small. Like, we need to understand how this energy scales with simple geometric shapes.
Right, the textbook examples. Like a solid sphere of charge.
Yeah. Looking at Feynman's figure 8.2, it outlines the mathematical process of building a uniform sphere of charge from scratch. And my brain immediately went to making a gobstopper candy, or, dipping a candle.
Oh, that's a great analogy.
You start with absolutely nothing at the center, radius 0. Then you bring in a tiny speck of charge from infinity and lay it down. Then you bring in the next infinitesimally thin spherical shell of charge and wrap it around the first.
And every single time you add a layer, the repulsion gets stronger. The accumulated charge in the center is, well, it's actively pushing against the new layer you were trying to add.
So you are constantly doing work against that growing repulsion, adding it layer by layer, all the way out to your final radius. It must take a massive amount of hypothetical effort.
It does. And by mathematically summing up the work for all those continuous layers, so integrating from a radius of 0 out to your final radius A, you find a very elegant result.
What does the math look like?
The total energy required to assemble that sphere is proportional to the square of the total charge and inversely proportional to the radius. So the bigger the charge, the harder it is to build.
Right.
But the true power of this energy concept becomes clear when we move from hypothetical spheres to flat plates, like in condensers or what we typically call capacitors today.
Okay, yeah.
The energy equation for a condenser is straightforward. It's 1/2 times the charge squared, divided by the capacity of the plates.
And here's where physicists use a really neat trick to solve real-world engineering problems without going completely insane.
Yes, the principle of virtual work.
Let's say you want to know the actual physical force pulling two oppositely charged plates together. You could try to calculate the microscopic pull of every single individual electron on one plate against every single proton on the other.
Which would be impossible.
It would be an absolute vector calculus nightmare. You'd be tracking billions of varying angles and distances. Instead, you just imagine moving the plates a tiny infinitesimal distance apart. You pretend to do physical mechanical work.
Right, because the total energy of that isolated system must be conserved. So the tiny bit of mechanical work you just imagined doing has to exactly equal the change in the electrostatic energy of the condenser.
You completely bypass all the messy microscopic vectors.
Exactly. You just look at the change in the total energy formula and the physical force falls right out of the equation.
You can even use this virtual work trick to find the rotational force, the torque, on a variable capacitor with pivoting plates, like the one shown in figure 8.3.
Oh yeah, instead of imagining pulling them apart in a straight line, you just imagine twisting them a tiny fraction of a degree. The change in energy gives you the torque. It's brilliant.
It really is. But looking at the final result of the straight line force calculation, I have to push back on something in the text.
I think I know what you're going to say. The factor of 1/2.
Yes. The math says the force on one plate of that condenser is 1/2 times the total charge times the electric field. So force equals 1/2 QE0. Wait, shouldn't the force just be the total charge times the electric field?
Yeah.
Why exactly 1/2? Where do we lose half the force?
Well, we didn't lose it. We have to remember that physical reality has depth. We often draw electric charge as a purely mathematical two-dimensional plane on the surface of a metal plate.
Right, like a flat sheet.
But it isn't two-dimensional. That charge exists in a very thin but physically real three-dimensional layer on the surface of the metal conductor.
Ah, because charges inside a conductor are free to move.
Yeah.
If there were a strong internal field pushing them, they would just, flow until they hit the very edge and cancel that internal field out.
You've got it. Figure 8.4 illustrates this beautifully. If you go just inside the conductor itself, behind the surface layer, the electric field is 0. But if you step just outside the plate, into the empty gap between the two plates, the field is at its absolute maximum strength, E0.
Okay, so if I am an electron actually sitting inside that microscopic surface layer of charge, I'm not feeling the full force of E0.
No, you are feeling a gradient. As you cross through that incredibly thin physical layer of surface charge, the field is transitioning. It's ramping up from 0 on the inside edge to E0 on the outside edge.
Oh, wow.
The average field acting on the millions of charges packed into that depth is exactly halfway between 0 and maximum, hence the factor of 1/2.
That makes perfect sense. The math isn't broken. It's just accurately reflecting the physical depth of the surface. So we've built our hypothetical spheres, we've figured out flat plates, and we understand the virtual work trick.
Yep.
Does this macroscopic geometry-based math actually work for complex microscopic things like, actual atoms?
It does. Our goal here is wildly ambitious.
Good.
We are going to calculate the exact amount of energy needed to vaporize a macroscopic crystal of sodium chloride, basically table salt, into a cloud of isolated atomic dust.
Mathematically, you want to calculate the force of billions of individual atoms pulling and pushing on each other in a literal grain of salt.
To do that, we rely on the exact same principle we used for the sphere. We look at the interactions. Figure 8-5 shows that sodium chloride forms a perfect three-dimensional cubic lattice.
Like a massive atomic checkerboard.
Exactly. Alternating positive sodium ions and negative chlorine ions. And they are spaced exactly 2.81 angstroms apart.
Just to ground that for you listening, an angstrom is 1/10,000,000th of a meter. We are talking about distances so small that a single wavelength of visible light is like thousands of times larger.
At that scale, we calculate the energy of one single positive sodium ion interacting with all of its neighbors. Its closest neighbors are negative chlorine ions. They pull it in. That's negative energy holding the crystal together.
Right.
But the next closest neighbors, slightly further out, are other positive sodium ions. They push it away. Positive energy, trying to blow the crystal apart.
I was looking at how the math plays out for this, and it's fascinating. If you just take a single, straight horizontal line of ions through the crystal, you get an alternating infinite series of fractions.
Because of the distance.
Right. It's pulling, pushing, pulling, pushing. A positive force at distance 1, a negative force at distance 2, positive at 3. It basically becomes 1 minus a half plus a third minus a fourth. The forces get weaker with distance, but they stretch out literally forever.
And mathematicians have known for centuries how to solve that specific alternating series. It perfectly maps onto the Taylor series expansion for the natural logarithm. That infinite push and pull converges exactly to the natural log of 2.
The natural log of 2. Out of an infinite line of atoms. I love when math does that.
It's beautiful, isn't it? When you patiently extend that sum beyond a single line, calculating the forces in all three dimensions, the lines above, below, the diagonal stretching out to infinity, the grand total of the pure electrostatic energy holding the crystal together is 8.94 electron volts per molecule.
Okay, let's pause and define that. An electron volt is a microscopic unit of energy physicists use because, well, joules are just too massive for the atomic scale.
Way too massive.
It's the energy one single electron gains when moving across 1 volt. So the theoretical math says it takes 8.94 electron volts to pull apart one molecule in the salt crystal. But here is the reality check.
Right, the experimental data.
Actual physical chemists melting and boiling salt in a lab measure that it only takes 7.92 electron volts per molecule to break it apart. That is a massive 10% discrepancy. The textbook equations are overshooting reality.
What's fascinating here is that the discrepancy isn't a failure of the equations, but a failure of our physical assumptions. Our math assumed the ions were perfectly rigid, unyielding spheres, like tiny billiard balls packed together.
Which they aren't.
No, atoms aren't billiard balls. They are fuzzy clouds of electrons surrounding a nucleus. When the positive and negative ions pull each other incredibly close in that lattice, their outer electron shells start to physically overlap and violently repel each other. They get slightly squashed.
It's like trying to pack too many tennis balls into a tight cardboard box. You can force them in, but they deform. They're actively pushing back against the confines of the box, just waiting to spring out.
Deforming them takes energy. When you start to pull the crystal apart, that stored, compressed squish energy is released. It actually helps push the ions apart, doing some of the vaporization work for you.
Oh, so it requires less outside energy than our rigid sphere math predicted. That makes sense. But how do you mathematically account for the squishiness of an atom?
You measure it macroscopically. Physicists literally put a solid block of salt under immense mechanical pressure in a lab and measured its bulk compressibility, how much it physically squishes.
Okay.
By translating that macroscopic mechanical resistance back to the atomic scale, they found this repulsive force accounts for exactly 1 divided by 9.4 of the pure electrostatic energy.
Oh, wow. So if you subtract that 1 over 9.4 squish factor from our theoretical 8.94 calculation,
And make a tiny correction for the kinetic energy of the atoms constantly vibrating at room temperature, the math lands on 7.92 electron volts. It matches the experimental reality perfectly.
that is incredible. We just proved a bulk macroscopic property of matter, literally how much heat it takes to boil table salt, using nothing but atomic electrical forces, infinite series math, and a squish factor.
It's remarkably elegant.
Okay, so electrostatics perfectly explains a crystal lattice. But what happens if we zoom way, way in, past the crystal, past the electron clouds, right into the center of the atom itself? Does this classical math still hold up inside the atomic nucleus?
To answer that, we have to understand the chaotic environment inside the nucleus. It's bound together by the strong nuclear force, which holds protons and neutrons in a tight cluster. For decades, physicists smashed protons together, hoping the strong force would follow a simple equation like the inverse square law for gravity or electricity.
And did it.
They found a nightmare instead.
Figure 8-6 in the text illustrates this chaos pretty well. The strong force depends on the distance between the particles, sure, but it also changes based on their velocity. It changes based on the direction of their orbital rotation.
It even depends on the orientation of their spin. The force is vastly different if two protons are spinning parallel to each other versus anti-parallel.
It is arguably as complicated as a force can possibly be.
We still don't have a simple underlying machinery to explain it. But amidst that chaotic list of parameters, there is a shocking, beautiful simplicity. The strong nuclear force between a proton and a proton, a neutron and a neutron, and a proton and a neutron is entirely identical.
Wait, but a proton has a positive electrical charge and a neutron has zero charge. They are completely different particles electrically.
They are. But the strong nuclear force is entirely colorblind to electric charge. We have undeniable proof of this from looking at the energy levels of mirror nuclei. Consider two specific isotopes, boron-11, which has 5 protons and 6 neutrons, and carbon-11, which is the exact flip, 6 protons and 5 neutrons.
I am looking at figure 8-7, which charts their excited energy states.
Yeah.
When you hit these nuclei with high-energy particles in an accelerator, they absorb the energy and jump up into specific higher energy configurations.
Right.
And the charts for boron-11 and carbon-11 are near-perfect mirror images. The first jump in energy from the baseline is about 2.14 mega electron volts, millions of electron volts for both of them. Then there's a huge 2.3 MeV gap to the second level for both. Then a tiny zero 0.5 MeV jump to the third. The pattern is identical for the first 15 energy levels.
It's uncanny. Swapping a neutron out for a proton doesn't change the intricate structural dynamics of the nucleus one bit.
Let me try an analogy here to make sure I'm getting this. It's like watching an insanely complex high-speed ballet routine. You have 11 dancers constantly interacting, spinning, lifting each other, moving at blinding speeds.
Okay, I like this.
The next night, you swap out one dancer or neutron for an understudy, a proton. If the routine looks exactly the same, with the same leaps, the exact same timing, and the same formations 15 moves deep, you know for an absolute fact that those two dancers have exactly the same physical capability.
That is a perfect visualization. The physical capability, the strong force interactions are identical. But if you look closely at the energy chart, there's one small difference. The ground state, the baseline mass energy of carbon-11, is absolutely higher than boron-11. It's higher by exactly 1.982 MeV. All of carbon's subsequent jumps are shifted up by this exact same amount.
Going back to the ballet, it's like the understudy is doing the exact same routine, but they're wearing a heavy backpack. Carbon-11 has 6 positively charged protons, while boron-11 only has 5.
Exactly.
Those 6 protons are electrically repelling each other much harder. That extra electrical repulsion creates extra stored electrostatic energy. The backpack is the electrostatic repulsion.
The strong force dance is identical, but the electrical force adds tension. Now, we must also account for the mass difference. Replacing a neutron with a proton and an electron means a change in rest mass, and Einstein's E equals mc squared tells us mass is energy.
Right, you can't ignore the mass.
When we add that rest mass energy difference, which is 0.784 MeV, to the 1.982 MeV gap, we get a total energy difference of 2.766 MeV.
And here's the genius part. We assume that this entire 2.766 MeV difference is purely electrostatic. It's just the energy required to stuff one extra positive charge into that tiny spherical nucleus, which means we can take that sphere-building gobstopper equation we talked about in the very beginning and run it in reverse. We know the energy it took to build it, so we can solve the equation backward to find the physical radius of the nucleus.
When you run the math backward, it outputs a nuclear radius of 3.12 times 10 to the negative 13 centimeters.
Which is amazingly close to reality. The text notes that actual real-world measurements, where physicists bounce fast particles off nuclei to measure their literal physical size, give a radius of 2.7 times 10 to the negative 13 centimeters. That's only a 15% discrepancy.
And that minor discrepancy vanishes when we refine our model. Our math assumed the protons and neutrons were uniformly blended in a perfect sphere. But current models suggest nuclei often form a tightly packed inner core with an even number of particles.
Oh, interesting.
In this case, 5 protons and 5 neutrons making a tight sphere. The odd particle out, the 11th particle, revolves on the outside of that core rather than being perfectly absorbed.
Ah, so the shape is slightly different.
Right. If we adjust our math to model a core plus 1 revolving particle, the predicted radius drops to 5/6 of our original number. It lands exactly on the measured 2.7 times 10 to the negative 13 centimeters.
So the exact same electrostatic rules we used for the virtual plates in the salt crystal work flawlessly down at 10 to the negative 13 centimeters. The scale is almost unimaginably small, but the mathematical rules hold up.
They do indeed.
Okay, so we've seen what electrostatic energy can do. But we've been avoiding a massive, frankly, philosophical question this entire time. Where is this energy physically located?
This raises an important question indeed. In classical Newtonian mechanics, energy is just a bookkeeping tool. It's a number we track in an equation to make sure everything balances.
Yeah.
We didn't need to say the energy of 2 interacting charges is located specifically at charge A or charge B or hovering in the middle. But in modern physics, energy must have a specific physical location in space.
All right, I want to slow down here because this is a huge shift. This is because of relativity, right? Einstein's E equals mc squared. Energy and mass are fundamentally the exact same thing.
They are completely equivalent. All mass creates a gravitational field, which means all energy must also be a source of gravitational force. If we cannot pinpoint where the energy is located, we cannot pinpoint where the mass is located.
Our entire theory of gravity would break.
Our entire theory of gravity would become incomplete. We need a principle of local conservation of energy. Energy can only change in a specific volume of space if it physically flows in or out of that space.
So we can't just wave our hands and say the energy is between the charges. According to electrostatics and Maxwell's equations, that energy lives in the empty space itself. It lives wherever the electric field is.
Correct.
Figure 8 to 8 visualizes this. Every tiny volume of empty space, everywhere in the universe, holds an energy density equal to the square of the electric field passing through it. If there is a field in a vacuum, there is physical, measurable energy sitting right there in the void.
We completely shift our perspective. We aren't looking at the charges anymore to find the energy. We are integrating the energy density over the empty space surrounding them. It's a highly elegant solution that satisfies relativity perfectly.
Here's where it gets really interesting. If the physical energy lives out in the surrounding field, what is the total energy of a single point charge, like an individual electron? By definition, an elementary point charge has absolutely zero physical volume. Its radius is exactly zero.
And here's where the elegant math finally explodes. Let's apply our new rule. We calculate the total energy by integrating the energy density of the electric field from infinity all the way down to the surface of the charge.
Okay.
The field gets infinitely stronger the closer you get, scaling as 1 over the distance squared. For a normal physical sphere of charge, you integrate down to its physical radius, a, and you get a finite, sensible amount of energy. But for a true point charge, you are integrating down to a radius of 0.
Integrating a fraction down to a denominator of 0 means you are essentially dividing by 0.
The integral races off to infinity. Equation 8.36 proves it unequivocally. A true mathematical point charge would create a field so strong near its center that it would hold an infinite amount of electrostatic energy in the surrounding space.
So what does this all mean? If it has infinite energy, and E equals mc squared says energy is mass.
It would have infinite mass, which is physically impossible. By moving the energy to the field to satisfy relativity, we are essentially saying it would require an infinite amount of mechanical work to assemble a single electron from infinitesimal parts.
We just spent this entire deep dive proving how flawlessly electrostatics works for capacitors and macroscopic salt crystals and the complex nucleus of an atom, and then we point those exact same laws at a single elementary electron, and it completely breaks physics.
It is a fundamental glaring flaw in the classical theory of electricity. The very idea of locating energy in the electromagnetic field is entirely inconsistent with the assumption that point charges exist.
That's wild.
Our theory of electricity works beautifully at almost every scale of the universe. But at the very smallest scale, the scale of the elementary particles themselves, it fails completely. And this isn't some historical footnote that got neatly swept away by quantum mechanics decades ago. These deep structural difficulties with infinite self-energy have never been completely overcome. They exist in theoretical physics to this day.
That is absolutely wild. We've covered a staggering amount of ground today. We started by building hypothetical spheres of charge layer by layer. We used that exact same math and the trick of virtual work to calculate the macroscopic squishiness of a salt crystal.
We did.
Then we jumped inside the nucleus of an atom to prove that protons and neutrons do the exact same complex dance, right down to measuring their radius. And finally, we tried to trace the physical location of that energy into the empty field itself, only to hit a brick wall, breaking physics with the infinite energy of a point charge.
It shows you how a single, powerful idea, like electrostatic energy, can unify the entire universe right up until you push it to its absolute limits. And I want to leave you with a final thought to mull over.
Lay it on us.
If the mathematics of a zero-radius point charge inevitably lead to infinite energy and impossible mass, then perhaps fundamental particles like electrons aren't actually infinitesimally small points at all. Maybe they have a real physical size, like an unimaginably tiny solid sphere of charge.
Okay,
But if an electron is a microscopic sphere made entirely of pure negative charge, what holds it together? Every tiny piece of that sphere would be violently repelling every other piece. Wouldn't its own internal electrostatic repulsion blow it apart instantly? How can something so fundamental exist if our own math says it should destroy itself?
Imagine holding your hands apart and trying to assemble an object out of pure invisible force. It turns out, nature has figured out how to do it at the fundamental level, even if we are still just trying to read the instruction manual. Until next time, keep digging. Right now, assuming you are, standing outside on a clear day, there is a 200-volt electrical difference between your nose and your toes. Welcome to the deep dive.
Yeah, it's a really jarring thought, honestly, because we just tend to treat the atmosphere like it's this empty, passive void, like just the backdrop to our day.
Right, just air.
Exactly. But you, me, everyone, we are actually living inside an invisible giant electrical machine.
Which is wild. So today we're exploring a legendary chapter of Richard Feynman's physics lectures. Specifically, we're diving into Chapter 209 to completely decode the mechanics of this planetary battery.
Yeah, and we're not just skimming it. This is a full-length exploration.
Absolutely. As requested, we are getting past the complex terminology, the figures, and we're clearing up some massive misunderstandings about a global system that you literally walk through every single day.
Because it's happening all around you right now.
Okay, let's unpack this. Because 200 volts is no joke. I mean, if there is a 200-volt drop across my actual physical body when I go outside to check the mail, why am I not getting electrocuted?
Well, it all starts with the electric potential gradient. So the Earth's surface is naturally negatively charged.
Okay.
And the sky above us is positively charged. So on a clear day, the electric potential increases by about 100 volts for every single meter you go up into the air.
Wow. So at 2 meters high, which is, roughly the height of a tall person, that's your 200 volts.
Exactly.
But if I'm standing in a 200-volt field, why don't I feel a shock? Is it sort of like a topographical map? Like where I'm a boulder sitting on a hill and the elevation lines just kind of wrap around me instead of going right through me?
That is exactly what it is. Because your body is actually a relatively good conductor of electricity.
When compared to the air.
Right. Air is a pretty good insulator. So when you stand on the ground, you and the Earth essentially become one continuous, what physicists call an equipotential surface.
Equipotential surface.
Got it. Yeah. So because you are conducting the ground's electrical potential upward, those invisible field lines, like the elevation lines in your map analogy, they don't cut through your body.
They just bend.
Exactly. They distort and bend around you. So the actual voltage difference across your physical tissues stays at nearly zero.
Which is incredibly lucky for us, honestly.
Mm-hmm.
But that raises a pretty obvious problem for the physicists who first tried to study this.
Oh, the measurement problem.
Right.
Yep.
If putting a person or, even a piece of scientific equipment into the air actually distorts the invisible field lines, how did scientists ever measure the gradient in the first place?
They had to get incredibly creative. I mean, one method, this is from figure 9-2 in the text, involved placing a grounded metal plate flat on the Earth.
So it just gathers a surface charge from the ground.
Yep. And then they would suddenly cover it with another grounded conductor.
Wait, why cover it?
Because that caused the charge on the original plate to drop to zero, and then they could measure the tiny, tiny bit of charge that flowed away through the grounding wire.
Oh, that's smart. But I mean, I'm much more fascinated by the leaky bucket trick that they mentioned in the lectures.
It is a remarkably elegant solution, isn't it?
Yeah. Explain how that one works.
So you take a fully insulated bucket of water, you raise it up into the air, and you just, you simply let it leak.
Just let the water drip out.
Right. And as the individual water drops fall out, they physically carry away any excess electrical charge from the bucket.
That's brilliant.
It really is. Eventually, the bucket perfectly matches the electrical potential of the air at that exact height.
Because it's shed all the difference.
Exactly. So by measuring the bucket, you've measured the invisible field without drastically distorting it with a huge metal probe.
Wow. And using techniques like this, I mean, they mapped the entire atmosphere.
They did. And from the surface of the Earth all the way up to the conductive ionosphere, the total voltage difference is it's a staggering 400,000 volts.
400,000. That's a massive potential difference. But the atmosphere isn't a perfect insulator. Right?
No, it acts more like a leaky capacitor.
Yeah.
The air is actually peppered with tiny ions.
Like molecules that have lost or gained an electron.
Exactly. And because of those ions flowing around, the air actually conducts electricity just a little bit.
Okay, so if you have a 400,000 volt difference pushing on those conductive ions, that means there has to be a constant electrical current flowing.
And there is. Across the whole planet, there is about 1,800 amperes of positive current constantly flowing from the sky down to the negatively charged Earth.
Just constantly draining.
Constantly. To put that in perspective, that is a constant 700 megawatt electrical leak.
But wait, if a 700 megawatt leak is draining the sky right now, why hasn't the battery died yet?
See, what's fascinating here is that at this rate of leakage, the Earth's entire negative surface charge should completely drain away in just 30 minutes.
30 minutes.
Yeah, 30 minutes, and the whole system should just short out and be done. Yet we know this atmospheric electrical field has been stable for billions of years.
Okay, well, before we figure out what is recharging the battery to stop that 30-minute doomsday, where do these conductive ions even come from in the first place?
That was a huge mystery.
Right, because if the air is naturally an insulator, something has to be constantly breaking apart those air molecules to make the ions.
Exactly. And in the early 20th century, the prevailing assumption was that the ions were created by trace amounts of radioactive dirt on the ground.
Just rocks and soil.
Right. The idea was that the soil emitted alpha and beta particles, and those particles stripped electrons off the air molecules near the surface.
Wait, but if the radiation comes from the dirt on the ground, shouldn't the air get less conductive the higher you go up?
You would think so?
Yeah, you're moving further away from the source of the radiation.
That was the logical conclusion. So to test it, this Austrian physicist named Victor Hess performed just a wildly daring experiment in 1912.
What did you do?
He took an electrometer, which is a really delicate instrument for measuring electric charge, and he went up in a hot air balloon.
Oh, wow. In 1912.
Yeah, ascending miles into the freezing atmosphere. And he was fully expecting to see the ionization drop off as he got higher.
Let me guess. He found the exact opposite.
The ionization actually spiked the higher he went.
Yeah.
It completely proved the radiation wasn't coming from the dirt at all.
It was coming from above.
Yes. Hess had unwittingly discovered cosmic rays.
Oh, high-energy particles bombarding us from deep space.
Constantly. I mean, radiation from distant supernovae and ancient galaxies is literally crashing into our upper atmosphere every single second.
Shattering the air molecule.
Exactly. And creating that steady supply of ions that cause this massive 700 megawatt leak.
Which is mind-blowing on its own. Just radiation from dead stars making our air conductive.
It's beautiful, really.
It is. But we still have that 30-minute doomsday problem. So space radiation causes the leak, but what is pumping the charge back up to the sky to maintain that 400,000 volt difference?
To find the engine for that, scientists actually had to look at global data. They measured the atmospheric current over the open oceans.
Why the oceans?
Because the air there is cleaner, so the readings are much more stable. And what they discovered, this is in figure 9-5, is that the current universally goes up and down by about 15% every single day.
Okay.
And it always peaks at exactly 7 p.m. London time.
Wait, why would London time matter for a global atmospheric current?
Because it's an absolute globally synchronized measurement of time. At 19:0 UTC, the sun is hitting the massive land masses of South America and Africa.
Oh, so it's the hottest part of the day there.
Exactly. It creates the absolute peak of afternoon heating across the globe.
And peak afternoon heat triggers massive global thunderstorms.
Bingo. There are roughly 40,000 thunderstorms happening around the globe every single day.
40,000.
Yeah. And together, they act as a synchronized network of mechanical pumps pushing negative charge down to the ground and positive charge up to the sky.
Exactly, countering the leak.
Perfectly countering it.
Okay, here's where it gets really interesting. Because the lectures don't just, say, thunderstorms do it and move on.
Right.
They actually open up the hood on this engine.
They do, yeah. Feynman really gets into the mechanics.
Right. Like, how does a storm pump electricity? So let's talk about the thermodynamics first, the stuff in figure 98.
Sure. So it relies on a process called adiabatic cooling. When a mass of air rises into the atmosphere, the surrounding air pressure drops.
Because the air is thinner up there.
Right, and that causes our rising bubble of air to expand. Now, as any gas expands, it mechanically cools down.
Okay, makes sense.
So if a bubble of dry air gets pushed upward, it cools off very quickly, it becomes heavier than the air around it, and it simply sinks back down.
But wet air plays by completely different rules, right?
Very different. If that rising bubble is saturated with water vapor as it expands and cools, the water vapor actually condenses into liquid drops.
Rain.
Yeah. But the physical act of that condensation releases a massive amount of latent heat.
Wait, so the condensing water vapor is actually acting like an internal furnace, just warming the air bubble from the inside out.
Yes. This latent heat keeps the wet air warmer than the surrounding environment, and because it stays warm, it stays buoyant.
It just keeps rising.
It can shoot upward at 60 miles per hour, creating those mad-long, towering thunderheads that reach 15,000 meters into the sky.
But if the hot, wet air is rocketing upward at 60 miles per hour, how does the rain ever come down? I mean, you can't just have an endless updraft without something crashing back to Earth. Doesn't that sound like perpetual motion?
Well, for a long time, early models of thunderstorms really struggled to explain that exact problem.
I bet.
The key mechanism here is a concept called entrainment. See, that massive column of rising hot air isn't perfectly isolated in a tube. As it rockets upward, it actually acts like a vacuum.
Oh, sucking in cold, dry, ambient air from the edges of the cloud.
Exactly. It aggressively pulls the outside air in.
Wow.
And this freezing outside air violently mixes with the warm updraft, rapidly chilling vast pockets of it.
So it kills the buoyancy.
Right. These massive sections of the cloud suddenly become drastically colder and denser than their surroundings, and they just collapse back down to Earth as icy downdrafts.
Which is why, right before a thunderstorm hits, you almost always feel that sudden freezing gust of wind.
That's the downdraft hitting the ground, yeah.
So we have this chaotic engine of 60-mile-per-hour updrafts and freezing downdrafts. But how does wind and rain turn into a 100 million volt battery?
That's the real trick.
Yeah, because we know from brave pilots flying through these storms that the top of the cloud becomes highly positively charged and the bottom becomes intensely negatively charged. How do the charges physically separate?
Well, one of the most elegant explanations is C.T.R. Wilson's polarization theory.
Okay, let's break that down.
Remember that 100 volt per meter background electric field we talked about earlier? The one where the sky is positive and the ground is negative.
Right, gradient.
So as a large water drop begins to fall through that existing electric field, the field actually polarizes the droplet.
What does that mean for the drop?
It means the negative charge inside the water gets pushed up to the top of the drop, and the positive charge gets pulled down to the bottom.
Oh, so the bottom of every falling raindrop becomes a tiny positive magnet.
Now imagine this polarized drop falling heavily through the air. It creates a tiny updraft of air rushing past its sides as it falls.
Sure, just wind resistance.
Right. Now, if there are positive ions floating directly beneath the drop, the positively charged bottom of the drop repels them, and the updraft simply blows them away.
Makes sense. But what if it encounters negative ions?
Well, the positively charged bottom of the drop attracts them violently. It sweeps them up.
Wait, so it's almost like the raindrop is a microscopic snowplow, but it only scoops up negative charges, and it drags them all to the bottom of the cloud.
Exactly. And those positive ions that were repelled, they're left behind, caught in the storm's massive atmospheric updrafts and blown all the way to the top of the thunderhead.
So you get this massive, purely mechanical separation of charge.
It's a brilliant mechanism. And this physical separation creates an immense electrical tension. But eventually, that tension has to snap.
The lightning bolt.
Right. When the negative charge at the bottom of the cloud builds up to a potential difference of between 20 and 100 million volts relative to the ground.
100 million volts. Wow.
Yeah, the air simply cannot insulate it anymore. The air violently breaks down, creating a giant arc discharge.
But wait, a lightning bolt drains an enormous amount of energy.
Mm.
The lectures say a single strike drains about 20 to 30 coulombs of charge.
That's right.
And just to clarify the terminology for a second, a coulomb is essentially a massive bucket of electrons.
A huge bucket. Think of 1 coulomb as holding over 6 quintillion electrons.
Good grief.
Yeah, and a single lightning strike is dumping 20 to 30 of these massive buckets of charge in a fraction of a second.
Does that just empty the storm's battery entirely? Like, does it have to start over?
Not at all. The thunderstorm is a wildly efficient engine. It is constantly churning and pumping out about 4 amps of current. Because those updrafts and downdrafts are working so frantically, the storm can completely regenerate those lost 30 buckets of charge in just 5 seconds.
5 seconds to reload a 100 million volt gun.
The raw power is staggering,
Mm-hmm.
but the strike itself, the actual physical mechanics of the lightning bolt, is where the story gets really wild.
How so?
Well, we only understand the sequence because of an ingenious piece of 1930s equipment called the Boys camera.
Oh, this was the camera with lenses mounted on a rapidly rotating disc, right?
Exactly. So it physically spread the image of the lightning strike out over time on the film.
Right, letting scientists see the exact sequence of events millisecond by millisecond.
And what the film revealed completely upends how we intuitively think about lightning.
Okay, I love this part.
The process actually begins with something entirely invisible to the naked eye. It's called a step leader. A small pocket of negative charge leaves the bottom of the cloud and darts downward at roughly 1/6 the speed of light.
But it doesn't go all the way, right?
No, it only travels about 50 meters. Then it abruptly stops.
Why does it pause?
It hangs there for about 50 microseconds, seemingly charting the path of least electrical resistance through the turbulent air below it.
Oh, wow.
Then it takes another 50-meter step. Pauses. Steps. Pauses. It zigzags its way down toward the ground, violently ionizing the air molecules as it goes.
So it is effectively laying down an invisible, highly conductive plasma wire from the cloud to the Earth.
Exactly.
Okay, let me stop you right there, because this is the biggest misunderstanding we need to debunk today.
Let's do it.
When I watch a lightning bolt strike the ground, I am absolutely certain I am seeing a bright flash go from the sky down to the Earth. Are you saying my eyes are lying to me?
They are. It is a complete optical
Oh,
illusion.
seriously.
Yes. When that invisible step leader finally touches the ground, the physical connection is made. You now have a massive conductive wire full of negative charge connecting the cloud to the Earth.
Okay.
The electrons at the very bottom of the wire, closest to the ground, are the first to realize the door is open, and they dump rapidly into the Earth.
Like a vacuum.
Right. That creates a sudden vacuum, which pulls the electrons just above them down, which pulls the electrons above them down.
Oh, like a massive electrical traffic jam suddenly clearing from the front.
Exactly. The actual bright, blazing flash of light and heat that you see, what physicists call the return stroke, actually shoots UP from the ground to the cloud.
That is insane.
It's traveling back up the ionized path made by the step leader.
So the visible light of the lightning bolt is
Yeah.
blasting upward. That is incredible. But, lightning often flickers, like it strikes the same place multiple times in a fraction of a second.
Right. And that happens because that specific path through the air is now highly ionized and intensely conductive.
So the door is wide open.
Yeah, so the cloud doesn't need to send down a slow, pausing step leader anymore. It immediately sends down a dart leader.
A dart leader.
And this one doesn't pause to find a path. It goes full steam, straight down the exact same track in one smooth swoop. And the moment it hits the ground, another return stroke shoots up. You can easily have 5, 10, even 40 strikes on the exact same path in rapid succession.
That is terrifying and amazing. And the lectures also mention that the ground isn't just passively waiting for the leader to arrive, right?
Right. As the step leader gets within 100 meters or so of the ground, the localized electric field becomes intensely strong.
Because the negative charge is getting so close.
Exactly. So if there is a sharp object on the ground, a tall tree, a church steeple, or a high building, the electric field concentrates heavily around that point.
Okay.
And the object will actually send up a brush discharge. It shoots a spark up into the air to try and meet the step leader halfway.
So the tall objects are actually reaching out to grab the lightning.
They are. And if we connect this to the bigger picture, it brings us to a really fascinating historical perspective from the text. The lectures share a wonderful quote from Artabanus, who was an advisor to the Persian king Xerxes roughly 2,400 years ago.
Oh, the advisor who thought lightning was used to punish pride.
That's the one. He observed that lightning always seemed to strike the tallest trees and the highest houses. He wrote that the gods use lightning to bring down everything that exalts itself.
Yeah, I mean, you can't really blame him for the poetry of it. But it is pretty funny to realize that what he thought was divine retribution for human arrogance was actually just a localized concentration of an electric field sending up a brush discharge to meet a 50-meter step leader.
Literally just the ground reaching up to complete a circuit.
It's just pure physics.
Yeah,
But it's physics operating on a scale so grand it feels mythical.
it really does. It's an invisible thermodynamic engine that we walk through every single day without ever noticing.
It really is. And I think that brings us back perfectly to where we started, because the next time you step outside on a clear, sunny day, you aren't just walking into empty, passive air. You are walking directly through a 400,000-volt circuit.
And the only reason you aren't feeling it is because your body is bending the electrical field lines of a global machine.
A machine that is being synchronized by distant tropical storms and powered by cosmic rays bombarding the Earth from deep space.
It's beautiful.
Which leaves me with one final thought for you to mull over. Because we only discovered this massive 700-megawatt electrical circuit spanning the entire planet. Because a few incredibly curious people decided to play with leaky buckets of water and fly electrometers up in freezing hot air balloons. So it really makes you wonder, what other massive, invisible, planet-wide systems might be operating completely unnoticed right through the spaces we inhabit every single day?
You know, usually when we think about a barrier, we think of it as, well, doing absolutely nothing but blocking. Like, picture a thick, heavy concrete wall.
Right, just a totally passive obstacle.
Yeah, exactly. You throw a tennis ball at it, the ball hits the concrete, and it just bounces back. The wall itself is completely inert.
It just sits there taking up space.
Right. I mean, it doesn't help you throw the ball faster, it doesn't absorb the ball and shoot it out the other side, and it definitely doesn't change the physical rules of the game you're playing.
But that's the standard intuition, right? We expect it to be a completely passive participant in whatever is happening around it.
But imagine if you threw that ball at the wall, and somehow, I mean, just by being present in the space, the wall reached out, caught the ball, and actually magnified your throwing power.
That would be wild.
Right. Suddenly that passive barrier you thought you were looking at isn't just a wall anymore. It's this hidden, highly active engine.
Which, is the perfect way to describe the absolute headache that insulators caused for the early pioneers of physics.
Oh, absolutely.
They looked at materials like glass or rubber, expected a dumb, passive wall, but instead they found a completely invisible engine that was just messing with all of their equations.
Well, welcome to the deep dive. Today, we are exploring the secret, highly active life of insulators. Specifically, we're looking at a class of materials that physicists call dielectrics.
And we are pulling our insights from a truly fascinating source today, Volume 2, Chapter 10 of the legendary Feynman Lectures on Physics.
A total classic. And our mission for you on this deep dive is to uncover why materials that supposedly do not conduct a single drop of electricity actually have a profound active effect on the electric fields around them.
It really is a fundamental mystery of electromagnetism. I mean, everyone learns very early on in science class that conductors, like copper wire or gold, let electrical charge flow freely.
Which is why we use them for power lines.
Exactly. And insulators, like glass, plastic, or rubber, completely block that flow. So you would logically assume that if you took a solid block of glass and placed it inside an invisible electric field, it would do absolutely nothing.
Yes, you'd think putting a block of glass into an electric field is exactly like putting a heavy brick in a wind tunnel. The wind just goes around it. The brick doesn't care.
But that is not what happens at all.
No, it is not. Michael Faraday, way back in his early experiments in the 1800s, made a totally surprising discovery about this. He was working with a parallel plate capacitor.
And for those listening, a capacitor is basically just two flat pieces of metal with a small gap of empty air between them.
Right, and it's used to store electrical charge. And Faraday found something completely counterintuitive.
He really did. He found that if he took an insulating material, a dielectric, like a sheet of glass, and physically wedged it into that empty gap between the two metal plates, the capacitor's ability to store charge actually went up.
It increased. Okay, let's unpack this. How can a material that doesn't conduct electricity change the electrical properties of an entire system?
And it wasn't just changing it by some random amount either. It was a very specific, reliable multiplier. Faraday actually called this multiplier the dielectric constant.
Which physicists usually represent with the Greek letter kappa, right?
Right. To solve this mystery, we have to play detective and deduce what is actually happening to the invisible electric field inside that gap.
Okay.
Think about the fundamental relationship between charge, capacitance, and voltage. Faraday saw that if you pump a very specific amount of charge onto those metal plates and hold it there, but then you insert the glass insulator, the capacitance goes up.
Right, and because of the mathematical rules tying those three things together, if capacitance goes up while the charge stays exactly the same, it means the voltage between the plates must drop.
Precisely. And because voltage is basically just a measure of the electric field strength over that specific distance, a drop in voltage means a drop in the field.
Right.
So if the voltage drops while the distance between the metal plates remains exactly the same, it leaves us with one inescapable conclusion. The internal electric field is being actively reduced by the presence of the glass. The material is literally fighting back against the field.
But to understand how a piece of glass can fight back against an electric field, we have to zoom way. We have to transition from the macro world down to the microscopic atomic structure of the insulator to see how it's actually responding.
We do. And historically, physicists struggled deeply to picture this. In the text, Feynman details an early historical model that scientists came up with to explain this phenomenon.
Oh, I love this part.
It was incredibly clever, but ultimately completely wrong. Early scientists imagined dielectrics as being made of billions of tiny, microscopic conducting spheres.
Right, completely isolated from each other by a sea of perfect insulation. It's like they just couldn't let go of conductors.
Yeah.
They thought, well, the only thing we know of that affects an electric field is a metal conductor, so this piece of glass must just be secretly full of tiny metal balls.
That was the exact logic. They knew a solid block of metal would completely cancel out an electric field inside itself because its free electrons would just rush to one side.
So they just scaled that down.
Exactly. They assumed these tiny microscopic spheres were doing the same thing on a miniature scale. But the actual atomic model, like the quantum reality we understand today, is far more elegant than tiny metal balls.
So let's look at that true mechanism. In a real atom, you have a heavy, positively charged nucleus sitting right in the center, and it's surrounded by a fluffy cloud of lightweight, negatively charged electrons.
Right. And normally in a resting atom, their centers of gravity sit right on top of each other. They are perfectly balanced.
But when you turn on an external electric field, that delicate balance is violently disrupted.
The positive nucleus gets pulled physically in the direction of the electric field, and the negative electron cloud gets yanked in the exact opposite direction.
I always picture this atomic distortion like a really eager dog on a short leash.
Oh, that's a great analogy.
Right. So the nucleus is a heavy wooden post pounded firmly into the ground, and the electron cloud is the dog. When the electric field turns on, let's say a squirrel runs by, the dog lunges.
But it can't break free.
Exactly. It can't break free and run away like it could in a conducting metal, but it leans incredibly hard into the collar, shifting its entire center of gravity away from the post.
What's fascinating here is that this microscopic shift, this tiny leaning of a single atom, seems entirely insignificant on its own.
Right.
But a block of glass or plastic contains billions upon billions of these atoms. When they all lean in the exact same direction at the exact same time, they create a massive macroscopic effect.
Wow. We call this tiny leaning force a dipole moment, right?
Yes, and when you calculate the sum of all those leaning atoms per unit of volume, you get a powerful mathematical metric called the polarization vector.
Yeah.
Use a capital P for it.
And for our discussion today, this polarization is directly proportional to the strength of the external electric field pulling on that leash.
Exactly.
Okay, so we've got billions of atomic dogs all leaning on their leashes in the exact same direction. But how does this microscopic shift translate into a physical force that can actually alter a giant metal capacitor?
Well, because if you were to pull out a microscope and look closely at the atoms deep in the middle of this material, it seems like nothing has really changed.
Right, Feynman paints this incredible picture of what happens in a perfectly uniform slab of dielectric material.
Imagine every single atom shifts its positive center slightly to the right and its negative center slightly to the left. Deep inside the bulk of the slab, the shifted positive charge of one atom sits right next to the shifted negative charge of its immediate neighbor.
So they just overlap and cancel each other out completely?
Yes. Inside the deep interior of the material, the net charge remains exactly zero. It's only when you reach the extreme outer boundaries, the physical surfaces of the slab, that the magic actually happens.
Because on one side of the glass, you have a microscopic layer of electron clouds that shifted outward into empty space.
And there are no neighboring positive charges to cancel them out. They are left completely exposed.
And on the far other side of the glass, you have a layer of exposed positive nuclei.
We call this the surface polarization charge.
Wait, let me stop you right there because I want to clarify something that might be confusing for you listening. If I have a block of plastic, and suddenly there's a sheet of negative charge covering the left surface, and a sheet of positive charge covering the right surface, did electrons actually travel through the plastic from right to left to get there?
No, absolutely not. That is a crucial distinction to make. The electrons did not flow across the material like they do in a wire.
Okay, so it's just the shifting.
It is purely the exposed ends of those leaning atoms at the absolute boundaries. If you turn off the external electric field, say, by discharging the capacitor, that surface polarization charge doesn't flow out through your wires.
It simply vanishes.
Right. It vanishes as the atoms relax back to their normal, perfectly centered state. The dogs just stop pulling on the leash.
That is wild. It's effectively a phantom charge. It only exists as long as the external electric field is holding the atomic structure in tension.
It is a phantom, but while it's there, it acts exactly like real permanent charge. And this beautifully explains Faraday's capacitor mystery.
Because the surface polarization charge on the glass creates its own internal electric field.
Yes, and that field points in the exact opposite direction of the main field coming from the metal capacitor plates. These opposing fields literally subtract from each other.
Which reduces the overall internal electric field, which drops the voltage, which, as we established earlier, means the capacitance increases. It's all brilliantly connected.
It really is. Now, that's what happens if the material and the field are perfectly uniform. But Feynman brings up a scenario where things get a lot messier.
Right. What if the polarization isn't uniform? What if the field is lopsided and the atoms on the left side are leaning way harder than the atoms on the right?
If the polarization is non-uniform, then those atomic shifts don't perfectly cancel out in the middle of the material anymore. You might have more negative charge shifting into a specific microscopic region than shifting out of it.
Oh, wow. So you don't just get a phantom charge on the surface.
Right, you get a real volume charge density building up deep inside the solid material itself.
And because these polarization charges, whether they're sitting on the surface or buried deep in the volume, are essentially hidden inside the material's atomic structure, they caused an absolutely massive headache for early physicists.
Oh, incredibly frustrating for them. They were trying to write the fundamental mathematical rules of electricity,
Yeah,
but they couldn't physically see or control these tiny atomic shifts.
right. They were working with Maxwell's equations, which are basically the holy grail of electromagnetism. But dealing with these phantom polarization charges made the math incredibly, overwhelmingly messy.
And remember, at the time, they didn't even know atoms had a nucleus and an electron cloud yet.
So what did they do to fix their math? They invented a mathematical shortcut. Just to remind you, in physics, a vector is basically just a mathematical arrow. It tells you what direction a force is pointing and how strong it is.
Right. And to make Maxwell's equations look clean and simple again, early physicists invented a brand new vector, and they called it D.
And they defined this D vector as essentially the real electric field plus the material's polarization.
The entire purpose of this new D vector was to sweep all those hidden, messy polarization charges right under the rug.
I really like to think of this D vector like a corporate accounting trick.
Oh, how so?
Well, imagine a business with thousands of tiny microscopic daily expenses. Buying paper clips, paying for coffee, fixing a squeaky chair. It's a nightmare for the CEO to track.
Sure.
So the accountants invent a single category called overhead. They sweep all the tiny expenses into that one bucket, so the CEO only has to look at the big controllable expenditures. It makes the spreadsheet look clean.
Right, and by using D, engineers could write equations that only dealt with the free charges. The real charges they could actually control, like the electrons they pumped from a battery onto the metal plates.
They could just mathematically pretend the microscopic polarization charges didn't exist. But wait, isn't that just bad science? How can you just invent a letter to ignore reality and still have equations that build working radios and motors?
Well, engineering is often about finding what is useful, rather than what is perfectly true. It works exceptionally well for building circuits because in those everyday materials, the polarization really is perfectly proportional to the field.
Okay, but
But this raises an important question. If this D vector is essentially an accounting trick that sweeps reality under the rug, are these simplified equations actually a fundamental law of the universe?
Feynman argues very strongly that no, they are not.
He does. The equation relating D to the electric field is an approximation. It's a highly useful engineering tool, much like Hooke's law is for springs.
Right, Hooke's law says a spring stretches proportionally to the force you apply. Pull twice as hard, it stretches twice as far.
But if you grab a slinky and pull it too hard, it warps. The metal permanently bends, and it never bounces back. The law breaks down.
And the exact same thing happens with dielectrics.
Precisely. If the electric field gets too massive, the atoms don't just lean proportionally anymore.
The dog breaks the leash.
Exactly. Electrons get ripped right off the nucleus, and the material breaks down and shoots a physical spark.
Or, if the electric field is oscillating back and forth incredibly fast, like in a high-frequency radio wave, the heavy atomic nuclei might not be able to physically lean back and forth fast enough to keep up.
The proportionality completely falls apart. The fundamental truth of the universe always lies with the true electric field E, and you have to account for all charges, both the free ones from your battery and the polarized ones hidden in the glass.
This leads to a specific glaring error that Feynman points out, one that is still found in a lot of older and, frankly, some current physics textbooks.
Yes. They try to teach that the fundamental law for the force between two charges is Coulomb's law. But to account for an insulator, they just lazily stick that dielectric constant, kappa, right in the denominator of the equation.
Feynman emphatically explains why this is thoroughly unsatisfactory.
Teaching that modified Coulomb's law as a fundamental truth is a terrible habit, because it is only true if the entire universe is filled with a perfect liquid dielectric.
Okay, I have to ask, why does he draw us such a sharp, specific distinction between liquids and solids here? Like, if I stick a solid block of plastic between two electrical charges, why does the math break down compared to sticking those same charges into a vat of oil?
It comes down to mechanical stress and strain. Think about what happens if you have two highly charged metal spheres, and you try to move them closer together while they are embedded inside a solid block of plastic.
As you push them, the solid material physically resists the movement.
Yeah.
You are crushing and stretching the rigid atomic lattice of the plastic itself.
And that creates intense mechanical stress. And here's the kicker warping. The physical structure actually alters the material's electrical properties in real time. The electrical forces and the mechanical crushing forces become a horribly intertwined nightmare to calculate.
But in a liquid,
In a liquid, if you move the charged spheres, the liquid molecules simply flow out of the way. There's no permanent mechanical strain left behind in the fluid.
So the physical environment around the charge remains perfectly isotropic.
Yes, which is a fancy physics term, meaning it looks perfectly uniform in every single direction no matter where you move. Because the liquid just flows, the electrical characteristics remain unchanged, which makes the textbook math nice and clean.
But since we do not live in a universe made entirely of liquid oil, pretending that equation is a fundamental law is just bad physics.
Exactly.
Okay, so knowing that solid dielectrics involve these incredibly complex physical strains, how can we actually calculate the physical forces these materials experience in everyday life? Because we interact with this exact phenomenon all the time.
We do. And we can start with something almost everyone has experienced.
Here's where it gets really interesting. Think about combing your hair on a dry, static-filled winter day. You run a plastic comb through your hair, and the friction picks up a static electrical charge.
Right.
Then you hold that charged comb over a pile of tiny, completely neutral bits of paper on your desk, and the paper jumps up and sticks to the comb. Now, earlier, we established that a neutral piece of dielectric material, like paper, shouldn't do anything. The positives and negatives perfectly cancel out. So why does a charged comb attract paper that has absolutely no net charge?
It's a fantastic real-world puzzle.
Okay.
To solve it, we have to look at the shape of the field. When you bring the charged comb near the paper, the comb's electric field polarizes the paper. The atoms in the paper lean.
So the negative ends of the paper's atoms are pulled slightly closer to the positive comb, and the positive ends are pushed slightly further away.
Exactly.
But wait, if they are just leaning, isn't the force pulling the negative ends upward exactly equal to the force pushing the positive ends downward? Shouldn't it just cancel out completely and the paper just sits there on the desk?
That's a great observation. It would perfectly cancel out if the electric field from the comb was perfectly uniform. But a comb is not an infinite flat sheet of metal. It's a small, jagged object with pointy teeth.
Ah, so its electric field is highly non-uniform.
Exactly. The field is incredibly strong, right next to the plastic teeth, but it drops off very rapidly the further away you get into the air.
So the negative ends of the atoms in the paper are physically sitting in a much stronger part of the electric field than the positive ends are?
Yes. The attractive force, pulling up on the closer negative charges, is physically stronger than the repulsive force pushing down on the slightly further positive charges.
Because of this steep drop-off in the field's strength, there is a net upward pull.
A dielectric material is always physically drawn from a region of weak electric field toward a region of stronger electric field.
Feynman points out something incredible here about the math, because the amount the atoms lean depends on the strength of the field, and the force pulling them up also depends on the strength of the field they multiply.
Right. The actual force pulling that paper up to the comb is proportional to the gradient of the square of the electric field.
And that gradient just means how steeply the field's strength drops off over distance.
Yes.
Right, so for those of us whose calculus is a little rusty, what does that actually look like in the physical space around the comb?
It basically means the attraction force is highly localized.
Yeah.
Because you were squaring the field and then looking at its gradient, how fast that squared number changes, the force drops to nearly zero when you are a few inches away.
But the absolute millisecond the paper gets close enough to feel the steep part of the field, the pulling force spikes exponentially and the paper leaps off the table.
Exactly. And this non-uniform field effect creates one last puzzle. Let's go back to that parallel plate capacitor from the beginning. Two flat metal plates with a gap.
Okay.
But this time, instead of wedging the glass slab all the way in, you just slide it barely into the edge of the gap and let go.
So if the field is uniform perfectly in the center of the plates, why does the slab suddenly get violently pulled in at all? What on earth is grabbing it?
It's those sneaky non-uniform fields again. Right in the dead center of the metal plates, the field is uniform. But at the very edges of the metal plates, the electric field bows out and curves into the surrounding air. We call these fringing fields.
And just like the jagged comb, those curved edge fields are highly non-uniform.
Right, they grab hold of the polarized glass slab and pull it straight toward the strongest part of the field, which is right into the center of the gap.
But calculating the exact geometry of those curved bowing edge fields seems like it would be a mathematical nightmare. I mean, how do you even write an equation for a bowed line of invisible force pulling on a billion atoms?
You usually don't. It's
Yeah.
incredibly difficult to solve directly. But if we connect this to the bigger picture, Physics often uses a brilliant shortcut to bypass these massive calculations. We use the principle of conservation of energy.
We don't need to look at the messy edge fields at all to figure out how hard the glass is being pulled. We just look at the whole system's energy ledger. Because we know nature always wants to roll downhill. Nature seeks the lowest possible energy state, like a ball rolling to the bottom of a valley.
Exactly. We know from Faraday that sliding the glass slab inward increases the capacitance, and we know that increasing the capacitance lowers the voltage, which means it lowers the total electrical energy stored in the system.
The system is rolling downhill.
So by simply taking the mathematical derivative, which just means calculating the exact slope of how fast that energy drops as the slab moves a tiny distance, we instantly know the exact mechanical force sucking it into the gap.
We bypass the nightmare of calculating curved edge fields entirely just by looking at how the total energy changes.
Precisely.
So what does this all mean? We started this journey by throwing a tennis ball at what we thought was a passive concrete wall, and we ended up uncovering an invisible, highly reactive engine.
We've seen that insulators are anything but boring.
They actively polarize. Their atomic structures physically distort like dogs leaning on a leash, fundamentally changing the internal electric fields of the universe.
They increase capacitance, they lower voltage, and they physically mechanically react to the steep gradients of non-uniform fields.
It means matter is astonishingly complex.
Yes, and when we try to write simple equations like using the D vector for an accounting trick or lazily putting kappa into Coulomb's law, we have to remember we are making engineering approximations.
We shouldn't settle for textbook simplifications that ignore the true, chaotic, beautiful quantum reality of atomic polarization.
I love that.
Next time you're folding laundry in the dry winter air and a sock randomly leaps up and sticks to your shirt, or you see a plastic comb pull a piece of lint off the counter, you'll know you aren't just seeing a cute static magic trick.
You are witnessing the gradient of the square of an electric field acting upon billions of induced atomic dipoles.
You are literally watching the physical universe seeking a lower energy state.
And that leaves us with one final, profound puzzle to mull over. Throughout this entire deep dive, we simply accepted a premise. We accepted that an atom's polarization is proportional to the electric field.
You pull on the leash, the dog leans.
But why is there a proportionality at all?
Yeah, why does it happen at a fundamental level?
What deep underlying quantum mechanical rules dictate that the atoms in a piece of glass are highly polarizable and easy to stretch, while the atoms in a piece of wood barely react to the exact same field?
It's wild to think about.
The origin of the dielectric constant from a purely atomic quantum point of view is a massive, incredibly complex mystery. And yet it dictates how light moves through water, how our computer chips store memory, and how the very cells in our bodies communicate with each other.
And that deep quantum reality, why one wall acts like an engine and another acts like a sponge, is a beautiful mystery we'll leave for you to explore on your own.
You know, usually electricity is a story of movement, electrons sprinting down a copper wire, just this highly kinetic flow of current that powers, well, basically everything around us.
Right, it's incredibly useful, so we tend to just naturally fixate on that flow.
Exactly. But today, for all of you curious minds joining us on this deep dive, we are actually looking at the roadblock. We're looking at what happens inside materials where electricity categorically cannot flow.
And that's a really fascinating space because when you take an electric field and apply it across, say, a cloud of steam or a block of wax or a solid crystal, you don't just get a dead end.
No, you get this intricate, practically invisible microscopic ballet. Okay, let's unpack this. We know materials interact with electricity, but why? How do these invisible atoms and molecules actually physically shift and twist to create the phenomena we use every day?
Well, to figure out that big picture, we have to start incredibly small. Our source material today is all about the internal life of dielectrics, which are just insulating materials that don't conduct electricity but still profoundly respond to it.
Right, they kind of fight back against the electric field, don't they?
They do, yeah. And the key metric we use for this is called the dielectric constant, which physicists denote with the Greek letter kappa. It basically tells us how much a material weakens an external electric field by generating its own internal counterfield.
So this whole deep dive is essentially a journey of scale. We're going to start with isolated gas atoms, and then move into the really crowded environment of liquids, and finally look at the rigid and honestly kind of runaway structures of solid crystals.
Exactly. And the best place to start is at the absolute bottom of that scale. with gases. Because in a low-pressure gas, the atoms are spaced so far apart that they barely interact with each other.
We can just look at one isolated atom and see what it does.
Right. And the simplest case is a nonpolar gas. So think of something completely symmetric like helium or hydrogen. There is no inherent electrical imbalance. The center of the positive nuclear charge and the center of the negative electron cloud sit in the exact same spot.
So they're just perfectly electrically neutral and balanced.
They are, until you turn on an external electric field. The moment you do that, the balance physically warps. The field grabs the positively charged nucleus and pulls it one way, and simultaneously pulls the negatively charged electron cloud in the exact opposite direction.
Is electronic polarization basically like stretching a rubber band? Like the atom is naturally stiff, but the electric field pulls the positive and negative charges apart just a tiny bit, and the stretchiness of that specific atom is its polarizability.
What's fascinating here is that your analogy holds up beautifully when you look at the math. The constant of proportionality here is called polarizability, or alpha. Different elements have completely different internal stiffness.
Like they have thicker, thinner rubber bands.
Exactly. Take hydrogen, it has one proton, one electron. To completely overcome that atomic stiffness, basically to rip the electron away entirely, requires about 13.6 electron volts of energy.
Okay.
So classical physics uses that ionization energy to estimate the atom's basic stretchiness. And based on that, the math predicts hydrogen gas should have a dielectric constant of 1.00000.
And the actual real-world experimental measurement comes in at 1.00026, right? Which is remarkably close for a classical model that, completely ignores quantum mechanics.
It is remarkably close. It proves the fundamental mechanism is right on track. And you can see it with helium, too. Helium has 2 protons and 2 electrons, so the nucleus has a much tighter electrostatic grip.
So it's a much stiffer rubber band.
A significantly stiffer rubber band. It takes a massive 24.6 electron volts to ionize helium. Because it's so tightly bound, its polarizability is only about 1/4 that of hydrogen.
Which means a much lower dielectric constant. Okay, so stretching a perfectly symmetric atom makes sense. But what happens if the molecule is already lopsided, like a permanent dipole?
Yeah, water vapor is the classic example here. A water molecule has that bent shape, the Mickey Mouse head. So it has a permanent positive end near the hydrogens and a permanent negative end near the oxygen.
So the electric field doesn't even need to stretch it to create a dipole because the dipole's already there.
Exactly. It just needs to physically turn the molecule to align with the field. But that introduces a totally new physical dynamic, because without a field, a cloud of water vapor is essentially a microscopic mosh pit.
Just total chaos.
Complete chaos. Molecules are flying around at hundreds of miles per hour, colliding, tumbling end over end. So all those permanent dipoles are pointing in random directions, completely canceling each other out globally.
But then you turn the field on, and it tries to organize the mosh pit. The positive ends feel a pull one way, the negative ends the other. They try to line up because it lowers their energy.
Right, and this is crucial, it's only a partial alignment.
Wait, if the electric field really wants them to line up, why don't they all just snap into perfect attention and create a massive polarization? Why is it only partial?
Because of the mosh pit. The organizing force of the electric field is in a constant violent battle with the thermal kinetic energy of the gas.
Oh, so as soon as one molecule lines up, another one just smashes into it.
Exactly, just knocks it right off course. And this perpetual battle is formalized in Curie's law, which says that polarization depends inversely on temperature, 1/T.
Because if it gets hotter, they move faster, the collisions are harder, and the electric field just can't keep them organized.
You've got it. The experimental data on water vapor tracks this 1/T relationship flawlessly. But temperature isn't the only limiting factor. Frequency is huge here, too.
Right, like if you put water vapor in a microwave, the electric field is flipping its direction billions of times per second.
And that introduces molecular inertia. The oxygen and hydrogen nuclei are heavy. When the field flips that fast, the bulky water molecule just physically cannot pivot fast enough to keep up.
It's too heavy to spin that fast.
Right, so the permanent dipole alignment just gives up, it drops to 0. But, and this is the cool part, the tiny electrons still have basically 0 mass.
So the electronic polarization, that underlying rubber band stretching we talked about, that just
Yeah.
keeps happening.
It keeps going. The electrons effortlessly buzz back and forth to the microwave field, even while the massive nucleus is just paralyzed.
That is wild. Okay, so gases are relatively easy because the molecules are far apart. But what happens when we take that gas and condense it into a liquid? The crowded room problem.
Yeah, the physics of crowded spaces is notoriously messy. In a liquid, every molecule is practically shoved up against its neighbors.
So the electric field an individual atom actually feels the local field is totally different from the average field of the whole container.
Heavily different. The local field varies wildly depending on if you're right next to a nucleus or in the empty space between atoms. To figure out what an atom actually feels, physicists came up with this brilliant, kind of bizarre theoretical abstraction.
The imaginary spherical holes. So, wait, physicists couldn't actually measure the spaces between atoms, so they literally just imagined carving microscopic, perfectly spherical holes in the liquid to do the math.
That's exactly what they did.
That sounds like a mathematical cheat code.
It kind of is. If we connect this to the bigger picture, these theoretical thought experiments, like removing a uniformly polarized plug from the dielectric, let us isolate the effects of the surrounding material.
And lets them calculate that the local field in that little hole is the average field, E, plus the polarization divided by 3 times the permittivity of free space.
Right, which leads directly to the Clausius-Masati equation. It links the stretchiness of a single isolated atom to the density of the liquid and spits out a predicted dielectric constant.
And the CS2 triumph proves it actually works. Carbon disulfide, right?
Yes. If you condense carbon disulfide from a gas to a liquid at 20 degrees Celsius, it becomes 381 times denser.
So the local fields must be just incredibly intense.
They are. But if you take that basic gaseous stretchiness and plug it into Clausius-Masati with that massive density jump, the math predicts a liquid dielectric constant of 2.76, and the real-world experiment yields 2.64.
That is crazy accurate for an equation based on imaginary spherical holes.
It's a huge triumph of classical physics, though we should note it totally fails for water, which we'll get into later.
Oh, we definitely will.
Yeah.
But first, let's look at solids. Because liquids flow, but solid dielectrics literally lock atoms in place. How does that rigid structure change the game?
Well, it allows for frozen electricity. We call them electrets.
Right, melted wax with dipoles that get lined up by a strong field, and then you just freeze it. You mentioned electrets are the electrical analog to permanent magnets, but everyone has magnets on their fridge. I've never seen an electret stuck to anything. Why aren't these everyday objects?
That is a great question. It's because of how the real world constantly discharges them. Magnets produce a magnetic field, and most things in your kitchen just ignore magnetism.
Right.
But an electret produces a permanent electric field, and the ambient air around us is full of stray, free electrical charges, ion, static, trace radiation.
Oh, so the electret is sitting there broadcasting a huge positive and negative charge.
And those stray charges from the air just rush in. Negative charges coat the positive end, positive charges coat the negative end. Within a very short time, this microscopic layer of environmental static completely masks the internal polarization.
So the magic is hidden by environmental static. It looks neutral to us, but inside it's still locked in attention.
Exactly. The polarization is still there, just masked. Now, wax is one thing, but complex crystal lattices have their own intrinsic polarization.
Like pyroelectricity, where heating the crystal makes it expand and changes the polarization, or piezoelectricity, where bending it creates a spark.
Right. Mechanical stress literally deforms the polarized atomic grid, and even symmetrical ionic crystals like regular table salt, sodium chloride have these effects.
The positive and negative checkerboard ions actually pull apart slightly to create volume polarization.
Yes, the entire subgrid of positive ions shifts slightly one way, while the negative subgrid shifts the other.
Okay, so we've seen that crystals can have permanent polarization. But there's one special class of materials where this whole process just goes entirely off the rails into a mathematical runaway state.
Yes, the ferroelectric mystery of barium titanate.
This material is fascinating. Above 118 degrees Celsius, it's just a normal dielectric, but with an enormous constant, like 50,000 to 100,000.
Which is staggering. But the real magic happens below 118 degrees Celsius. It suddenly locks into a permanent dipole moment. It becomes ferroelectric.
And the math for this goes right back to the Clausius-Masati equation, right?
It does. If you look at the denominator of that equation, there's a term for the number of atoms times their polarizability. If that term, n alpha, ever equals exactly 3, the denominator becomes 0.
And dividing by 0 is never good.
It creates an infinite feedback loop. A tiny fluctuation creates a local field, which polarizes the neighbors more, which increases the field, which polarizes them even more.
The polarization just feeds on itself until the atomic lattice mechanically jams up.
Exactly, and the atomic setup for this is very specific. It's a cubic lattice, barium ions on the corners, oxygen ions on the faces, and one single titanium ion suspended dead center in the middle.
Okay, here's where it gets really interesting, because I was reading the source text and I caught a contradiction. The text says the titanium ion needs to shift off center to make this runaway polarization happen.
Right.
But it also explicitly says the titanium fits very tightly in its oxygen box, while the looser barium atoms on the corners don't cause the effect. How does the tightest piece do the moving?
This raises an important question, and it's one that even Richard Feynman noted. Even in classical, established textbook physics, there are deep mysteries.
So they don't actually know.
Well, the math absolutely demands that the titanium moves to achieve the required polarizability. But mechanically, it doesn't make total sense based on ionic radii.
It's just crammed in there.
It is. But to see how delicate this is, look at antiferroelectric materials. In those, alternating chains of atoms just cancel each other out. One points up, the next points down. Zero net polarization.
But barium titanate is ferroelectric because it has these intermediate chains that sort of force everything to lock parallel.
Right. The intermediate chains act as mechanical bridges, forcing the main chains to align in the same direction. It's an incredibly complex, delicate crystal structure.
Wow. Okay, let's bring it all together for everyone listening. We have been on quite the journey today. We started with the simple rubber band stretching of isolated helium atoms.
Then we waded into the thermal dance of water vapor.
And from there, we carved imaginary spherical holes in liquid CS2 to understand local fields in crowded rooms. Finally, we looked at the runaway locking crystal mysteries of barium titanate.
It really shows how structure defines electrical reality.
And that's exactly why this matters to you, listening right now. Because the screen you are looking at, the battery in your device, the sensors in your car, they all rely on exploiting exactly how these microscopic atoms handle electric fields.
They absolutely do. But I think we should leave everyone with one final, lingering puzzle from the margins of today's text.
The water problem. Let's hear it.
So we talked about how beautifully the Clausius-Masati equation predicted liquid carbon disulfide. But when physicists try to use that exact same elegant math for liquid water, it completely fails.
It literally predicts a negative number instead of the actual measured constant of 80.
Exactly. It predicts a physical impossibility. Water is the most abundant and essential liquid on Earth. It is the solvent of biology.
And yet it breaks the very rules that neatly explain almost everything else we talked about today.
It really does. So I challenge you to ponder this. If water breaks the fundamental models of local fields, what does that imply about the secret, deeply chaotic life of the water molecules right now in the glass sitting on your desk?
That is a brilliant thought to end on. The stuff we drink every day is a microscopic rebel. Thanks for taking this deep dive with us. Keep questioning everything, and we'll catch you next time.
You know, usually when you talk about mastering a complex subject like physics, there is this expectation of a really grueling uphill climb. You spend months studying one topic, you slowly internalize the rules for that specific domain, and then you move to the next chapter.
Yeah, and suddenly you are staring at a whole new set of rules. It just feels completely compartmentalized.
Right, exactly.
Yeah.
It's like you learn to play chess, and then someone hands you a baseball bat and says, okay, now learn this. The skills just don't seem to transfer.
No, they don't. Every new physical phenomenon demands a fresh start. I mean, it's a blank slate where you have to build your intuition completely from the ground up.
But occasionally you stumble into something that feels almost like cheating, like a fundamental skeleton key to the universe. What if learning the rules of just one physical phenomenon meant you instantly, like automatically understood the hidden mechanics of 5 completely different ones?
I mean, that is the ultimate shortcut in science right there. It completely shatters the idea that the universe is just this collection of random, disconnected rules.
Welcome to this deep dive. Today we are taking you through a fascinating piece of source material. It's Chapter 12 of the legendary Feynman Lectures on Physics, Volume II, titled Electrostatic Analogues.
A true classic.
Yeah, it really is. And our mission today is to explore a wild, almost unbelievable reality. The exact same mathematical equations that govern invisible static electricity also perfectly describe how a hot steam pipe cools down, how a rubber trampoline stretches, how a nuclear reactor operates, why a sphere falls through liquid, and even how to properly space the fluorescent light bulbs on your office ceiling.
What's fascinating here is the underlying architecture of it all. In physics, vastly different scenarios often share the exact same mathematical skeleton.
Okay, what does that skeleton actually look like?
Well, specifically, Feynman focuses on an equation where the divergence of a gradient equals some source. To translate that out of textbook jargon, just imagine a hill. The gradient is just how steep the hill is. It's the slope.
Right, the slope.
And divergence is how much of something is flowing outward from a specific point.
Yeah.
Like water spraying out of a sprinkler head.
Okay, let's unpack this. If I put those two ideas together, the gradient and the divergence, what does that actually give me?
It gives you a universal template for how things spread out over space. If you understand how electric voltage drops off as you move away from a charged wire, you possess a mathematical blueprint.
A blueprint for everything else.
Exactly. Any solution you discover for that electric field can be directly translated to other physical fields just by swapping the labels on the variables.
So we are talking about moving from the invisible abstraction of electricity to something you can actually feel on your skin. Let's look at heat.
A great place to start.
Imagine I have a heavy cast iron steam pipe running through a cold room. Calculating how fast that heat escapes into the room sounds like a completely different science than, calculating the electric field of a wire.
It does. And thermodynamics can be incredibly complex to calculate from scratch. But using Feynman's electrostatic analog, you don't have to. You just map the concept.
Map them how?
Well, in our static electricity equation, we have electric field, we have an electric potential, which is the voltage, and we have an electric charge, which is the thing creating the field.
Okay, I'm following.
When we map this to our steam pipe, the electric field simply becomes the heat flow, the voltage becomes the temperature, and the electric charge becomes the heat source itself.
Oh, wow. So if I wrap my steam pipe in a thick layer of insulation and I want to know the exact temperature on the outside of that insulation, I'm basically just looking at a wire wrapped in a material.
You are looking at the exact mathematical twin of a common electronics component, a charged wire surrounded by a conductive cylinder.
That's wild.
And because the math for the electrical component was solved decades ago, you already have your answer for the heat loss. The heat flow drops off logarithmically as you move from the center of the pipe to the outer edge of the insulation. You skip the grueling thermal calculations entirely.
That is incredibly satisfying. But let's push this analogy into a more extreme scenario from the sources. We aren't always dealing with a neat little pipe in a room, right?
Right. Things get messier.
What if we are looking at an intense underground point source of heat? Imagine a concentrated deposit of highly radioactive material buried deep under the earth, or like the aftermath of an underground atomic test.
Oh, that's a classic geophysics problem. You have a massive amount of heat radiating from a single point deep underground, and you want to know exactly how hot the surface of the ground is going to get directly above it.
And how it spreads out across the dirt, yeah. My mind instantly goes to dropping a heavy rock into a deep pool of water. You have this intense point of origin, and it sends ripples expanding outward in a perfect sphere.
That's a really good visual.
But here is where I get tripped up by the math. With a rock in a pool, the ripples just travel until they hit the concrete edge. With the underground heat, the energy travels up through the solid rock, but then it hits the surface. It hits the air.
And air is a terrible conductor of heat compared to solid earth.
Exactly. The heat essentially hits a wall and gets trapped at that boundary. How on earth does a smooth electrical equation handle a hard boundary like the sky?
That boundary condition is exactly where physicists deploy a brilliant mathematical trick. It's called the image source.
Image source.
Yeah. To make the math work so that the heat hits the surface and flows outward, instead of escaping up into the air, they imagine a fake secondary source of heat.
Wait, a fake source? Like a reflection in a mirror?
Think of it as a perfectly mirrored twin. You have your real underground radioactive deposit pushing heat up toward the surface. To balance the equation, you mathematically pretend there is a second, identical radioactive deposit hovering up in the sky.
Hovering at the exact same distance above the ground.
Right, at the exact same distance.
A fake atomic bomb hovering in the sky is a terrifying visual, I have to say.
It is a striking image, but mechanically it solves the problem perfectly. The real underground source is pushing heat up. The imaginary source in the sky is pushing heat down.
And they meet in the middle?
Exactly. Right at the surface, the exact midpoint between them, their vertical flows collide and completely cancel each other out. The mathematical result is a surface where the heat has no choice but to flow perfectly horizontally across the ground.
So by inventing a fictional mirror image in the sky, You trick the equation into modeling the real-world boundary of the Earth. That's brilliant.
You do, but this trick introduces a really fascinating caveat. This mathematical mirror only works if we assume the air above the ground is a perfect thermal insulator.
Meaning absolutely zero heat escapes into the atmosphere.
Yes. And if we want to find the equivalent for that in electricity, we would need an environment with a dielectric constant of absolute zero.
Wait, I need a translation there. What is a dielectric constant and why does absolute zero matter?
A dielectric constant basically measures how much a material resists the formation of an electric field within it. A constant of zero would mean the material offers infinite absolute resistance. No electric field could ever penetrate it.
Does a material like that actually exist?
It doesn't.
Yeah.
Not even the vacuum of deep space has a dielectric constant of zero.
Oh, wow.
So this is a beautiful paradox. To solve a very real physical heat problem, like the temperature of the dirt above a buried reactor, we have to map it to an electrostatic scenario that is physically impossible in our universe.
But the math still gives us the correct answer.
It absolutely does. The math creates a bridge between a tangible reality and an absolute impossibility.
The math really doesn't care if the universe can actually build the thing as long as the numbers balance. Okay, so we've looked at invisible heat transferring through solid ground, which is a rigid, stationary medium.
Right.
What happens if the medium itself can physically move and stretch? The sources talk about a stretched rubber membrane.
Picture a thin, highly elastic rubber sheet stretched very tightly over a large circular frame. Like a drum head or a trampoline.
Okay, I'm picturing it.
If you take a wooden rod and push it up into the rubber from underneath, and maybe take another rod and push down from above, the rubber stretches into a landscape of hills and valleys.
It does.
The physical shape that the rubber takes, the actual tangible curvature, perfectly mimics a two-dimensional electrostatic field.
Wait, how does poking a rubber sheet with a broomstick do the same math as an electrical circuit? I mean, I'm completely lost on how a physical piece of rubber knows how to do calculus.
It all comes down to the mechanics of tension. In this physical model, the height of the rubber at any given point, how high the hill is or how deep the valley is, represents the electrical voltage.
Okay.
The physical steepness of the slope represents the strength of the electric field.
Okay.
And the rubber itself, pulling against its own surface tension to try and flatten back out, acts as the medium that the electric field travels through.
Oh, I see. So when I push the rod up, I'm creating a high voltage point. And the way the rubber naturally drapes down away from the rod is the exact same curve as the voltage dropping away from a charged wire.
It maps perfectly.
That feels like a really fun classroom trick, but is there any practical use for that?
Historically, it was a massive technological breakthrough. Before we had powerful silicon computers capable of simulating complex electric fields, engineers built literal physical rubber sheet models.
Really?
Yeah. They would stretch out a huge membrane and push different shaped rods and blocks into it to represent various electrical components at different voltages.
So they built a physical bouncy simulator for electronics?
They created a literal analog computer. Once they had the hills and valleys set up, they would take little steel ball bearings and roll them across the surface of the rubber.
That is so cool.
By watching the paths those marbles took as they curved around the peaks and accelerated into the valleys, engineers could perfectly simulate the trajectories of microscopic electrons flying through a vacuum tube.
You're saying they mapped the paths of invisible electrons by rolling marbles on a tiny trampoline.
They did, and it led to incredible inventions.
Mm.
This specific rubber sheet method was used to design the internal mechanics of photomultiplier tubes.
What do those do?
They're highly sensitive devices that detect incredibly faint sources of light by bouncing electrons off a series of precisely shaped metal plates to multiply the signal.
Yeah.
Engineers used the rubber sheet to figure out the exact shape and angle those plates needed to be.
Okay.
And they used this to design the sensors that automatically dim the headlights on vintage 1950s Cadillacs.
No way. The luxury feature on a classic Cadillac was brought to you by engineers playing with a rubber drum head. I love that so much. We just jumped from an underground atomic test to a Cadillac headlight using the exact same equation.
It's universally applicable.
Okay, so rolling marbles on a stretch sheet makes sense because the marbles are physical objects we can track, right? We can watch them curve. But what if we zoom into things so small and moving so fast that we can't possibly track their individual paths? The source material takes us down to the chaotic world of a nuclear reactor.
Yeah, at the subatomic scale, inside a nuclear reactor, you have neutrons flying around at incredible speeds. Imagine a massive block of graphite. Reactor designers use pure carbon graphite because it slows neutrons down without absorbing them.
So the neutrons are free to just wander around?
Exactly. A single neutron travels in a straight line, smashes into a carbon nucleus, bounces off in a completely random direction, travels, and smashes into another one. It is a wildly unpredictable, chaotic mess.
So if I try to map the path of one single neutron, it's just a zigzag of random collisions. There's no smooth curve there.
Looking at one neutron is impossible to model with our smooth equation, but when you zoom out and look at the average behavior of millions of these bouncing neutrons diffusing through the graphite block, the chaos averages out.
And it creates a pattern.
Yes, the overall flow of that neutron cloud follows the exact same diffusion equation as our static electric charge.
So if we have a sphere of uranium sitting inside that graphite block, and it is actively undergoing fission, it's generating a massive cloud of neutrons.
And we desperately need to know the density of that neutron cloud in and around the sphere to keep the reactor safe. Because we know how a uniformly charged sphere behaves in electrostatics, we don't have to guess.
We just use the shortcut.
Right. The source of the neutrons replaces the electrical charge, and the density of the neutrons replaces the voltage.
Now, my intuition tells me that if the entire sphere of uranium is generating neutrons equally across its whole volume, then the density of the neutrons inside that sphere should also be equal everywhere. A uniform source should create a uniform density.
The math reveals that intuition is completely wrong.
Wait, really? Why? What is actually happening inside the sphere?
It comes down to traffic. Even though neutrons are being born evenly everywhere, the neutrons born near the outer edge of the sphere have a very short trip to escape into the empty graphite surrounding it. They diffuse away quickly.
Oh, I see.
But the neutrons born in the dead center of the uranium sphere are trapped. They are surrounded on all sides by other neutrons trying to push their way out. It creates a massive subatomic traffic jam.
So the center is far denser than the edges. Does the electrostatic equation tell us exactly how much denser?
It gives us the precise ratio. The equation reveals that the neutron density at the exact center of the sphere is exactly 1.5 times greater than the density at the outer edge. The curve of the density perfectly matches a parabola.
Understanding the electric field of a charged ball gives physicists a massive head start in predicting the core dynamics of a nuclear reactor. That is just incredible.
Okay, we've been talking about things diffusing through solid, stationary mediums, like heat through rock or neutrons through a block of graphite. What if the medium itself is moving?
Like a fluid. Yeah, what if we try to apply this to a flowing river? Does the math break?
Moving mediums bring us to fluid dynamics. Suppose we want to apply our electrostatic equations to water flowing past a stationary spherical ball in a stream. To make the clean, smooth equations of electricity fit the messy reality of water, we have to make some severe assumptions about the liquid.
I am guessing we can't just scoop water out of a river and expect the numbers to work perfectly.
Far from it. We have to pretend the liquid is totally incompressible, meaning you cannot squeeze it or change its density at all.
Okay.
We also have to pretend it is completely non-viscous, meaning it has zero internal friction. It flows with zero resistance. And, most critically, we have to pretend the flow is entirely irrotational, which means it has a curl of zero.
What is curl? How does water have zero curl?
Imagine dropping a tiny microscopic paddle wheel into the stream of water. As the water carries the paddle wheel downstream, if the water has any tiny whirlpools, eddies, or differences in speed, that paddle wheel will start to spin.
Okay, I can picture that.
That spinning motion is curl. For our math to work, that imaginary paddle wheel must float perfectly downstream without ever rotating a single degree.
Which is an enormous problem because real water spinning around a rock in a river creates turbulent wakes and whirlpools everywhere. It almost always develops circulation.
The famous mathematician John von Neumann had a great joke about this. He said that physicists who study this idealized, frictionless, non-spinning fluid aren't studying water at all. They are studying dry water.
Dry water. You have to invent a completely fake liquid to make the math happy.
Even with the absurdity of dry water, the mathematical cheat code gives engineers a vital theoretical baseline. They calculate the perfect, smooth flow first, and then use that foundation to add the messy reality of turbulence back in later.
Okay, let's step away from the abstract joke of dry water and look at a highly practical, everyday engineering problem from the sources. We are sitting in a room right now. If you look up at the ceiling.
We enter the world of illumination engineering. Suppose you have a large drafting desk, and you need it to be perfectly evenly illuminated. No harsh shadows, no bright spots. You are installing long tubular fluorescent lights on the ceiling.
Right.
The practical question is, how far apart should you space those light tubes to get a perfectly smooth wash of light down on the desk?
If I'm an electrician just guessing, I might space them too far apart and end up with annoying dark bands between the lights. Or I might pack them too close together and waste a fortune on electricity. How do we get from dry water to my office lighting?
The light radiating from a long fluorescent tube behaves mathematically the exact same way as the electric field radiating from a long charged wire. We can treat the lights on the ceiling as a grid of charged wires.
Oh, I get it. Think of the light from each tube as overlapping waves of water in a pond. The math is going to calculate exactly how those waves intersect, overlap, and average each other out until the surface of the light hitting the desk is perfectly flat. So if I want the lighting on my desk to be so uniform that the human eye couldn't possibly detect a single difference in brightness, say variations of less than 1 part in 1,000, how far apart do the tubes need to be?
The electrostatic math provides a surprisingly simple rule of thumb. To achieve that near-perfect uniformity, the spacing between the tubes on the ceiling should be roughly 0.91 times the distance from the ceiling to the desk.
And if you want to be perfect,
If you run the absolute exact calculations to minimize every possible shadow, the ideal spacing coefficient is closer to 0.83.
so if my ceiling is 10 feet above my desk, I can space those light tubes over 8 feet apart, and the light hitting my desk will still look practically flawless. That is surprisingly far apart.
It is. The overlapping waves wash out the dark spots remarkably fast.
And you know that for a fact, without having to build a single test room or turn on a single light bulb, all because you understand the electric field of a charged grid.
That's the power of the analog.
We have jumped from a hot steam pipe to a rubber trampoline, to the chaotic core of a nuclear reactor, to dry water, to the fluorescent lights above our heads. So what does this all mean? We have to ask the ultimate philosophical question here. Why are the equations the same? Is everything in the universe secretly made of the exact same stuff?
It is deeply tempting to think that, but no. Heat flowing through rock is physically nothing like a bouncing subatomic neutron. A stretched rubber membrane is not a voltage.
So where does the connection come from?
The underlying unity of nature doesn't come from the physical material itself. It comes from the framework that all these materials exist within. Space.
Space is the canvas.
The differential equations we are using are actually just smoothed out macroscopic approximations. As long as things are spread out reasonably smoothly over a large enough area of space, the laws of physics depend on how things change with position in that space.
It's like zooming out from a massive crowd of people in a city square. If you look closely at the neutrons in a reactor or the individual heat molecules in a steam pipe, they are chaotic, unpredictable, zipping around and crashing into each other.
Right, totally random.
But when you zoom out far enough, their average behavior looks like a single, smoothly flowing river. We're just using simple math to imitate highly complicated microscopic chaos.
We are tracing the macroscopic shadow of microscopic complexity.
Okay, here's the million-dollar question then. If heat and neutrons are just chaotic things smoothed out when we zoom out, is electricity the same?
That is the big question.
We have these beautiful, perfectly smooth equations of electrostatics. Are they actually hiding some tiny, chaotic, undiscovered particles underneath? Let's call them exons. Are there chaotic little exons causing electricity that we just can't see because our microscopes aren't powerful enough?
That is the most profound question Feynman poses in this chapter. It is entirely possible that our pristine equations for electricity are just smoothed out versions of a hidden underlying machinery.
Do we have any proof?
Currently, our equations for electrodynamics work flawlessly at distances down to about 10 to the negative 14 centimeters.
Yeah.
That is a decimal point, 13 zeros, and a 1.
Incredibly small.
Beyond tiny. But below that threshold, at distances smaller than 10 to the negative 14 centimeters, things start to get weird. The smooth equations begin to fray. So physicists have actively tried to invent theories of a hidden underlying complexity, your exons.
And what happens when they try to rewrite the equation to include the microscopic chaos?
They hit a mathematical brick wall. The combined laws of relativity and quantum mechanics seem to forbid it. Whenever someone tries to change the fundamental equation of electrostatics to account for a hidden mechanism, it results in severe internal mathematical contradictions.
What kind of contradictions?
Well, the math suddenly predicts absurdities. It will predict that the sum of the probabilities of all possible events occurring is greater than 100%. Or it will calculate that the energy of a system is an imaginary number.
Oh, that just breaks reality. You can't have a 120% chance of an electron moving left, and you certainly can't have an imaginary amount of energy powering a light bulb.
No, you can't. Nobody has yet formulated a successful theory of electricity with a hidden chaotic mechanism underneath that doesn't ultimately lead to some kind of mathematical absurdity.
So we are trapped with the smooth equations. Thank you so much for joining us on this deep dive. You started this journey looking for a cheat code to the universe, and you really found one. You can literally map the core of a nuclear reactor by poking a rubber sheet with a stick.
It's an amazing universe.
It really is. But before we sign off, I want to leave you with a final mind-bending paradox directly from Chapter 12. As we just discussed, trying to change the smooth electrostatic equation to find hidden particles leads to absurdities. But assuming that the smooth equation is perfectly valid at all microscopic distances leads to an absurdity of its own.
The ultimate trap.
Exactly. If you zoom all the way in on a single point-like electron, the distance from the center of that charge goes to zero. And because the equation requires you to divide by that distance, if you run a distance of zero through our perfect, flawless electrostatic math, the calculation for the electrical energy of that single electron becomes infinite.
Which is impossible.
It is an impossible contradiction. The cheat code works beautifully for 5 completely different levels of reality, from steam pipes to Cadillacs. But at the very bottom of the code, at the smallest possible point in the universe, there is a bug that breaks reality. Something for you to chew on as you sit back, look up, and appreciate the incredibly uniform fluorescent lighting in your room. The magnet holding a picture to your fridge right now, it doesn't actually exist. At least not the way you probably think it does.
Yeah, that invisible pole, the one that feels completely distinct from, like, the static electricity you get from rubbing a balloon on your hair.
Exactly. Well, here's the crazy part. It is literally just electricity. I mean, it is an electrical force that has been heavily disguised by the bizarre space-bending effects of Einstein's theory of relativity.
It really is wild when you break it down.
It's mind-blowing. So, welcome to this custom-tailored deep dive into the source material you provided us. We are taking a really close look at Chapter 13 of the legendary Feynman Lectures on Physics, Volume 2.
Right, the chapter titled Magnetostatics.
Our mission for you today is to unpack the dense ideas, the specific terminology, and the mathematical framework in this text to uncover what the actual mechanical reality of magnetism is.
Because it's not just about things sticking to metal, you know. It's a journey that starts with a highly counterintuitive sideways push and ends up unraveling the very fabric of space-time.
Yeah, so let's get into it. Where does this start?
Well, Feynman structures this exploration beautifully. He doesn't just hand you the grand unified theory right up front. He forces you to confront the mechanical strangeness of the phenomenon first.
Right, building it from the ground up.
Exactly. So we begin with the total electromagnetic force acting on a charge, which physicists call the Lorentz force. And the electric component of this force behaves linearly and predictably.
Meaning what, exactly?
Meaning, if you place an electron in an electric field, it gets pushed or pulled along the field lines, completely independent of what it's already doing.
Oh, okay, so it doesn't matter if it's moving.
Right, it could be stationary or it could be traveling at a massive fraction of the speed of light. The electric force vector operates exactly the same way, pushing it straight.
The magnetic component, however, is a whole different beast. It strictly depends on velocity.
Yes. If a charged particle is sitting perfectly still inside, like a super powerful magnetic field, the magnetic force acting on it is exactly zero.
Wait, really? Zero?
It's literally zero. The interaction fundamentally requires motion. And when that motion does occur, the resulting force isn't applied in the direction of the field, nor in the direction the particle is traveling.
It pushes it sideways, right?
Yeah, it acts perpendicularly to both. Mathematically, the Lorentz force equation uses a cross product to describe this. So the force is the charge multiplied by the cross product of the velocity vector and the magnetic field vector.
Right, and in three-dimensional space, a cross product gives you a new vector that is mutually orthogonal to the plane created by the first two.
Exactly. So if your velocity is, say, moving along the x-axis,
Yeah.
and your magnetic field points along the y-axis.
Then the resulting force pushes along the z-axis. That is so bizarre.
It is.
You know, it's conceptually similar to, well, it's like walking down a hallway and there's a magical fan blowing, and it does absolutely nothing when you stand still, but the moment you start jogging forward, it only blows you sideways into the wall.
That is a highly accurate mechanical analogy, actually. I love that.
Thanks. It just helps to visualize it, you know.
Definitely. And Feynman illustrates this right-angle deflection. using the classic example of a cathode ray tube, like the kind found in vintage heavy televisions.
Oh, yeah, the big boxy
All
ones.
right, those tubes fire a continuous beam of electrons toward a screen. If you bring a standard bar magnet near the glass of that tube, you literally see the invisible electron beam deflect sideways.
Because the electrons have a velocity vector toward the screen, and the magnet introduces a field vector intersecting that path.
Exactly, and the cross product of those two vectors dictates a physical force pushing the electrons laterally. You are directly observing the Lorentz force cross product playing out in real time.
That's so cool. And the text gives us a specific metric for quantifying this field strength, right? Newton seconds per Coulomb meter.
Yeah, though in more common terminology, physicists refer to these units as Webers per square meter.
Webers per square meter. Got it. So this establishes our foundational premise. Moving charges are subjected to this orthogonal magnetic force.
Which means the logical flip side to that premise is that only moving charges can generate the field in the first place.
Right. If moving charges feel the force, they must create it too. And the text quantifies this generation through the concept of current density.
Yeah, and current density isn't just a scalar number, like a simple measurement. It's a vector field representing the flow of electrical charge per unit area.
And it operates under a pretty strict principle in physics, right? The conservation of charge.
Exactly. Charge is an intrinsic property of matter that can never be created or destroyed.
Mm-hmm.
If we look at the continuity equation for electromagnetism, it dictates a hard rule.
Which is?
If the total amount of charge in a specific closed volume of space decreases, it absolutely must be because a measurable current flowed outward through the boundaries of that volume.
Ah, I see. It has to go somewhere.
Right. And when that charge translates through space, the magnetic field is born. Magnetostatics specifically focuses on scenarios where these currents are steady and unchanging over time.
But this introduces a massive structural divergence from how electric fields operate, doesn't it? Because electric fields have clear source points.
You do. You can isolate a single proton or a single electron, and the electric field lines will just radiate outward from that point, source in all directions.
So in physics terminology, electricity has monopoles, but magnetism does not.
Right. Ampere's law governs this behavior. It details that magnetic field lines never have a distinct starting point or ending point. They never diverge from a central source.
So what do they do?
They strictly form closed loops circling around the path of the moving current. Because there are no single magnetic charges or magnetic monopoles, you can never isolate a source of, like, northness or southness.
Wait, so if there are no single source points for magnetism, what happens if I take a typical bar magnet with a north pole and a south pole and just chop it perfectly in half? Do I get a north magnet and a south magnet?
Well, no, that's a classic physics thought experiment, actually. You instantly get two smaller complete magnets.
Really? Just two smaller ones?
Yeah. Because the macroscopic magnetic field isn't, pooling at the ends of the iron bar. It is the sum of continuous, microscopic, closed loops traveling entirely through and around the material structure.
Wow, okay. So to understand how those loops form a permanent magnet, the text has us look at the behavior of parallel wires.
Right. If you run a steady current through two parallel wires in the exact same direction, the magnetic fields generated by those moving charges interact.
And they cause the physical wires to attract one another.
Exactly.
Yeah.
And if you reverse the current in one wire so they flow oppositely, the wires physically repel.
Okay, so then Feynman asks us to imagine taking one of those wires and tightly coiling it into a spiral, creating what's called a solenoid.
Yeah, solenoid. Because the current is looping repeatedly in the same direction, the individual magnetic fields from each loop perfectly align and stack on top of each other.
Oh, that makes sense. The geometry of the coil forces the magnetic vectors to add together.
Exactly, generating a powerful, uniform magnetic field pointing straight down the hollow center of the coil. And here's the kicker. The external field of this solenoid looks absolutely identical to the field of a standard bar magnet.
Which brings us back to the atomic reality of that chunk of magnetized iron on your fridge, because the iron doesn't contain a dedicated, magnetic substance.
Right, it's composed of atoms containing electrons. And electrons possess two crucial properties. They carry an electric charge, and they have quantum mechanical spin.
Okay, spin?
Yeah, this intrinsic angular momentum essentially makes every single electron a microscopic loop of electrical current.
So a single electron operates as an incredibly tiny solenoid.
That's a great way to put it.
But then, in non-magnetic materials like wood or plastic, The spin axes of these countless electrons are just oriented randomly, right, pointing in every conceivable direction.
Yeah, meaning their microscopic magnetic fields completely cancel each other out on a macroscopic level.
But in ferromagnetic materials like iron, it's different. The quantum mechanics of the crystal lattice allow for regions called magnetic domains.
And within these domains, the spins of billions of unpaired electrons cooperatively align in the exact same direction.
So when an external magnetic field is applied to magnetize the iron, these domains shift and lock into a unified orientation.
Precisely. The permanent magnet on your fridge is simply the macroscopic summation of billions of atomic currents perfectly synchronized. It is moving charge, entirely contained within the atomic structure.
That is unbelievable. So understanding that magnetism fundamentally requires moving charges really sets up the core relativistic mind bender of this entire deep dive.
It really does. It is the exact problem that guided Albert Einstein towards special relativity.
Because if the existence of the magnetic force depends entirely on the relative velocity of the charge, then the fundamental reality of the force should change if we shift our frame of reference.
Exactly. And Feynman sets up a brilliant thought experiment to demonstrate this. Imagine a perfectly straight copper wire carrying a steady, direct electrical current.
Okay, I'm picturing it.
Spatially adjacent to this wire, there is a single negative particle, let's say an electron, moving parallel to the wire at the exact same velocity as the drift speed of the conduction electrons flowing inside the wire.
All right, so let's establish our first observational perspective. We'll call it frame S. In frame S, we're sitting perfectly stationary in a laboratory, just watching the system.
Right. From our perspective, the physical copper wire is perfectly still. Because it's a standard wire, it is electrically neutral.
Meaning the stationary positive protons in the copper lattice are perfectly balanced by the equal number of negatively charged conduction electrons flowing through it. So there is zero electric field.
Correct. However, because the external electron is moving relative to us, it feels that cross-product Lorentz force we talked about. The magnetic field generated by the current in the wire deflects the moving electron, pulling it laterally toward the wire.
Okay, makes total sense. The mechanics in frame S are perfectly consistent with classical electromagnetism. But here is where the paradox emerges.
Right, when we shift to frame S prime.
Yes, in frame S prime, we accelerate our observational perspective so that we are flying alongside the external electron.
So from this new vantage point, the external electron is hovering right next to us. Its relative velocity is exactly zero.
And according to the absolute rules of the Lorentz force we just established, if velocity is zero, the magnetic force must be zero.
Exactly.
But if there is zero magnetic force, the particle shouldn't be pulled toward the wire. But that completely breaks the laws of physics. The universe has to agree on objective reality.
Yeah, an observer in the lab sees the particle hit the wire, so the observer in frame S prime must also see the particle hit the wire.
Right. So the fundamental question is, if the magnetic field essentially vanishes because our relative velocity is zero, what physical mechanism is pulling the particle toward the wire?
It's a huge paradox. But the resolution lies in the fact that we cannot ignore the constraints of special relativity.
Einstein's postulate, right?
Yes. It states that the speed of light in a vacuum must remain constant for all observers, regardless of their frame of reference.
And for the speed of light to remain invariant while relative velocities change, the dimensions of space and time themselves must bend.
Which introduces relativistic length contraction. When an object moves relative to an observer, its spatial dimension actually contracts along the axis of motion.
So the spatial geometry of the wire literally changes depending on how fast you are moving.
It does. Let's look really closely at the charges inside the wire from our moving perspective in frame S prime.
Okay.
The negative conduction electrons in the wire were moving at the same speed as our external electron. Since we are now flying at that exact speed, those conduction electrons appear perfectly stationary to us.
Okay, so because they are stationary relative to our frame, they do not undergo length contraction. Their spatial density remains exactly the same as it was in the laboratory frame.
Exactly. However, consider the positive copper ions forming the crystal lattice of the wire. In the laboratory frame, they were stationary.
But from our moving perspective, in frame S prime, those positive ions are now rushing backwards away from us at high speed.
Yes, and because they are moving relative to our frame, the space between them undergoes relativistic length contraction. The physical distance between each positive ion literally shrinks.
Oh, wow. Which means the spatial density of the positive charges fundamentally increases. You have a higher concentration of protons per millimeter of wire than you do electrons.
Precisely.
So the wire is no longer electrically neutral.
Exactly. The length contraction breaks the electrical neutrality of the wire in this specific frame of reference. From our perspective in frame S prime, the wire now possesses a net positive electrical charge.
And a positively charged wire will exert a standard linear electric force on a nearby stationary negative particle.
Right, pulls the electron straight in. The physical reality of the universe remains consistent. The particle hits the wire in both frames.
But the mechanism driving it completely transformed.
Yeah, the phenomenon that the stationary observer measured as a completely magnetic force has mathematically and physically transformed into a purely electric force for the moving observer.
That is insane. So the mixture of electric and magnetic fields you measure is not an absolute property of the objects themselves?
Not at all. It is entirely dependent on your relative velocity.
This proves that magnetism isn't an independent fundamental force of nature. Electricity and magnetism are a single unified phenomenon, electromagnetism.
Beautifully said. Magnetism is just the electrostatic force viewed from a different inertial frame, modified by the spatial geometry changes demanded by special relativity.
Which forces us to reconsider the ontological reality of the fields themselves, because Feynman explicitly warns against a very common conceptual pitfall here.
He does. In textbooks, we represent these fields using continuous, sweeping lines of force. We often visualize them as like physical strings under tension.
Right, but assigning tangible physical reality to these field lines leads to logical contradictions. I mean, especially since we just proved a magnetic field can literally disappear simply by accelerating our perspective.
Exactly.
So thinking of magnetic field lines as actual physical objects in space is kind of like looking at a meteorological weather map.
Oh, the isobar analogy.
Yeah. You see the wavy isobar lines denoting high and low atmospheric pressure systems. But if you walk outside into a storm, you cannot reach up into the sky and physically touch an isobar.
No, you definitely can't.
The lines aren't physical entities. They are just abstract mathematical shorthand used to calculate the physical force, the wind that will act upon you at a specific set of coordinates.
That's exactly right. The fields are mathematical constructs detailing the potential forces within a space. And the text outlines several key mathematical properties governing this construct, the most crucial being superposition.
Right, superposition, which dictates that if you have multiple steady currents creating multiple magnetic fields, you can calculate the total field at any point simply by taking the vector sum of the individual fields.
Yeah, the fields add together cleanly, without distorting each other.
Because if electromagnetism didn't obey the principle of superposition, the fields would interact nonlinearly. It would cause unpredictable, chaotic interference.
The mathematics of our universe would be impossibly complex if that were the case.
Thankfully, they aren't. And the underlying symmetry that allows for this linear behavior is deeply tied to how these quantities transform relativistically.
Yes. In relativity, space and time are not independent. They are bound together into a single four-dimensional continuum known as Minkowski spacetime.
Right, where you define an event using a four-vector, 3 spatial coordinates and 1 time coordinate.
And the text reveals an incredibly profound parallel here. Charge density and current density also form a four-vector.
Oh, wow. So just as space and time scale together under Lorentz transformations, the charge density, which generates electric fields, and the current density, which generates magnetic fields, they scale together too.
Exactly. They are intrinsically mathematically linked. It is the mathematical skeleton of the universe.
That's incredible.
When you shift your frame of reference, time dilates and space contracts. Because charge density is intrinsically tied to spatial volume, the contraction of space necessitates a proportional shift in the charge and current densities.
Which is the exact mathematical engine that transformed the magnetic field in frame S into the electric field in frame S prime.
You got it. The geometry of space-time dictates the rules of electromagnetism.
You know, this inherent geometric symmetry brings up an interesting detail regarding the right-hand rule.
Ah, yes, the good old right-hand rule.
We use it constantly in physics to calculate the orthogonal direction of the Lorentz force cross product. You know, you point your fingers along the velocity vector, curl them toward the magnetic field, and your thumb indicates the resulting force. But does this mean the physics of our universe possesses an inherent preference for right-handedness or parity?
It does not. The physics of electromagnetism perfectly conserves spatial parity. The right-hand rule is strictly a human bookkeeping convention.
Just a way to maintain mathematical consistency when dealing with three-dimensional cross products.
Exactly. Think about it. If the global physics community decided tomorrow to rewrite every textbook using a left-hand rule, two things would happen.
Okay, what's the first?
First, the mathematical vector representing the magnetic field would flip 180 degrees on paper.
Right.
But secondly, the cross-product calculation for the resulting force would also reverse.
Oh, it's a double negative.
Yes, the reversal of the field vector and the reversal of the calculation method perfectly cancel each other out.
Meaning the physical observable result in reality, like the electron beam deflecting toward the glass of the TV or the parallel wires attracting each other, it remains completely unchanged.
The universe operates symmetrically. It is entirely indifferent to our mathematical conventions.
Well, we have covered immense intellectual territory today. To trace the arc of this deep dive, we started by examining a highly counterintuitive, velocity-dependent sideways force.
A very weird force.
Very weird. Then we tracked the source of that force to the continuous closed loops of moving electrical current, scaling from parallel wires all the way down to the cooperative quantum spin of unpaired electrons inside ferromagnetic iron.
Right down to the atoms.
And finally, we shattered the illusion of a divided universe by utilizing relativistic length contraction to prove that magnetism isn't an independent phenomenon at all.
Not at all.
It is simply the electrostatic force mathematically distorted by the geometric constraints of moving through spacetime.
It really is the ultimate testament to the elegance of physics. Deepening our understanding of the mechanics didn't fracture the universe into more complicated pieces. It actively unified it.
It proved that phenomena that appear wildly distinct in our macroscopic lives are actually just different perspectives of the exact same underlying reality.
Exactly. Which leaves us with a profound, lingering question to ponder.
Ooh, lay it on us.
If electricity and magnetism, forces responsible for everything from lightning strikes to the structure of solid matter, can be unified into a single mechanism simply by shifting our relativistic velocity, what other fundamental forces might just be different perspectives of the same exact phenomenon?
Wow.
Could gravity and quantum mechanics, which are currently totally incompatible in our math, one day be unified through a similar geometric revelation?
It's the ultimate goal of modern physics, hiding right there in the math of a simple fridge magnet. Thank you for providing such incredible, rigorous source material for us to explore. Keep questioning the mechanics of reality, keep reading, and most importantly, keep learning. So imagine the empty space just outside a tightly coiled wire, like the kind you'd find inside your car's alternator.
Or, even just resting inside your wireless phone charger.
Right, exactly. Now, if you were to take a compass and hold it right there, just millimeters away from the outside of that coil, absolutely nothing would happen.
Yeah, the needle wouldn't twitch at all.
Which is wild because you'd think, quite reasonably, that the space is completely empty. But today, we're going to prove to you that it is actually haunted by this invisible, swirling mathematical ghost.
It really is one of the most beautiful and counterintuitive illusions in all of physics.
Yeah.
We get so used to thinking about physical fields in a very linear, straightforward way. But electromagnetism demands a totally different perspective.
Welcome to the deep dive. Today, we are immersing ourselves in the legendary Feynman lectures on physics, specifically Chapter 14 from Volume 2.
A fantastic chapter.
It really is. And our mission today is to conquer a deeply misunderstood concept known as the vector potential. We are going to decode the terrifying vector calculus behind it, visualize these invisible fields in your mind, and along the way, we're even going to solve this bizarre paradox about relativity and spinning cylinders.
Exactly. Our journey today takes us from the pure, abstract mathematics of steady electrical currents, magnetostatics, right, to the physical reality of coils, wires, and rotating tubes.
And if we do this right, it is going to fundamentally change how you look at the supposedly empty space around you.
Oh, absolutely.
Okay, so let's unpack this. Usually when we try to figure out a physical field like gravity or just a simple electric field, we rely on a very comforting shortcut.
We treat it like geography.
Right. You get an elevation map. If you put a ball on a hill, the map tells you which way is downhill, and you instantly know which way the ball is going to roll.
Yeah. And in physics, that neat little shortcut is called a scalar potential.
And it's so nice when we can use it.
It's a huge relief. We love categorizing things as a simple landscape of high points and low points. If you know the voltage, which is really just the electric potential, you just look at your map, find the steepest slope, and that tells you exactly what the electric field is doing.
Water flows straight down the hill.
Exactly.
straight down.
But then you step into the world of magnetic fields, and suddenly that simple elevation map goes right out the window.
Completely out the window.
Because magnetic fields don't play by those rules, right? They don't just point from high to low. They twist, they loop, they wrap around things.
Right, and what's fascinating here is the mathematical reason why they do that. It comes down to a property called curl.
Which is exactly what it sounds like.
Yeah, imagine throwing a tiny leaf into a river. If the leaf just flows straight downstream, the curl is 0.
Okay.
But if the leaf gets caught in a whirlpool and starts spinning, that region has a high curl.
I see.
In electrostatics, the electric field has 0 curl. It just flows straight outward from a charge, down the hill. So because it doesn't whirlpool, you can use that simple elevation map.
Precisely. But a magnetic field, which we call a B field, is generated by currents flowing through wires. It loops entirely around those wires in continuous circles.
So its curl is definitely not 0.
Not at all.
Yeah.
So you can't represent it as a simple gradient or slope. You can't just assign a single number, like a simple height, to every point in space to describe it.
Which means the math gets terrifyingly tangled.
Oh, it's a nightmare.
But wait, so you're telling me physicists couldn't solve the magnetic field directly using an easy map, so they invented a loophole. I was reading the source material, and I gotta be honest, it almost feels like cheating.
Well, it is the ultimate mathematical hack,
Right.
but it's a perfectly legal one. While the magnetic field's curl is very much alive, it has another property called divergence that is completely dead, just 0.
Okay, what exactly is divergence? Give me another visual for that one.
Think of divergence like a sprinkler head or a drain. If a field bursts outward from a central point, like water spraying from a sprinkler, it has high divergence.
And electric fields do this all the time, right?
Yes, they diverge away from an electric charge. But there are no magnetic charges in the universe. There's no isolated North Pole particle sitting there spraying out magnetic field lines.
Oh, right, because magnetic lines never start and they never stop.
Exactly. They always form closed loops.
Okay, so because they only ever loop and never burst outward or drain inward, the divergence of a magnetic field is strictly 0.
Always 0. And here is the ironclad rule of vector calculus that saves the day.
Hit me.
The divergence of a curl is mathematically always 0.
Okay.
Since we know the magnetic field B has 0 divergence, we can boldly state that B must be the curl of some brand new, entirely different vector field.
Enter the vector potential, which physicists just call A.
Exactly, just A.
So let me get this straight. We define the physical magnetic field, B, as just being the whirlpool effect of this completely made-up field, A.
Yes, we invented A to make the math work. But because A is an invention, it comes with a lot of flexibility. The physics notes actually call this flexibility latitude.
So because it's a tool we created, we get to set some of its rules.
Yeah, you can actually add the mathematical gradient of any arbitrary scalar field to your A field, and when you finally take the curl to find the real physical magnetic field, B, that extra junk just vanishes.
It just disappears.
Completely cancels out.
Yeah.
Doesn't change the physical reality of the magnetic field one bit.
You know, it's like defining altitude.
How so?
Well, think about it. Whether you choose to measure a mountain's height starting from sea level, or you decide to measure it from the exact center of the Earth, the physical steepness of that mountain.
The actual slope.
Yeah, the actual rocky slope you have to climb and sweat over is exactly the same. The physics of the mountain hasn't changed. We just choose the baseline that makes the math easiest for us.
That is a perfect analogy. The physical steepness is the magnetic field B. The baseline you choose is the vector potential A.
Right.
And physicists, being brilliantly lazy, chose a baseline that makes the equations incredibly elegant. They arbitrarily decided to set the divergence of A to exactly 0.
Just because we can.
Just because we can. And when you do that, and you plug it into the fundamental equations relating the magnetic field to the electrical current, the terrifying, tangled 3D geometry equations collapse into something beautifully simple.
Wow.
Yeah, instead of a horrific mess of vectors crossing each other, you get an equation mapping how the field changes based on the density of the current.
And here's where it gets really interesting for you listening. In the notes, it shows that this new hacked equation has the exact same mathematical shape as the simple electrostatic equations we already know how to solve.
Yes, it perfectly mirrors the equation relating basic electric voltage to stationary electric charge.
Wait, so what does this all actually mean? To find the incredibly complex twisting magnetic field in 3D space, we don't have to solve a twisting 3D puzzle at all.
Yep.
We just pretend we are solving three completely separate, simple, flat electrostatic problems, like one for the current flowing left to right, one for up and down, and one for back and forth.
That is exactly the trick.
Yeah.
You calculate the x component of this new A field as if the x current were just a static blob of electric charge. Then you do the exact same thing for the y component and the z component.
It's like trying to understand a wildly complex 3D sculpture by just looking at its three flat 2D shadows.
Yes.
You analyze the flat shadows, which is easy math, combine them,
Okay.
and you've mapped the entire invisible vector potential A, then you just calculate the whirlpools of A, and boom, you have your real magnetic field.
It's profound. But, to really grasp it, I think we need to stop looking at the equations on paper and start visualizing what this invisible vector potential actually looks like in physical space.
Right, because right now it just sounds like a math trick. Let's make it real. I want you to picture a uniform magnetic field. Just straight, parallel magnetic field lines pointing straight up towards the ceiling.
Okay, got it.
What does our invented A field look like in this room?
Well, remember the rule, the magnetic field B is the whirlpool of A. So A has to be actively curling to create that straight-up magnetic field.
Right.
If you map it out, the vector potential A is rotating around the central axis of the room. It literally looks like water circling a drain, getting faster and stronger the further you move away from the center.
That's wild.
In fact, if you draw any imaginary hoop in the air, the total amount of A circulating around that hoop is perfectly equal to the total magnetic flux shooting up through the middle of it.
Okay, water circling a drain, I can picture that.
Yeah.
Let's apply this to a real physical object that you might find in a lab. Let's look at the classic long solenoid.
Ah, perfect example.
For you listening, a solenoid is basically just a long, tightly wound coil of wire. Think of a slinky or a spring, and you run an electrical current through the wire.
And we know exactly what happens inside a solenoid. The current looping around and around the coil creates a very strong, uniform magnetic field pointing straight down the hollow center of the tube.
But the textbook rule we all learn in high school physics is about the outside of the coil.
Right.
If the solenoid is infinitely long outside the coil, the magnetic fields completely cancel themselves out. The magnetic field B is perfectly zero everywhere outside.
And this is where we get to the absolute mind bender of this deep dive. Even though the physical magnetic field B is exactly zero outside the solenoid, the vector potential A is not zero outside.
Hold on, I really need to emphasize this because it feels wrong.
It does.
You're telling me that in the space outside the coil, a place where my compass wouldn't even twitch, where there is literally zero magnetic force pushing or pulling on anything, there is still a mathematical field, this vector potential A, circling around out there in the so-called empty vacuum of space.
I am. The math is undeniable.
Mm-hmm.
Because there is magnetic flux trapped inside the hollow center of the coil, the rules of the math dictate that the vector potential must circulate around the outside of the coil to account for it.
Unbelievable.
Its strength slowly drops off the further you get from the coil, but it is undeniably there, swirling silently in the zero-field vacuum.
Okay, so this fake math field is just hanging out in completely empty space where literally nothing is happening. I feel like that's going to come back to haunt us later.
Oh, keep that exact thought in your back pocket. It is going to be crucial.
Okay, noted.
But before we get too deep into the philosophical implications of empty space, let's test our logic against a paradox. The Feynman notes use a brilliant thought experiment to clear up a massive misunderstanding about relativity and electromagnetism.
Oh, the spinning cylinder paradox. I love this one.
It's a great one.
Okay, I want you to picture yourself holding a hollow PVC pipe. We're going to coat the outside of this pipe with a layer of static electric charge. Now we mount it on a wall and spin the cylinder really fast on its central axis.
Now, moving charge is the literal definition of an electrical current. So by spinning this charged cylinder, you've essentially created a surface current wrapping around it.
Right.
And just like the coiled wire of the solenoid we just talked about, this spinning current creates a uniform magnetic field trapped inside the hollow cylinder.
Okay, now for the trap. We take a short, straight piece of wire and we attach it radially inside the cylinder, meaning we attach one end to the center axis and it points straight out to the inner wall.
Like a spoke.
Exactly, like a spoke on a bicycle wheel. And we fasten it so that it rotates with the spinning cylinder.
Okay, so if we connect this to the bigger picture of how electromagnetism works, we know that when a wire moves through a magnetic field, it experiences forces. Specifically, there is a magnetic force that uniquely acts on moving charges, pushing them sideways.
Right, because our little wire spoke is physically sweeping through that internal magnetic field we just generated.
Exactly. This sideways force will physically push the loose electrons along the wire. The center of the wire ends up with one type of charge, and the outer tip near the wall gets the opposite charge.
Wow, okay.
You could actually hook up a microscopic voltmeter to measure this charge separation, and you could use that reading to calculate exactly how fast the cylinder is spinning.
Yeah.
You have successfully built a completely self-contained angular velocity meter.
But wait, here's the relativity trap, and when I read it, it seemed like a totally bulletproof gotcha moment. What if I shrink myself down and I sit on the inner wall of that spinning cylinder?
Okay, so you are now the spinning observer.
Right. From my point of view, sitting on the wall, the cylinder isn't moving, the wire spoke isn't moving, I'm just sitting in a small room.
Because you're moving with it.
Exactly. The whole system is completely at rest from my perspective. To me, it's just a static tube covered in static charge. And standard electrostatics tells us, without a doubt, that there is absolutely no electric field inside a static charge tube.
That is entirely true.
So, if there is no electric field and nothing is moving from my perspective to sweep through a magnetic field, there should be zero force pushing the charges in the wire. My tiny meter should read 0. So who is right? The stationary observer standing in the lab who sees the spinning and measures a voltage, or the spinning observer riding the wall who says everything is completely static and measures absolutely nothing?
This raises an important question, and it's one that trips up a lot of physics students who think they understand Einstein.
I can see why.
The resolution is vital to understand. The stationary lab observer is right. The forces are completely real. The charges will physically build up, and the meter will register a voltage.
Wait, really?
Yes. The spinning observer is simply wrong.
But what does this mean for Einstein's relativity? I thought the whole point of relativity is that all frames of reference are equally valid, that you can't prove who is actually moving.
But that's the misunderstanding. The relativity of motion only applies to constant velocity, cruising in a spaceship at a steady speed in a straight line. There is absolutely no relativity of rotation. A rotating system is fundamentally constantly accelerating because you are constantly changing direction to move in a circle. It is what physicists call a non-inertial frame of reference.
Because you'd feel the centrifugal force pushing you against the wall.
Exactly. And the standard laws of electromagnetism, Maxwell's equations, the calculations we use for the vector potential, strictly only apply to inertial, non-accelerating coordinate systems.
Oh, I see.
When you sat on the spinning cylinder, you tried to use standard non-accelerating physics in a violently accelerating frame of reference.
Yeah.
That's why I gave you the completely wrong answer.
Wow. So you can absolutely measure absolute rotation without ever looking out a window. That is a fantastic trap to avoid. Okay, let's shift gears from spinning cylinders to tiny loops of wire.
This is honestly one of the most elegant symmetries in the entire textbook. We're going to consider a very small rectangular loop of wire with a current flowing around it.
Okay.
And we want to know what its magnetic field looks like from very far away.
So we zoom way out. Imagine looking at this tiny glowing loop from a mile down the road. We calculate our mathematical hack, the vector potential A, for this little loop.
And we find that from far away, the vector potential is simply proportional to the amount of current multiplied by the area of the loop.
Which is an important number.
Very. This product is so important it gets its own name, the magnetic dipole moment.
So a flowing loop of current creates this magnetic dipole moment. But here is the kicker. When you take the curl of A to find the final physical magnetic field B far away from this loop, the equations you get are mathematically identical to the electric field equations for an electric dipole.
Utterly identical.
Yeah.
An electric dipole being just two stationary point charges, one positive, one negative, sitting near each other, like a tiny battery.
It's like looking at two completely different chefs in a kitchen from across a huge field. Chef A is a dynamic, constantly flowing loop of electrical current. Chef B is just two completely stationary charges sitting frozen in place on the counter.
I love this analogy.
They are using completely different recipes, operating under completely different laws of physics, but when you finally taste the cakes they baked from a mile away, they taste exactly the same. The geometric shape of their fields is utterly identical.
And this is crucial to grasp because remember what we said earlier, there are no magnetic charges.
Right.
There's no such thing as an isolated magnetic north pole sitting there like an electron. Yet this dynamic little loop of current mimics a pair of static electric charges flawlessly.
So why? You always help us see the why. Why do totally different physical laws yield the exact same geometrical shape?
It comes down to the strict rules of empty space. Think back to our equations. The electric field's divergence depends on the density of charges. The magnetic field's curl depends on the density of the current. But what happens when you are far, far away from the loop, or far away from the charges?
Well, out there, the space is empty. There are no charges and there are no currents.
Exactly. Out there, the charge density is exactly zero, and the current density is exactly zero. Therefore, far away from the sources, both the divergence and the curl of both fields drop to exactly zero.
Ah, so the fields are forced to obey the exact same geometrical rules.
Yes, the equations of empty space take over. Because both fields have zero divergence and zero curl in that faraway vacuum, the rigid mathematics of empty space dictates that they must adopt the identical shape.
That's beautiful.
The empty space forces the symmetry.
Yeah.
It dictates the geometry.
That is deeply satisfying. But it brings me to a bit of a challenge. Our final hurdle, really.
Yep.
We've spent this entire deep dive obsessing over this mathematical hack, taking a detour through the vector potential A to find our magnetic field. But the source material explicitly offers a totally different way to find the magnetic field directly.
Ah, yes. The law of Biot-Savart.
Yes. It's a direct formula. It's a big integral, sure, but it gives you the magnetic field B directly from the currents in a wire.
It does.
You don't have to invent a fake field. You don't have to calculate A first and then take the curl. You just go straight from current to the real magnetic field.
So, I have to ask the obvious question on everyone's mind.
Let's hear it.
If we have a direct formula to find B, why did we spend all this time going through the middleman? Why do we care so much about A?
It is the perfect question to ask, and if you look closely at the math, there are three very compelling reasons. First, let's look at what the direct formula, the Biot-Savart law, actually demands of you. It requires you to calculate vector cross products inside complex integrals.
Which is an absolute nightmare, right? Can you explain why that's so much worse?
Sure. Imagine trying to calculate a 3D trajectory while the wind is blowing at a right angle to you, but the wind's direction dynamically changes based on your own trajectory.
Okay, my brain hurts already.
Right. It's a 3D geometric nightmare where every vector is pushing at right angles to every other vector. It is notoriously messy and incredibly easy to mess up. Whereas calculating our middleman, the vector potential A, bypasses the cross products entirely. Oh, wow.
It just uses simpler, flat, scalar-style math for each of the three directions independently. It's vastly easier to compute when you are dealing with complex antennas or circuits.
Okay, so reason one, it saves us from a vector calculus headache. What's reason two?
Efficiency. Because we hacked A's math to be identical to basic electrostatics, we can literally recycle centuries of mathematical solutions that physicists have already solved for electric fields and simply copy-paste them onto magnetic problems.
Oh, that's smart.
We don't have to reinvent the wheel every time we design a new magnet.
Work smarter, not harder. I love it. And the third reason?
The third reason is the most profound, and it brings us back to that thought you put in your back pocket earlier.
About the ghost field in empty space.
Exactly. It points to the entire future of physics. In classical everyday circuits, the vector potential, A, might just feel like a clever mathematical convenience, a fake field we made up to avoid cross products. But as you move into advanced theoretical physics, when you study the principle of least action, and especially when you get to the bizarre world of quantum mechanics,
Middleman takes over.
completely. In the quantum realm, the magnetic field B is actually pushed to the side. It turns out that the vector potential A is the truly fundamental physical entity of the universe.
Wow.
The universe itself calculates using A, not B.
Okay, let's summarize this incredible journey we've been on. We started with the twisting, curling puzzle of magnetism, and we learned that the easiest way to solve it is to invent a ghost field, the vector potential A, effectively turning one nasty 3D magnetic nightmare into three simple, flat electrical shadows.
Brilliantly simple.
We debunked a relativity paradox by proving you absolutely can feel absolute rotation because acceleration breaks the rules.
Yeah.
We saw how loops of flowing current perfectly mimic pairs of static charges from afar, all because empty space forces them into the same shape.
Yep.
And we realized that this mathematical hack we invented to avoid hard math might actually be the universe's true language.
It is a fundamental shift from seeing space as just empty geography to seeing it filled with invisible potential. And speaking of that, I want to leave you with one final puzzle to chew on.
Yeah, on us.
Think back to that long coil of wire, the solenoid, that we discussed. We know for a measurable fact that the physical magnetic field, B, is absolutely zero on the outside. A compass sitting there does absolutely nothing.
Right.
Yet we proved through the math that the vector potential A is swirling around out there in that seemingly empty space. Now, if advanced quantum physics tells us that A is the truly fundamental field of the universe, not B,
Wait, I see where you're going with this.
could a tiny quantum particle, like an electron traveling entirely outside the solenoid through a region with absolutely zero magnetic field, somehow still feel the presence of that swirling vector potential?
Wait, so an effect with absolutely no classical cause.
Exactly. Does that invisible mathematical ghost field have real, measurable physical consequences on a particle that never once touches a magnetic field?
That is insane to think about.
It is, isn't it?
Let that bend your mind a little next time you drop your phone onto a wireless charging pad, because that simple elevation map of the universe is a whole lot weirder and a whole lot more haunted than it looks. Thank you for taking this deep dive with us.
Have you ever learned a rule that seemed absolute, like a fundamental truth of the universe, only to find out later it was just, the training wheels version of a much wilder reality?
Oh, absolutely. I mean, think back to when you first learned math and the teacher told you that you simply cannot subtract a larger number from a smaller one.
Right. It was just an impossible thing to do.
Exactly. And then years later, someone introduces the concept of negative numbers. And you suddenly realize the world you were operating in was just this perfectly curated sandbox.
Yeah, the sandbox is a great way to put it, which is, a necessary simplification. If we started day one with the unvarnished complexity of how things actually work, it would be completely paralyzing.
Oh, for sure. But eventually, those simplifications kind of hide the actual mechanics of the universe.
And that transition moving from the sandbox to the deeper reality is the exact journey we're taking you on in today's deep dive.
I'm really excited for this one.
Me too. We're exploring Chapter 15 of Volume 2 from the legendary Feynman Lectures on Physics. And our sources map out this massive paradigm shift.
The huge shift.
We're going to start with the basic mechanical forces on a simple loop of wire and follow that thread all the way to a quantum experiment that forced the whole physics community to completely reevaluate what is mathematically real.
Right, because the core of this deep dive is a profound mystery about the tools we use to describe the world. When physicists rely on a mathematical construct to solve a problem, how do they know if it's just a clever bookkeeping trick?
Like a shortcut to make the calculus easier.
Exactly. Is it just a shortcut, or is that math pointing to a hidden physical layer of the universe that we just couldn't perceive before?
It's so fascinating. So we'll decode the vector potential, we'll uncover a hidden energy accounting error, and explore how a microscopic crystal of iron exposed a 30-year blind spot in science.
It's quite the story.
To set the stage, let's look at the classic scenario Feynman presents. Picture a rectangular loop of wire with a current running through it, sitting inside a uniform magnetic field.
Right. So if you're visualizing this, imagine a square wire frame positioned right between the north and south poles of a large magnet.
Okay, I got it.
Because the current travels in opposite directions on opposite sides of this loop, the magnetic forces on those sides pull in opposite directions too.
So they cancel out.
The translation cancels out, yeah. The whole loop doesn't get pulled left or right. But the forces do create a twist. One side is pushed down, the other is pushed up, creating a torque.
Like turning a steering wheel.
Exactly like a steering wheel.
Yeah.
The loop wants to rotate until its magnetic moment aligns perfectly with the external field.
Yeah.
Because that's its lowest energy state.
Okay, so the text gives us this elegant little equation for the mechanical energy of the system. It basically states the mechanical energy is the negative dot product of the magnetic moment and the magnetic field. And for anyone calculating the physical torque, the actual force twisting that wire, this equation works flawlessly. But then Feynman immediately drops his massive caveat.
He does. He just casually reveals that the energy we just calculated is fake.
Right, a fake energy, which, let's unpack this, demands an explanation. If a formula gives you the exact measurable physical force twisting the wire, calling the energy fake seems entirely backwards.
It sounds totally counterintuitive.
Why put quotation marks around the word energy there?
Because it completely ignores the total energy of the world. I mean, the formula relies on a microscopic view that pretends the rest of the universe just doesn't exist.
How so?
Well, physicists use a principle called virtual work to calculate these forces. You imagine letting the loop rotate just an infinitesimal amount, and you calculate the change in mechanical energy to find the force.
Okay, that makes sense mathematically.
It does, but doing this assumes a huge constraint.
Mm-hmm.
It assumes the electrical current flowing through the loop magically stays perfectly constant while the loop moves.
Okay, wait, let me try an analogy here to contextualize this. It sounds like calculating the cost of a long road trip by only adding up the toll booths you pass.
Oh, that's good.
Right. But you're deliberately omitting the cost of the gas your engine is burning to actually get you between those booths.
That captures the accounting error perfectly. The mechanical work, that torque twisting the loop, represents the toll booths. But we have to look at the gas.
What's the gas in this scenario?
It's the rest of the physical system. When you force that wire loop to move through the magnetic field, the field interacts with the conduction electrons flowing inside the wire. It exerts a force on those moving charges, effectively doing electrical work on them.
Oh, and according to Faraday's law of induction, moving a wire through a magnetic field induces a voltage that opposes the change.
Exactly.
So the current should naturally drop.
Precisely the issue. The current would drop. But our initial calculation for mechanical energy demanded that the current remain absolutely constant.
Right.
So for the current to stay constant while the magnetic field pushes against the electrons, a battery, or whatever power supply is driving the loop, must step in.
Has to work harder.
Exactly. The power supply has to actively deliver or absorb energy to fight that magnetic push and maintain that steady flow of electrons.
So our simple equation completely ignores the battery sweating in the background. It only accounts for the mechanical torque and acts like the power source isn't even part of the system.
Feynman proves the scale of this omission by looking at the total energy balance sheet using a relativity argument.
Oh, this part blew my mind.
It's so elegant. Imagine moving your wire loop toward a stationary coil that's generating the magnetic field. In this perspective, the mechanical work done is perfectly balanced by the electrical work done on the loop.
Okay, straightforward enough.
Now switch the perspective. Keep your loop stationary and move the field-generating coil toward the loop.
Right, because the physics has to hold up regardless of which object we define as the one moving.
Exactly. In the second scenario, electrical work is being done on the coil. When you step back and calculate the entire system, the electrical energy of the loop, the electrical energy of the coil, and the mechanical energy, the math reveals something really striking.
What happened?
The total energy of the whole system is the exact opposite of the mechanical energy alone. If the mechanical energy is negative, the true total energy of the system is positive by the exact same magnitude.
Wow. So the gas from our analogy costs twice as much as the toll booths.
Exactly.
And by only looking at the mechanical equation, we were operating in a mathematical fantasy. The true energy is the total inverse of what the simplified rule suggested.
It serves as a really stark warning. I mean, an artificial calculation can give you the right answer for a highly specific local question, like the force turning the wire, while completely misrepresenting the true holistic reality of the system.
Right. And if calculating the true energy of a simple rectangle uncovers all these hidden complexities, applying this to messy real-world circuits becomes practically impossible.
Right. Oh, an absolute nightmare. Calculating energy with just magnetic fields or B fields gets incredibly messy, so physicists needed a workaround.
And that introduces a new mathematical tool to make sense of steady currents, the vector potential, denoted by the letter A.
Yes, the A field. To find the total energy of a large, weirdly shaped circuit, physicists imagine the circuit as a grid made up of millions of tiny microscopic current loops.
Like a mesh.
Like a mesh, exactly. They use a principle from advanced calculus called Stokes' theorem. It essentially provides a way to translate the magnetic field piercing through a surface into a flow around the boundary of that surface.
Okay, so it shifts the perspective.
Right. Through this math, the B field is transformed. You arrive at an equation where the total energy of the system is linked directly to this new construct, the vector potential, A. The magnetic field B is then defined simply as the curl of A.
Which brings us to the most crucial philosophical debate in the text. Is this vector potential, this A, a real field?
That is the million-dollar question.
Let's look at the case against it first, because honestly, it looks pretty bad. First, we can't feel it. We don't have instruments that measure A directly. We only ever measure the resulting B field.
Right, it's invisible to our instruments.
Second, it is mathematically squishy. The text explains gauge invariance, meaning you can alter the A field by adding the gradient of any scalar function, and the underlying physics don't change at all.
The forces on a particle remain identical, yeah.
It feels like redefining the baseline for sea level. It changes the coordinate numbers, but the actual physical mountain you have to climb is exactly the same.
That's a perfect way to put it. And add to that the fact that computing A is sometimes vastly more complicated than just computing B directly.
Really, even though it's supposed to be a shortcut.
Yeah, Feynman points out that for a simple ring of steady current, finding the vector potential requires elliptic integrals, really complex mathematical functions that don't have simple closed-form solutions. So you have a tool that is mathematically ambiguous, unmeasurable by classical instruments, and often a total nightmare to compute.
It's easy to see why classical physicists viewed it merely as a handy mathematical stepping stone. You just endure the annoying math of A to eventually drive the magnetic field B.
Because B is what actually pushes charged particles around. To them, B was the true reality.
Right. But to resolve this, Feynman establishes a rigorous definition of what makes a field real.
He does. He defines a real physical field as a set of numbers at a specific point in space that completely determines what happens to a particle at that exact point.
So no outside context needed.
Right, without needing any information about what is happening anywhere else in the universe.
It effectively outlaws the concept of action at a distance. If a field is real, a particle only interacts with the microscopic space it occupies. It doesn't, like, magically sense a magnet sitting on the other side of the room.
Exactly. It only responds to the field values at its specific coordinate. And classically, the magnetic field B fits that definition perfectly. If an electron travels through a vacuum and the B field at its location is 0, the classical rules state it experiences 0 magnetic force. Its path remains unchanged. No local B field, no physical effect. End of story.
So if we are testing the reality of the vector potential A, we need a scenario where we can separate the two. We need a situation where the B field is completely 0, but the A field is not.
Yes, because if A is just a math trick, nothing should happen. But if A is physically real, it should affect the particle.
And this is where the text introduces the quantum shock, the Aharonov-Bohm effect, where quantum mechanics just shatters the classical worldview.
It really does. So you're likely familiar with the baseline two-slit electron experiment.
Right, where electrons act as waves, pass through two slits, and create an interference pattern like a barcode of bright and dark bands on a screen.
Exactly. The twist comes when we introduce a microscopic, infinitely long solenoid right between the two slits.
Okay, so we run a current through this solenoid. Inside a perfect, infinitely long solenoid, a strong B field exists. But the mathematics dictate that outside the solenoid, the B field is absolutely 0.
Not just weak, but perfectly 0.
And the electrons are traveling outside the solenoid. They pass on either side of it to get through the slits. They never cross into the interior.
Right, they never encounter the B field at all. So classically, the electrons shouldn't even register that the solenoid is turned on.
Wait, but the vector potential A does exist outside the solenoid. It circulates around the exterior space where the B field is dead 0.
Yes.
If the electrons never touch a magnetic force field, what exactly is physically interacting with them to change their path? Isn't that literal magic?
It seems like it to a classical physicist. This is the huge blind spot of classical mechanics, the assumption that a force must mechanically push a particle.
But quantum mechanics is different.
Very different. It operates on probability amplitudes and the phase of the electron's wave. The fundamental quantum law dictates that an electron's phase is shifted by the path integral of the vector potential A.
So as the wave travels through the A field, the field alters its phase directly.
Exactly.
But explain how that phase shift physically manifests. I mean, how does a change in the wave's phase translate to a physical change on the detector screen?
Well, when the electron wave splits and goes around both sides of the solenoid, the A field affects each path differently. One path's phase is advanced while the other's is delayed.
Okay, I'm visualizing the waves.
Right, and the interference pattern on the wall relies on where the peaks and troughs of those waves meet. Because the phases have been shifted, the location where the peaks perfectly align, those bright bands of the barcode, physically moves to a different angle on the wall.
Oh, wow. So the entire interference pattern shifts.
It shifts.
Even though the classical B field was 0 along the electron's entire journey, their final physical destination was altered by the A field.
Yes. And this wasn't just some abstract thought experiment.
Here's where it gets really interesting.
Yeah, the text outlines how experimental physicists proved this reality. But pulling this off requires absurd precision because electron wavelengths are incredibly small.
Right, and you need a solenoid thin enough to actually fit between the two slits.
Exactly. So researchers used microscopic magnetized iron crystals called whiskers.
Iron whiskers. I love that.
Yeah, these iron whiskers act like ideal solenoids, strong magnetic field inside, practically zero outside.
And when they directed the electron beams around these magnetized iron whiskers, the pattern on the screen shifted precisely according to the quantum equations governing the A field.
Which completely satisfies Feynman's definition. The electrons interacted with the local environment they were passing through. Since the local B field was zero, the entity they interacted with was the vector potential A.
So it proves definitively that A is a real physical field.
It's physically real.
And the historical context provided here is just staggering. Feynman points out that this mathematical relationship, the fact that A governs the quantum wave phase, was embedded in the Schrödinger equation back in 1926.
It was sitting right there from the very inception of quantum mechanics.
But people ignored it.
Well, human psychology is a powerful deterrent, even in physics. The scientific community was so entrenched in the classical mindset, so committed to the dogma, that only the B field and the E field were tangible entities.
That they effectively ignored the implications of their own math.
Yeah. It took 30 years before two physicists, David Bohm and Yakir Aharonov, formally highlighted this in 1956. They stated unequivocally that the vector potential is physically real.
And it sent shockwaves through the physics community.
Oh, absolutely. It's a brilliant example of how fundamental truth can hide in plain sight, obscured by the assumptions we bring to the chalkboard.
Right. But Feynman doesn't let us rest there, does he?
Not at all.
Just as we accept this mind-blowing reality about A, he forces us to confront another artificial simplification. He points out that everything learned in the course so far, all the beautiful static equations we've been relying on, are built on an assumption that fields don't change.
Yeah, the training wheels come completely off in Table 15.1, where he compares statics to electrodynamics. The moment time varies, the old rules fracture.
Take Coulomb's law, the foundation for calculating electric forces between stationary charges. In a dynamic, time-varying universe, Coulomb's law fails.
It's just false in general.
He also targets the rule about solid conductors. We are taught that there is no electric field inside a solid conductor because free charges instantly rearrange themselves to cancel it out.
That is also false when fields vary with time. The free charges attempt to rearrange, but they cannot do it instantaneously.
Because nothing is instant.
Right. They are constantly chasing the changing field, generating currents in the process, so a conductor is no longer a perfect equipotential surface. Furthermore, Faraday's law shows that a changing magnetic field creates an electric field. Electric fields are no longer strictly conservative, which is why calculating a simple scalar voltage is no longer enough to describe the system.
Okay, wait. If all the basic rules of statics are collapsing, what actually survives the transition to electrodynamics? What can we still trust?
The foundational pillars hold firm. The Lorentz force equation, which dictates the force on a charge moving through electric and magnetic fields, that remains universally true.
Okay, yeah.
Gauss's law remains true. The physical reality that there are no magnetic monopoles remains true, but the equations governing how these fields propagate across space require a massive upgrade.
And this upgrade centers on the ultimate speed limit of the universe, the speed of light, see?
Exactly. This introduces the concept of retarded potentials.
Retarded potentials. What does that mean in this context?
Well, in the static simplified version of physics, if you wiggle an electron here on Earth, the mathematical equations assume the resulting field updates everywhere in the universe instantaneously.
Right, like pulling a taut string.
But reality is constrained by the speed of light. Nothing propagates instantly.
So if you are trying to calculate the electric or vector potential at a specific point in space, you cannot plug in the state of the surrounding currents and charges as they exist in this exact moment.
Because the news of what those charges are doing right now hasn't actually reached your location yet. It literally takes time for the electromagnetic influence to cross the distance.
Oh, think of it like a live television broadcast from the other side of the planet. Or, better yet, trying to communicate with a rover on Mars.
That's a perfect analogy.
If the rover encounters a problem and transmits an alert, the engineers on Earth don't receive it instantly. There's a multi-minute delay. The data they're looking at on their screens is a ghost of what happened minutes ago.
The exact same delay applies to the microscopic wires and batteries on your desk.
Really?
Yeah.
Even at that small scale?
Yes. When an electron is pushed by a magnetic field, it isn't reacting to where the surrounding charges are right now. It is reacting to where they were at a very specific point in the past.
Wow.
To make the math match reality, you have to evaluate the sources at the retarded time. You take the current time and subtract the distance divided by the speed of light.
T minus R over C. So the formula dynamically adjusts based on the distance between the source and the observer.
Exactly. The equations for the potentials look remarkably similar to the static versions, but instead of integrating over the current state of the universe, you integrate over this delayed, retarded time state.
It is an incredibly elegant substitution. It basically single-handedly bridges the gap between static approximations and the dynamic, breathing reality of electrodynamics.
It ensures that cause always precedes effect, fully constrained by the physical limits of space-time.
Looking back at the scope of Chapter 15, we have untangled some massive conceptual knots today. We began with the deceptively simple wire loop, uncovering the hidden battery energy that proved mechanical formulas can totally mask the true accounting of a system.
We really did. And then we explored the vector potential, A. We debated its reality, looking at its squishy math and arbitrary gauges, before the Aharonov-Bohm effect demonstrated that an invisible field can physically alter quantum interference patterns.
Even when the classical magnetic force is entirely absent.
Exactly.
And finally, we confronted the limits of statics. We learned that the moment fields begin to change, instantaneous formulas fail. We have to incorporate retarded potentials, acknowledging that every electromagnetic interaction is an echo from the past, rippling outward at the speed of light.
It fundamentally shifts how you look at the physical space around you.
It really does.
And, it highlights a persistent vulnerability in how we understand science. The vector potential was a term in an equation that brilliant minds ignored for 3 decades because their classical prejudices dictated how the universe should operate.
They dismissed the math as a bookkeeping trick until a physical experiment proved it was steering the quantum world.
Right. Which leaves you with a really lingering question to ponder.
Yeah.
If a mathematical quirk like the vector potential was ignored for 30 years before we realized it was a physical reality, what other invisible mathematical tools in today's science are actually hidden gears of the universe?
Oh, that is a great question. What anomalies in today's theories are we just dismissing as abstract calculus?
Exactly. There are likely profound realities sitting right in front of us, in equations researchers use every single day, just waiting for the right experiment to expose them. The simple fact that you can just listen to this audio right now or, walk into a completely dark room and just flip a switch to flood it with light.
Right, we didn't even think about it.
Yeah, exactly. It feels completely normal. It's just the backdrop of our entire lives. But if you really strip it down, if you look at the bare mechanics, it's actually incredibly strange.
It's totally bizarre.
Right. Like everything we do, the entire infrastructure of the modern world, it all relies on this invisible, almost magical relationship between just like pieces of copper, pieces of iron, and physical motion.
It really is the closest thing to actual magic that human beings have ever engineered.
Yeah.
I mean, you take a river, right? You force that water to push a massive piece of metal past a magnet, and suddenly...
Hundreds of miles away.
Exactly. Hundreds of miles away across a desert, a screen lights up or, a speaker vibrates. We just accept it. But the chain of events making it happen is mind-bending.
And today, we are going to figure out how that trick actually works. So let's unpack this. Our mission for this deep dive is to demystify these invisible forces that literally run your life.
Yeah, we're diving straight into Chapter 16 of our source text today.
Right, Chapter 16, which is all about induced currents. And we're going to trace how a few quirky, almost accidental physics experiments from the 1800s, the kind that baffled the greatest minds of the time.
But really weird parlor tricks.
Yeah. How those evolved into the massive continent-spanning electrical grid that powers human civilization today.
Because to really understand the modern world, we kind of have to rewind to a time when electricity and magnetism were considered completely, fundamentally separate things.
Like 2 different silos of science.
Totally. Before 1820, electricity was essentially just sparks and static. You could store a static charge in a glass jar, you could shock someone, and, well, that was about it.
A neat party trick.
Right. And magnetism, on the other hand, was just compass needles pointing north. But then, a Danish physicist named Hans Christian Ørsted noticed something weird during a lecture.
Just by accident, right?
Completely by accident. He had a compass sitting near a wire, and when he sent a battery current through that wire, the compass needle twitched.
Which shatters everything they thought they knew. An electric current flowing through a wire actually creates a magnetic field.
And conversely, a wire carrying a current will experience a physical force if you place it inside a magnetic field. This was basically the birth of electromagnetism, the realization that these two forces were just sides of the same coin.
Which naturally leads to the ultimate engineering question, right? If electricity mixed with a magnet creates a physical pushing force, can we harness that push to build an engine?
And that was the immediate next step. If you look at the first diagram in our source text, chapter 16, it shows the bare bones of a simple electromagnetic motor.
Okay, picture this.
Yeah, picture you take a permanent magnet, so a north pole and a south pole with a gap between them. Now you place a rectangular loop of copper wire right in that gap.
Because the wire is a loop, right, when you send a current through it from a battery, the electricity flows away from you on the left side of the loop and then comes back toward you on the right side.
Exactly. So because the current is traveling in opposite directions on each side, the magnetic field pushes one side of the wire loop up and forces the other side down.
So opposite forces on opposite sides, that creates torque.
Right. The copper coil twists.
Yeah.
And if you mount that coil on a central shaft, that twist becomes rotation. Hook that rotating shaft to gears or pulleys, and suddenly, boom, electrical energy from a chemical battery is doing physical mechanical work.
It's wild. But it's worth noting that initially the scientific community didn't use this to build massive factories. They actually used it to build highly sensitive measuring tools called galvanometers.
Yeah, because if you use a very fine, delicate wire
And attach a tiny mirror to it, exactly.
right, to track the rotation, then even the absolute faintest, weakest electrical current will make the coil twist slightly.
And that sensitivity led to one of the greatest accidental inventions in history, which I love. Two scientists in Germany, Gauss and Weber, this is around 1833, they had built one of these galvanometers, and they were so amazed by how electricity moved that they just decided to test its limits.
They literally strung copper wire over the rooftops across the entire city of Göttingen.
Just strung it right over the houses. Gauss hooked up a battery at his lab at one end of the town, and Weber watched the tiny mirror on the galvanometer twist at the observatory on the other side of town.
They were basically just playing around, trying to see if the magnetic push would decay over a long distance.
And they accidentally invented the telegraph.
It's amazing.
They realized they could send pulses of movement across a city instantaneously.
It's such a brilliant example of curiosity driving innovation. But, it also highlights a common misunderstanding about how electricity actually travels. Like, why did that signal travel so fast across a whole city?
Right, because it's not like a single electron sprinted from Gauss's battery all the way over the rooftops to Weber's observatory in like a fraction of a second.
No, not at all. The electrons themselves actually drift quite slowly.
I always try to picture electrons moving in a wire, like a really, really long line of train cars sitting bumper to bumper on a track.
Oh, that's a good analogy.
Yeah, so if you push the very first train car, it instantly bumps the second, which bumps the third, and that mechanical force travels down the entire line at the speed of sound through the steel, pushing the very last car almost immediately.
Right. The individual train cars may be moved an inch, but the actual push traveled miles instantly.
Exactly.
The electrons repel each other, so the wave of electromagnetic force travels at a significant fraction of the speed of light, even if the electrons themselves are just crawling. But here is where the scientific story hits a massive brick wall.
The search for symmetry.
Yes. Once the scientific community knew that electricity could create magnetic fields and physical motion, they naturally assumed the universe would allow the reverse.
A magnet should be able to create an electric current.
Right. It was a completely logical assumption.
So,
Likes prefer to move alike was the general thinking. So scientists took massive, heavy magnets, placed them right next to coils of wire, hooked up those ultra-sensitive galvanometers, and
nothing.
absolutely nothing. Not a single spark.
Our sources say they even tried putting two separate wires right next to each other, running a heavy current through one, hoping its magnetic field would kind of drag the resting electrons through the second wire.
And still, just nothing. Until Michael Faraday broke the deadlock in the 1830s. Faraday realized the secret ingredient everyone was missing.
And the secret wasn't the strength of the magnet.
No, and it wasn't proximity either.
Yeah?
The secret was change.
Okay, change. Let's break down what that actually means in this context.
So if a magnet just sits stationary next to a wire, nothing happens. The universe doesn't give away free energy just because a magnet is nearby. But Faraday discovered that if you physically move the wire past the magnet,
Or you take the magnet and move it past the wire?
exactly, suddenly the galvanometer jumps.
Yeah.
Or if you have two separate coils of wire sitting next to each other and you suddenly turn the battery current on or off in the first one, that sudden change induces a current in the second one.
Because it's suddenly shifting.
Right. Faraday proved that electrical effects are only induced when the magnetic environment is actively changing.
Wait, okay, I'm trying to map this back to our earlier thought experiment. If moving a magnet past a wire creates an electric current, what happens if I take that simple motor we built earlier, the copper loop on a shaft sitting between two magnets, but instead of feeding it power from a battery to make it spin, I just grab the shaft with my hand and forcefully spin it myself?
You have just built a generator.
Yeah. So the motor and the generator, they aren't two different inventions.
No, they are the exact same machine, just run in reverse.
That is wild.
They are the identical piece of hardware. And this is just a beautiful, profound demonstration of the conservation of energy. If you pump electricity in, you get physical motion out. If you pump physical motion in, you get electricity out. It all comes down to what Faraday called the flux rule.
Magnetic flux. I feel like this is one of those terms that sounds incredibly intimidating, but is actually a very physical, relatable concept once you visualize it.
Yeah, think of magnetic flux as the total amount of magnetic field passing through the open area of your wire loop.
Yeah.
Imagine you are holding a hula hoop outside in a rainstorm.
Okay, I've got my hula hoop.
If you hold the hoop perfectly flat, parallel to the ground, a maximum amount of rain falls through the hole.
Right.
But if you tilt the hoop upright, so it's perpendicular to the ground, the rain just falls past the thin edges. No rain actually goes through the hole.
So when I manually rotate that copper coil inside the magnetic field, the amount of magnetic rain, the flux passing through the loop, is constantly changing.
Exactly. First it's catching all the flux, then it's sideways catching none, then it's upside down catching the flux in the opposite direction.
You hit the nail on the head. So the flux rule states that the electromotive force, the EMF, which is literally the voltage pushing the electrons through the wire, is determined entirely by the rate of change of that magnetic flux.
Yes. The faster you spin the crank, the faster the flux changes, and the higher the voltage you generate.
And because the loop keeps flipping over and over as it spins, the electrons get pushed one way, then the other way, then back again.
Which is the exact origin of alternating current, or AC power.
Oh.
The current literally alternates direction because the loop is rotating through the magnetic field. And once you understand this two-way street of motors and generators, you start to see it everywhere. Like a fantastic real-world application of this from our sources is Alexander Graham Bell's original telephone.
Right, because I always assumed the telephone was just like sending actual physical vibrations down a pipe, kind of like a string between two tin cans, but it's actually way more sophisticated than that.
Oh, way more. A telephone receiver is essentially a tiny voice-powered electrical generator.
Voice-powered.
Yeah. Inside the handset, you have a small permanent magnet, a tiny coil of wire wrapped around it, and a very thin, flexible iron diaphragm sitting just fractions of an inch away.
So when I speak into it, the air pressure from my voice, the actual sound waves physically push and pull on that flexible iron disc.
Yes. And because iron heavily influences magnetic fields, when that diaphragm wiggles back and forth, it constantly changes the shape and intensity of the magnetic flux passing through that little coil of wire.
Okay, my mind is slightly blown here. So the telephone wire isn't carrying sound at all.
Nope.
It's carrying a topographical map of magnetic change created by my voice.
That is a gorgeous way to describe it. Your voice creates a rapidly changing magnetic flux, which induces a varying electrical current in the wire that perfectly mimics the frequency and amplitude of your sound waves.
That's nuts.
And then that electrical current travels miles down a wire to another identical handset. When that varying current hits the second coil, it changes the magnetic pull on its iron diaphragm, causing it to vibrate and recreate your voice.
So with just a little bit of iron and copper, you translate physical sound into invisible magnetic change, shoot it across a continent, and translate it back.
Exactly.
Okay, here's where we need to take a step deeper. We've established that physical motion, turning a crank, vibrating an iron disc with sound waves that changes the flux and creates a current. But what if nothing physically moves at all?
Oh, this is the good stuff.
Right. Can we create this change entirely invisibly?
This brings us to the transformer, which is purely about harnessing the magic of changing currents. Imagine two separate coils of wire, We'll call them coil A and coil B. They are wrapped around heavy bundles of iron to help guide the magnetic field, but the wires of coil A and the wires of coil B never physically touch.
Like, at all. There is no direct electrical connection whatsoever.
Completely isolated from each other. Now, you hook coil A up to an AC generator. Because it's alternating current, the electricity is constantly ramping up, reversing direction, and ramping down 60 times a second.
60 times a second. So this means the magnetic field created by coil A is actively growing, collapsing, and reversing over and over again.
Yes. And because that magnetic field is constantly swelling and collapsing, it's washing over coil B. It's essentially bathing coil B in a constantly changing magnetic flux.
Which, as Faraday taught us, induces a current in coil B.
Exactly. You can literally wire a light bulb to coil B, and it will light up, drawing heavy power entirely through the invisible changing magnetic field crossing the gap between the coils.
That is just, it's like ghost electricity.
Right. And the true genius of the transformer is that you can use it to manipulate the voltage. If coil B has twice as many turns of wire wrapped around the iron as coil A, it will output twice the voltage. Because every single individual loop of wire gets its own independent push from the changing flux, and all those pushes just add up.
Hold on, I'm trying to visualize this changing magnetic field. If coil A is creating this massive, constantly fluctuating magnetic field that radiates out and induces a current in coil B, doesn't that changing field also wash over coil A itself? Like, does it interfere with its own current?
That is a phenomenal question, and the answer is yes. It absolutely does.
Really?
Yeah, this introduces a crucial concept called self-inductance, and it's governed by something called Lenz's rule.
Lenz's rule.
Right. So while Faraday's rule tells us how much voltage is created by a changing flux, Lenz's rule tells us the direction of the induced current. The rule is, well, it's brilliantly stubborn. An induced current will always try to oppose the change in flux that created it.
Oppose the change. It sounds like a Chinese finger trap. Like, the harder you pull to try and change the state of the trap, the harder the system restricts and fights back against you.
Oh, the Chinese finger trap is a brilliant analogy. It's essentially the electrical version of inertia. Nature abhors a change in magnetic flux.
So it fights it.
Yes. When you first turn on the current in a massive coil, the magnetic field starts to build. The coil itself feels that changing flux and immediately induces a back EMF, a backward voltage, that tries to fight your current. It's trying to keep the net current at zero.
So it takes physical time for the current to overcome this fight and actually build up.
Exactly.
So the coil fights you when you try to start it, but what happens when you try to stop it?
And that's where it gets really dangerous. Once a strong current is flowing and a massive magnetic field is established, if you try to suddenly turn it off, the coil fights you again.
It wants to maintain the status quo.
Right. It tries to keep the current flowing.
Because turning off the switch means the magnetic field collapses instantly, which is a massive rate of change in flux.
Exactly. The coil violently opposes this rapid change, generating a massive, incredibly dangerous surge of back EMF to try and force the current to keep moving. The voltage spikes so intensely that the electricity will literally tear through the air, bursting across the open switch like a lightning bolt.
It's just the universe desperately trying to stop the magnetic field from changing. But that lightning arc could easily destroy the machinery or, electrocute the engineer pulling the switch.
Which is why engineers can't just install normal light switches on massive industrial electromagnets. They have to carefully wire in bypass lamps or specialized bleed-off circuits.
Oh, so the energy has somewhere to go.
Right.
Yeah.
When you cut the main power, the circuit redirects that collapsing magnetic energy into the lamps, giving it a safe place to slowly burn off as heat and light, rather than just arcing across the room.
That is wild, and it transitions us perfectly into the physical world because Lenz's rule, this idea that induced currents always fight back like a finger trap, it isn't just an invisible electrical concept. It creates incredibly powerful, visible physical forces.
Oh yeah, you're thinking of the classic physics demonstration.
The flying aluminum ring. Picture a powerful electromagnet, basically an iron core wrapped in wire, pointing straight up at the ceiling. You take a solid, unconnected aluminum ring, like a thick metal donut, and you just rest it casually on top of the electromagnet.
Okay.
Then you flip the switch to send high voltage alternating current into the magnet, and the moment you do, the heavy aluminum ring violently leaps up into the air.
And if we apply Lenz's rule, we know exactly why it leaps. The electromagnet is blasting a rapidly changing magnetic field up through the center of the ring.
And the ring, following the laws of physics, wants to oppose that change.
So it induces a massive circular current inside itself.
And because an electric current creates a magnetic field, the ring essentially turns itself into a reverse electromagnet.
Precisely. If the base magnet is pushing a north pole up, the induced current in the ring creates a north pole pointing down to fight it. North pole meets north pole, and the ring physically repels itself, launching into the air.
It's basically pushing off the invisible field.
Yeah, these isolated currents swirling around inside solid pieces of metal are called eddy currents. Now, if you want to see the absolute extreme version of this phenomenon, we have to look at perfect conductors.
Superconductors, the materials that have absolutely zero electrical resistance when you freeze them. Our sources mention cooling tin down below 3.8 degrees Kelvin.
Right. In a normal metal like aluminum or copper, electrical resistance eventually slows the eddy currents down. But a superconductor has zero resistance.
Meaning?
That means the absolute slightest change in magnetic flux will generate an infinite eddy current to fight it, which means a superconductor is a flawless, perfect magnetic shield. It will not allow a single line of magnetic flux to pass through it, ever.
Wait, so if you bring a standard bar magnet near a supercooled bowl made of tin?
The perfect eddy currents in the bowl will instantly create an exact, flawless, opposing magnetic field. The bar magnet will literally levitate in midair above the bowl,
Just floating there.
supported permanently by invisible magnetic repulsion that's locked in space.
Okay, levitating magnets over supercooled bowls is phenomenal. But I want to bring this back to normal metals that we interact with every day. Metals with normal resistance, like just a sheet of copper, they can't levitate permanently?
No, because the normal resistance in the copper causes those eddy currents to quickly die out, dissipating their energy as heat. But they still fight back aggressively while they are actively moving through a field.
Right.
The classic demonstration of this is the copper pendulum experiment.
I was hoping we'd get to this. It's such a visceral description in the text. Imagine a heavy, solid, square sheet of copper suspended on a rod, swinging back and forth like a grandfather clock pendulum.
Okay, so it's swinging.
And at the absolute bottom of its swing, it passes between the narrow poles of an incredibly strong electromagnet.
Right, so if the magnet is turned off, the copper plate swings freely, back and forth, completely unimpeded.
It's just normal gravity.
But if you turn the electromagnet on and then drop the pendulum from the top of its arc, it doesn't bounce off the magnetic field like a brick wall.
Yeah.
But it doesn't swing through cleanly either.
The sources describe it as if the solid copper suddenly hits a vat of incredibly thick honey.
Yeah.
It just sinks slowly, smoothly downward through the air. Why does it feel viscous like that?
Because as the solid copper plate enters the heavy magnetic field, huge eddy currents swirl inside the metal, creating a magnetic drag that aggressively opposes the forward motion.
It's fighting the swing.
Exactly. It is forcefully converting the physical kinetic energy of the swinging pendulum into electrical energy, which then immediately burns off as heat due to the copper's natural resistance. It is flawless, frictionless magnetic braking.
But the sources also highlight a brilliant engineering trick to fix this. If you take that exact same copper plate, but you take a saw and cut narrow vertical slots into it.
So the bottom looks like the teeth of a comb.
Right. It swings right through the heavy magnetic field with almost zero drag. Why does cutting slots turn off the honey effect? Like, did we just remove too much metal?
No, it has nothing to do with the amount of metal removed. It's entirely about geometry. You are physically restricting where the eddy currents can flow.
Oh, because of the cuts.
Right. By cutting slots, you prevent massive, wide loops of current from forming across the whole plate. The electrical loops are forced to be tiny, restricted to the individual narrow strips of copper between the slots.
And smaller loops mean?
Drastically less magnetic flux can pass through each loop, which means less opposing voltage is generated, and the resistance of the narrow path is much higher. The eddy currents are literally choked out, so the magnetic braking force almost entirely vanishes.
It's incredible how much physical, mechanical control you can exert over these invisible forces just by, changing the shape of a piece of metal.
Totally.
Which brings us to the grand finale of our deep dive. Because all of these quirky effects we've talked about, magnets pushing wires, induction, transformers, eddy currents, magnetic drag, these aren't just laboratory parlor tricks.
No, not at all.
They are the exact principles that were scaled up to power human civilization.
Yeah, and it's worth remembering that when Michael Faraday first discovered induction, when he noticed that tiny twitch of a galvanometer caused by moving a magnet, politicians and critics asked him, what is the practical use of this?
And he famously replied,
what is the use of a newborn baby?
I love that quote. And look what that baby grew up to be.
It grew up to be the global electrical grid. Engineers took these exact principles and scaled them to unimaginable heights.
Like the three-phase AC power mentioned in the text.
Right. By arranging 3 separate coils in a circle and sending slightly delayed alternating currents through each one, engineers can create a massive magnetic field that smoothly rotates in a circle, continuously, without any physical parts actually moving.
Wait, a rotating invisible magnetic field? So if I just take a metal ring and drop it inside that field, the magnetic track, the thick honey effect we just talked about, would grab the ring and force it to spin.
You've just described the induction motor, the backbone of modern industry.
Yeah.
The magnetic field rotates, the eddy currents fight the change, and the rotor is dragged along for the ride.
That's genius.
And an even more clever simplified version of this from the text is the shaded pole motor. You take a standard alternating electromagnet, but you cover exactly 1/2 of the iron pole with a simple, flat aluminum plate.
Let me stop you there. If you cover half the magnet with aluminum, wouldn't the magnetic field just go around the covered part?
It doesn't go around it, it gets delayed by it.
Oh.
The aluminum plate acts like a tiny shield. When the AC current pulses, the eddy currents in the aluminum instantly fight the changing flux, which physically delays the magnetic field from passing through that half of the pole by a fraction of a second.
So the magnetic field pulses first on the uncovered side of the pole, and a split second later, it pushes through the covered side.
Exactly. It creates a moving magnetic field from a single stationary coil.
So it creates a sweeping directional wave.
That sweeping field grabs the rotor and spins it. You get a fully functional spinning motor with no internal wiring touching the spinning part at all, just cleverly shaped metal tricking the magnetic field into doing continuous work.
Which culminates in the ultimate synthesis of everything we've discussed today, the Boulder Dam.
Oh, it's the perfect example.
Right. A massive, perfectly curved concrete wall holds back the colossal weight of a river. That crushing water pressure is forced through a turbine.
The water turns the turbine. The turbine turns a massive steel shaft.
And the shaft spins an incredibly intricate, massive arrangement of copper coils and iron cores, a revolving monster of a generator. Because the massive copper coils are physically moving past massive magnetic fields, the flux is constantly, violently changing.
Which induces an enormous electromotive force. The baby Faraday discovered, fully grown.
Fully grown.
Then, that raw current runs straight into a transformer. 2 massive coils of wire that never touch, wrapped around iron. The changing current in the first coil bathes the second coil in a changing flux, inducing an even higher voltage.
Stepping the power up so massively that it can travel efficiently over 600 miles of wire across the desert. I mean, think about the absolute miracle of this sequence. 600 miles away, in a city, the power from that distant river hits another transformer, steps the voltage back down, and flows into a tiny induction motor to turn a dentist's drill. Or it runs through the filament of a light bulb to light up a dark room.
It's astounding.
We are getting hot light from cold water hundreds of miles away, and it is all happening simply because we figured out how to arrange pieces of copper and iron in very specific shapes to harness the flux.
Right.
If you stop the big wheel at the dam, the flux stops changing, the induction stops, the invisible gear stops turning, and all the wheels everywhere else stop. The lights go out.
They really are connected by an invisible, unbreakable chain. The endless grid running your life right now is just the highly engineered, perfected application of Faraday moving a magnet past a wire.
It's so cool to think about.
But, this raises an important question about where we go next. Because designing electrical machinery isn't a dead science.
Oh, are we talking about the future of the grid?
Yes. We briefly mentioned low-temperature superconductors earlier. The materials that perfectly repel magnetic flux and carry current with absolute zero resistance.
Right, but right now they require extreme cold, right?
Currently, yeah. But material science is pushing closer to room temperature superconductors.
Wow. So if we can master large-scale superconductor networks, the fundamental design parameters of the entire world change, don't they?
Entirely. We currently rely on heavy spinning iron and copper monsters to force magnetic fields to do our bidding. But with superconductors, we wouldn't lose energy to heat. We would need massive iron cores.
Will the giant roaring generators of Boulder Dam eventually look like, I don't know, primitive steam engines to us? Replaced by perfectly silent, frictionless, levitating systems that route infinite power with zero loss?
It's highly possible. The power networks of the future might bear very little physical resemblance to the heavy metal spinning monsters of today. The principles of induction will remain, but the execution will look like pure magic.
It really makes you look at a simple wall outlet differently. Every single time you plug something in, you're tapping into a continuous, unbroken chain of changing magnetic flux, stretching all the way back across the country to a spinning turbine and a falling river.
Yeah, it's not just electricity. It's physical motion, translated into invisible fields and translated back again.
Something for you to ponder the next time you flip a switch.
The profound magic of copper, iron, and change.
Thanks for taking this deep dive with us. We'll see you next time.
Welcome to today's deep dive. So, I want you to imagine finding a mysterious master key just sitting on the sidewalk.
Okay.
You pick it up, try it on your front door, and it just works flawlessly.
Right.
And then, you walk over to your car, slide it into the ignition, and it starts right up.
I mean, that would be incredibly convenient, though deeply suspicious from a security standpoint.
Yeah, exactly.
Yeah.
You'd logically assume your car and your house must have, like, the exact same locking mechanism.
Naturally, yeah.
But what if a master locksmith took them apart and told you that these are completely different locks?
Oh, wow.
Right. They have entirely different internal mechanics, different pins, different tumblers, yet somehow this single key just flawlessly turns them both.
It's funny you bring that up because that bizarre coincidence isn't just a lock and key analogy. What you're describing is essentially the flux rule of electromagnetic induction.
Exactly. And that's our mission for this deep dive. Today, we're exploring the laws of electromagnetic induction, specifically guided by Chapter 17 of Volume 2 of the famous Feynman lectures on physics.
It's such a brilliant chapter.
It really is. We're going to explore how moving magnets and wires power, well, our entire world. We'll uncover that bizarre coincidence in nature we just hinted at, break some fundamental rules, and leave you pondering an unsolvable physics paradox.
I love that paradox. It really breaks your brain a little bit.
Oh, totally. But let's start with that master key. We all kind of know the flux rule. It's day one electromagnetism.
Right. The electromotive force, the EMF, equals the negative rate of change of magnetic flux through a circuit.
Okay, let's unpack this for you listening. Imagine a loop of wire, and the magnetic field is like rain falling down through that loop.
That's a good way to picture it.
The flux is just how much rain gets through. So the rule says that if you change the amount of rain getting through, either by shrinking the loop or by changing the rainfall, you create an electrical push, an F.
Yeah, and it's the simple rule that powers the modern grid. But what's fascinating here is what Richard Feynman points out. He notes that this single mathematically elegant rule is actually two completely distinct physical laws just wearing a trench coat.
Wait, really? Two different laws?
Yeah. Nature is using entirely different mechanisms to yield the exact same result. It really is one of the strangest quirks in classical physics.
So, okay, if we break down that master key of the flux rule, what are the two different tumblers?
Well, case one. Imagine a physical loop of wire moving or, say, shrinking within a static magnetic field.
Okay.
The flux through the loop is changing because the physical area is changing. In this case, the EMF is generated by the magnetic force acting on moving charges.
Because the physical material itself is moving.
Exactly. The electrons in the wire are physically moving through the field, so they experience that transverse Lorentz force. In physics notation, it's the V cross B force.
Velocity interacting with the magnetic field.
Got it. Yes. But then you look at case two. In this one, the wire is completely stationary, like it's glued to the table.
Okay, it's not moving at all.
Right. Instead, you change the strength of the magnetic field itself. You change the rainfall. The flux is changing again, so the rule says you get an EMF.
But the electrons aren't moving yet, so there's no V cross B force.
Exactly. There is no V cross B. Instead, as Michael Faraday discovered, a changing magnetic field creates an entirely new electric field in the surrounding empty space.
Oh, wow.
Yeah, that's the Maxwell-Faraday equation. The curl of the electric field equals the negative rate of change of the magnetic field.
Wait, hang on. So nature bakes the exact same cake using two completely different ovens.
That's a great way to put it.
But isn't physics usually about finding, like, one underlying cause for a phenomenon? We usually look for a single, elegant equation that unites everything.
You would expect a deep, unifying, underlying principle. I mean, usually in physics, a beautiful generalization stems from a single, deep principle. But Feynman makes a point to emphasize that there really isn't one here. We haven't found some profound implication that links them at this classical level. It just appears to be a sheer coincidence of nature.
That is so weird. So we just have to accept it?
Pretty much. The rule works flawlessly for engineers, but from a physics perspective, it's just the combined effect of two entirely separate phenomena happening to give the identical mathematical result.
Okay, so if the flux rule is just a happy coincidence of two different laws overlapping, it stands to reason that we can find, edge cases where the rule breaks down entirely.
Oh, absolutely. When a rule is just a convenient summary, you can always find situations that violate it.
If it's a shortcut, there must be a way to trick it.
Yeah, and Feynman illustrates this with a couple of brilliant thought experiments.
Let's look at the first one, the rotating disk.
Right, figure 17-2 in the book.
So imagine a spinning conducting disk, just a solid copper plate sitting in a constant magnetic field. We put an electrical contact touching the center shaft and another one rubbing against the outer edge of the disk.
Okay.
And we connect a wire between them to measure the current. The disk is spinning. Now, the total magnetic flux passing through our circuit area isn't changing at all.
Right, the area is constant, the field is constant.
Exactly. So according to the flux rule, the rate of change of flux is zero. So the current should be zero.
But the meter shows a strong, continuous current.
Wait, really? So the flux rule completely fails here?
It fails completely. It gives you the wrong answer because the physical material of the disk is moving through the magnetic field.
So it's that V cross B force again.
Exactly. Those V cross B forces are pushing the free electrons radially outward toward the edge of the disk, which creates a current even though the geometric flux hasn't changed.
Okay, let's flip it and look at the complete opposite scenario, the rocking plates.
Oh, this is a fantastic setup because of what happens to the geometry.
Right, so imagine two curved metal plates sitting in a magnetic field, and they are rocking back and forth against each other.
Like a rocking chair on a flat floor.
Yeah, but with two curved conductive surfaces touching at one single point. And we connect our measuring wire to each plate to complete the circuit.
Okay, so as they rock, that point of contact physically rolls back and forth.
Yes, and here is where it gets really interesting. Because that contact point is moving, the boundary of our circuit loop is moving wildly.
The physical area is changing massively.
Exactly. So the flux is changing massively. By the flux rule, there should be a huge F generated.
There should be, but there isn't. The meter reads 0.
How is that possible? The boundary of the circuit is literally sweeping across the magnetic field.
It comes down to a fundamental misunderstanding of what the flux rule actually describes. The rule only works if the physical material of the circuit remains the same.
Oh, I see.
Yeah, think about those rocking plates. You aren't stretching or moving a single piece of wire through a field. The path the electricity takes is constantly swapping out to different physical atoms as the contact point rolls.
Wow. So you're constantly building a brand new circuit path.
Precisely. The actual physical motion of the metal plates rocking is very slow, so the V cross B force on the charges is basically negligible.
So the boundary of the geometry is moving, but the metal itself is barely moving at all.
Right. When the material making up the circuit changes, the shortcut rule fails. You just have to abandon it and go back to the two fundamental laws to see what the electrons are actually doing.
Okay, that makes sense. But if the physical material of the circuit dictates whether this rule works, what happens if we remove the material entirely?
What do you mean?
Like, do we actually need wires at all for induction to happen?
Oh, I see. No, we don't. And this is where we get into the pure physics of fields.
Okay, explain that.
Remember that second law, the Maxwell-Faraday equation. A changing magnetic field creates an electric field in free space.
Right.
That electric field doesn't care if there's copper wire there to conduct it. It exists regardless.
So if I put an electron in an empty space, and like a vacuum chamber with a changing magnetic field, it's like a surfer catching an invisible electric wave.
That is exactly what happens. And if you shape that magnetic field correctly, you can make that invisible electric field circular.
Okay.
The electron will get caught in it and accelerate in a massive circle. This is exactly how a batron works.
A batron?
Yeah, it's a particle accelerator that relies entirely on induction without wires.
It sounds incredibly straightforward. You just ramp up a magnetic field, it creates a circular electric wave, and the electron rides it.
It's theoretically straightforward, but practically there is a massive engineering hurdle here.
What's the hurdle?
Well, you are pumping energy into this electron, so it's accelerating to a substantial fraction of the speed of light.
Right, it's going incredibly fast.
And as it goes faster and faster, it wants to fly off tangentially. You need a magnetic field at the actual orbit of the electron to provide a centripetal push, like an inward force, to hold it in that tight circle.
So you need a changing field in the center to accelerate it, and a strong field at the edge to contain it.
Exactly. And here is the brilliant constraint Feynman highlights. To keep the electron in a perfect circle of a constant radius while continuously accelerating it, the average magnetic field inside the entire orbit must increase at exactly twice the rate of the magnetic field directly at the orbit itself.
Wait, exactly twice. A perfect 2-to-1 ratio.
A perfect 2-to-1 ratio. The central flux has to grow twice as fast as the orbital field.
What happens if it doesn't?
If the central flux grows too fast, the electron gets too much energy and spirals outward. If the edge field grows too fast, it pinches the electron inward.
Wow.
Yeah, that 2-to-1 ratio perfectly balances the increasing forward velocity with the increasing inward force required to maintain the radius.
That is such an elegant piece of machine design.
It really is.
But, we don't really hear about batrons anymore. Like
Well,
the big machines today, the Large Hadron Collider, they aren't batrons. Why is there a limit?
well, because at super high energies, the physics turns against you. Any charged particle that accelerates radiates energy, and moving in a circle is, by definition, constant acceleration.
Right. Changing direction is acceleration.
Exactly. So when electrons get up into the hundreds of millions of electron volts, they start bleeding off massive amounts of energy as X-rays.
Oh, synchrotron radiation.
Yes, synchrotron radiation. The simple induction equations of the betatron just break down because the electron is radiating away the energy as fast as you're trying to induce it.
That makes total sense. Well, since we're on the topic of the physical mechanics of fields and moving charges, I want to pivot to a beautifully frustrating thought experiment Feynman poses in Chapter 17.
Oh, the spinning disk paradox. This is one of the most famous puzzles in classical electromagnetism.
It really is.
Period.
And we want you, the listener, to try and solve this with us, because it perfectly illustrates how two, perfectly logical physics arguments can just violently collide.
Yes. Lay out the setup.
Okay, vividly picture this. Imagine a plastic disc mounted on a perfectly frictionless bearing. It is completely free to spin. Right in the center of the disc, there is a coil of wire, a solenoid, with a steady electrical current running through it, creating a strong magnetic field.
Got it.
Now, symmetrically around the outer edge of this plastic disc, we embed a bunch of small metal spheres, and we give each sphere a strong electrostatic charge.
So to recap the starting state, we have a static magnetic field in the center, static electric charges sitting on the rim, and the whole disk is perfectly stationary. Zero motion.
Absolutely still. Everything is perfectly still. Now, the event, somebody pulls the plug, we suddenly switch off the current in the central coil.
Okay, the magnetic flux rapidly drops to zero.
Exactly. Now, here is the paradox. We have two arguments. I'll take argument number one.
Go for it.
The rapidly collapsing magnetic field creates a circular electric field in the empty space around the coil. We just established this with the betatron.
We did.
That circular electric field washes over the charged spheres sitting on the edge of the disk, applying a tangential force to them. Therefore, the disk absolutely must start rotating.
That is a rock-solid argument based on Faraday's law of induction.
Right.
But here is argument number two from a totally different perspective. We have to look at the macroscopic laws of the universe.
Okay.
The principle of conservation of angular momentum states that a system at rest must remain at rest unless acted upon by an outside torque.
Right. Newton's laws.
Exactly. Our system started with exactly zero angular momentum. No outside physical forces touched it. We just flipped a switch on a wire.
Yeah.
Therefore, according to the bedrock laws of mechanics, the disk cannot possibly start rotating.
So the electric field fundamentally has to push the charges, but the laws of motion say the disk cannot move.
Yes.
Which is it? Does the disk spin or not?
This is where we force a reconciliation between mechanics and electromagnetism.
And Feynman deliberately refuses to give the answer in the text. He leaves it as an exercise.
He does. And honestly, we aren't going to give you the answer either.
No, we won't spoil it, but we can give you a hint.
Yeah, a small hint. To solve this, you have to critically evaluate argument number two.
Okay, conservation of momentum.
Right. You have to ask yourself, did the system really start with zero angular momentum?
Wait, what? Nothing was moving.
I know, but is it possible that a static magnetic field and a static electric field crossing each other in empty space can somehow store actual physical momentum before anything even moves?
That is a wild concept to chew on. Fields storing actual momentum in empty space.
It really is.
But leaving theoretical paradoxes to simmer in your mind, let's shift from theoretical spinning disks to the actual spinning coils that power our modern world.
Yes, putting it to work.
Yeah.
generators.
Right. If fields can push on matter like in our paradox, we can use matter to push back on fields.
Which brings us to the AC generator, the absolute backbone of the global electrical grid.
The mechanics of an AC generator are remarkably simple. You just take a coil of wire and physically rotate it inside a uniform magnetic field.
Right, figure 17-6.
As it spins, the angle changes. The amount of magnetic flux passing through the loop is constantly rising and falling.
And according to our flux rule, this changing flux creates an alternating electromotive force, an alternating current.
Right, you convert mechanical motion into electrical energy.
That's the mechanism.
Yeah.
But the physics of what happens next is where it gets really interesting.
Because if I have a little hand crank generator
Yeah.
and I'm physically turning it to light up a bulb,
Yeah.
what does this all mean for energy?
What are you actually fighting against?
Yeah. Am I just fighting the mechanical friction of the gears and bearings? Or is the electricity itself pushing back against me?
The electricity is actively fighting you.
Really?
Yeah, the mechanical work you put in is exactly equal to the electrical energy you get out. Think about the sequence of events.
Okay.
You push a wire through a magnetic field, which induces a current. But now you have a live current flowing through a wire that is sitting inside a magnetic field.
Right.
By definition, a current in a magnetic field experiences a Lorentz force. And Lenz's law dictates that this force will always oppose the motion that created it.
Wow. So the magnetic field pushes back on the very current it just birthed.
Exactly. And the math shows this is a velocity proportional force.
Meaning what exactly?
Meaning the faster you try to spin that crank, the higher the induced current, and the harder the magnetic field pushes back against your hand.
Oh, wow.
It's exactly like the force of viscosity. It feels like you are trying to crank that handle while the coil is submerged in thick, heavy syrup.
So you are physically feeling the resistance of the electrical power being consumed by the light bulb.
Yes. If the bulb burns out, the circuit breaks, the current stops, and the crank suddenly becomes incredibly easy to turn.
Because the electrical syrup is gone. You literally feel the grid in your hands.
You do. And engineers actually use this electrical viscosity, these eddy currents, to their advantage in the real world.
Oh, how so?
Consider the older domestic watt meters on the side of houses. To measure power, they use these exact eddy current forces.
Oh, the ones with the little spinning aluminum disc that tracks your power usage. The ones that spin faster when the AC kicks on.
Right. A small motor drives that disc based on the voltage and current your house is pulling. But if it were just a motor attached to a free spinning disc, the disc would accelerate continuously until friction stopped it, which wouldn't give you a stable speed to measure.
That makes sense.
So, to make the rotational speed exactly proportional to your power usage, they place a permanent magnet over the edge of the aluminum disc.
Oh, I see where this is going.
Yeah. As the disc spins, it generates eddy currents in the aluminum. These currents create a perfect velocity-dependent drag.
The electrical viscosity acts as a precise brake.
Exactly. It balances the motor's torque, so the speed is a flawless measurement of your power consumption.
That is a brilliant application of eddy currents.
It really is elegant.
So we've seen how pushing a moving wire through a field creates current, and how that current pushes back mechanically like syrup.
Right.
But what if the circuit is entirely stationary? No hand cranks, no spinning
Yeah.
coils, no moving parts. Does the electricity still fight back?
It does. And this brings us to arguably one of the most profound concepts in circuit theory, inductance.
Inductance. Simon breaks this into two parts.
Yep.
First, mutual inductance.
Yes, figure 17-8.
Imagine two separate coils of wire just sitting on a table near each other. If I change the current in coil 1, it changes the magnetic field around it.
Right.
That changing field washes over coil 2, inducing a voltage, an electrical push, in coil 2.
And how effectively coil 1 influences coil 2 is dictated by a geometric factor called the mutual inductance.
Okay.
Interestingly, the laws of physics dictate that the mutual inductance of coil 1 on coil 2 is mathematically identical to coil 2 on coil 1. Nature is perfectly symmetrical here.
That's really cool.
Yeah. And the coefficient of coupling, K, tells you how tightly they are linked. If they're wound tightly around the same iron core, K is near 1. If they're across the room from each other, it's near 0.
Mutual inductance makes total sense. But then there is self-inductance, which is, honestly, a bit mind-bending. Because a single coil does this to itself. If you try to change the current in a single coil, the changing magnetic field of the coil creates a reverse push, a back amp, in its own wires that actively fights the change.
It stubbornly resists any change to its current state.
So self-inductance is basically the electrical version of pushing a heavy car.
What do you mean?
Like when the car stopped, it has inertia. It fights you when you try to speed it up.
Right.
But once you finally get it rolling, it fights you when you try to slam on the brakes.
I love that analogy. It's a very useful starting point, and the mathematics parallel it perfectly. The equations for a circuit with self-inductance are a flawless mirror of Newton's laws of motion.
Wait, how exact is the mirror?
Mathematically identical. Figure 1710 lays it all out.
Yeah.
In mechanics, force equals mass times acceleration, which is the rate of change of velocity.
Right. F equals ma.
In electrical circuits, voltage equals inductance times the rate of change of current.
Oh, wow.
Voltage acts as the force. Current is the velocity. And inductance, represented by L, is literally the exact equivalent of mechanical mass. It is the electrical inertia of the circuit.
So when a coil is carrying a steady current, storing magnetic energy, that is the exact electrical equivalent of a heavy car rolling down the highway with kinetic energy.
Exactly. Kinetic energy is 1/2 mass times velocity squared. The magnetic energy stored in a coil is 1/2 inductance times current squared. It's the same fundamental truth of nature expressing itself in a different medium.
That is beautiful. But here's where I need you to clarify something, because Feynman points out a very weird geometry quirk here.
Ah, yes.
If I want to calculate the mass of a car, I just weigh the car. The mass is inside the physical object.
Right.
But you can't just look at the 1D line of a wire circuit to calculate inductance.
You cannot, and this is where your car analogy breaks down in a fascinating way.
Why is that?
If you try to calculate the self-inductance, the electrical mass, by mathematically treating the circuit as a one-dimensional line of wire, the equations completely blow up. They literally integrate out to infinity.
Wait, why do they go to infinity?
Because the energy isn't inside the mathematical line. In the real world, wires have physical thickness, and more importantly, the magnetic field doesn't exist inside the electrons.
Where does it exist?
It exists in the space around them. To find the inductance, you actually have to look at the physical 3D volume of the wires and calculate the total magnetic field energy distributed throughout the entire empty space surrounding the circuit.
Okay, that is wild. So we have covered some serious conceptual ground today.
We really have.
We started with the dual nature of the simple flux rule, that bizarre master key that relies on two totally independent mechanisms to get the exact same result.
And we watched that rule completely fail when we swapped out the material in rocking metal plates.
We examined how electrons can surf invisible electric waves in empty space inside a betatron, provided the magnetic fields are balanced at that perfect 2-to-1 ratio.
We challenged you to figure out where the momentum is hiding in a stationary spinning disk paradox.
We felt the thick, syrupy drag of electrical viscosity in a hand crank generator. And finally, we realized that electricity has its own version of mass and inertia.
And if I can leave you with one final mind-expanding thought based on that exact realization.
Please do.
We just established that inductance is the literal inertia of an electrical circuit.
Right.
But as we noted, to calculate that inertia, you have to measure the magnetic field energy filling the empty space around the circuit.
The infinite volume of space extending outward from the wire.
Exactly. Think about the implications of that the next time you plug something in. Does the mass of an electrical current actually live inside the copper wire where the electrons are moving, or does the true inertia of electricity live out in the invisible empty space surrounding it?
It really makes you look at a high-voltage power line completely differently. The real heavy lifting is happening in the air around the wire, not inside the metal. That's incredible. And to think, we started this whole journey just wondering why a single master key could open two entirely different locks. The universe is full of these strange, elegant mechanics. Thanks for joining us on this deep dive. Keep questioning the world around you and see if you can solve that spinning disk paradox on your...
So, I mean, if you think about it, there was this specific moment in the history of science where the perfect code of the universe, it had this glaring, fatal glitch.
Right, yeah, a literal mathematical glitch.
Exactly. Like, the math essentially said, you know, this thing cannot happen, while it was literally happening right in front of everyone's eyes on a lab bench.
Oh, which is pretty big problem for physicists.
Yeah. So today we're unpacking the tiny mathematical correction that fixed that glitch. And what's wild to me is that the single correction didn't just like patch a formula, it basically birthed the modern world.
It really did. I mean, everything changed after this.
So we are diving into a really pivotal turning point mapped out in the legendary Feynman lectures on physics, specifically Chapter 18 of Volume 2.
An absolute classic.
Right. And the mission of this deep dive is to understand exactly how we got wireless communication, light, electromagnetic waves, all of it. We're going to strip away the heavy jargon, to show you the elegant logic underneath.
Yeah, because up until this specific point in the history of physics, and well, in Feynman's lectures too, the focus had really only been on special restricted situations.
It's like the safe stuff.
Exactly, the safe stuff. Things like steady currents or charges that are just fixed permanently in place.
And moving.
Right, predictable. Yeah. And the mathematical rules governing that specific reality seemed incredibly airtight, like totally solid.
But, I mean, the training wheels have to come off eventually, right? Because even if you, listening to this right now, even if you don't calculate electromagnetic fields every day, your entire modern life relies on what happens when those fields actually start moving.
Absolutely.
Every single time you turn on a light switch or, your phone catches a Wi-Fi signal or a radio wave, you are directly interacting with a phenomenon that early physicists literally thought was mathematically impossible.
Which is kind of funny to think about now.
It is. So, okay, let's unpack this. To really understand the fix, we first need to see the flaw.
Right. So we need to go back to the laws of physics just before James Clerk Maxwell came along.
Okay, pre-Maxwell, set the stage.
Right. So at that time, science had this working equation for the magnetic fields produced by steady currents. Mathematically, it basically stated that the curl of the magnetic field was directly proportional to the electric current.
Hold on, let me just, for those of us not doing vector calculus on a daily basis, curl is essentially just measuring how much a field is like rotating or swirling around a particular point.
Right. Yeah, exactly.
Like water swirling around a drain.
That is a perfect way to visualize it, measure circulation. But so Maxwell noticed a fatal problem with this equation.
The glitch.
The glitch. In the absolute unbreakable rules of vector calculus, there's this strict identity. If you take the divergence of a curl, the answer mathematically has to be 0 every single time, no exceptions.
And divergence here basically means like the net flow of something outward from a specific space, right?
Yes, the net outward expansion. So if you take the divergence of the left side of this equation,
the curl of the magnetic field.
Right, the curl, you get 0,
Uh-huh.
which means if the equation is actually true, the divergence of the right side, the current, must also always be 0.
Meaning the total flow of current out of any closed surface has to balance out completely?
Precisely.
It's saying the amount of electric charge inside a closed space can never, ever decrease. Like, it is impossible for charge to just flow away from a central point and actually deplete the source.
Which, as you can imagine, puts physicists in an impossible bind. If the divergence of the current is 0, you are strictly forbidden from ever draining a source of charge.
Wait, so the old physics was essentially like a bank ledger where money is flowing out to pay your bills, but the account balance never actually goes down.
That is exactly what it was doing, yeah.
But that violates the entire concept of the conservation of charge. We know charges move. We know batteries drain. How did physicists not notice their ledger was completely broken?
Well, because for steady currents, it actually works perfectly.
Oh, because it's a loop.
Exactly.
Yeah.
If current is just flowing in a continuous unbroken loop, the amount of charge in any one section stays totally constant. The flaw only reveals itself when things start to change.
Okay, I see.
And Feynman uses this brilliant analogy to show how absurd this was. Imagine a large block of Jell-O.
Okay, I'm picturing a massive block of Jell-O.
Now imagine there is a small hollow cavity right in the exact center of this Jell-O block. You take a hypodermic needle, you reach into the center, and you inject a large amount of electric charge right into that cavity.
Right.
Because the Jell-O is slightly conductive, that charge then slowly starts leaking out radially in all directions at once, just seeping through the Jell-O.
Which is a completely reasonable physical scenario. You have a central source of charge, and it's slowly dissipating outward.
Yeah, exactly. There is a clear current flowing outward, and the total charge in the center is visibly decreasing.
So the bank account is draining.
Right. But the old equations of electricity and magnetism, they looked at that leaking Jell-O and just hit a brick wall. The math insisted the divergence of the current had to be 0.
It just couldn't handle a source that was actually losing charge.
No. It literally broke the math.
So the math was essentially denying a physical reality that you could easily set up on a lab bench.
Pretty much.
So how did Maxwell actually fix the bank ledger?
Well, Maxwell proposed that the problem could be resolved by adding just one new term to the right side of the equation.
Just one term.
Just one. He added the rate of change of the electric field over time.
Wait, just the rate of change? So he didn't care about the static electric field itself, but specifically how fast that field was altering at any given moment?
Yes, that distinction is everything. As soon as he added that rate of change, the math perfectly aligned with reality.
Wow. Okay, so let's look at how this resolves physical paradoxes, because Feynman gives some great examples.
He does. Imagine a completely symmetrical sphere covered in radioactive material. It's basically acting like a microscopic sun, just radiating charged particles outward equally in every single direction.
Okay, so because there is current flowing out in all directions, we might intuitively expect there to be a magnetic field swirling around this microscopic sun?
Right, but here we hit a massive paradox of symmetry. If you try to actually measure the magnetic field swirling around that sphere, which way would it circulate? Clockwise or counterclockwise?
Oh, well, because the sphere is perfectly symmetrical, there's absolutely no physical reason it should prefer one direction over the other.
Exactly. You can't pick a direction without breaking the fundamental symmetry of the universe.
So, logically, there just can't be any circulation of the magnetic field at all. The field must be zero.
It has to be zero. But the old equation said the outward current had to create a magnetic field.
What's that broken ledger again?
Right. We are saved from this paradox solely by Maxwell's new term. Because as those charged particles shoot outward, the total amount of charge left on the central sphere is decreasing.
Which means the electric field radiating from that sphere is getting weaker over time. It is changing.
Yes. In Maxwell's updated accounting system, the actual current, the charges shooting out, creates a tendency for a magnetic field.
Okay.
But the rate of change of the electric field, which is dropping, creates an exact, equal, and opposite effect.
So they fight each other.
They perfectly cancel each other out.
Yeah.
The mathematical result is exactly zero magnetic field. The paradox vanishes.
The universe's accounting system finally balances. That is so satisfying. But let's apply this to something you might actually find in an everyday electronic device, like a parallel plate capacitor.
Oh, this is a real mind bender.
It really is. So a capacitor is basically two metal plates facing each other, right, with just a gap of empty space between them. And you have a wire connected to the outside of each plate.
Yeah, it's a very standard component in almost every circuit board out there.
Okay, so we push current through the wire to charge up the capacitor. The electrons float down the wire, and as they do, they create a magnetic field swirling around the wire. You can measure it.
Very easily, yeah.
But what happens if you take your measurement instrument and slowly slide it down the wire until you slip off the edge of the physical wire and into the empty gap between the two plates?
Right, and this is where the old physics completely fell apart. In that gap, the physical wire stops.
There's nothing there.
Nothing. There are no electrons moving across the empty space. The physical current is literally zero. So under the pre-Maxwell rules, the magnetic field should instantly blink out of existence the moment your instrument enters the gap.
But it doesn't.
No, it doesn't.
The magnetic field is still there, swirling in the empty space between the plates, maintaining the exact same strength it had around the wire.
And that is entirely because of Maxwell's addition.
Yeah.
Even though there is no physical wire, charge is rapidly building up on the capacitor plates.
Right.
That means the invisible electric field stretching between those plates is growing stronger. It's changing. Maxwell's equation reveals that this changing electric field steps in and acts exactly like a current. If you integrate the changing electric field in that empty gap, it produces the precise magnetic field that the physical current was producing just a millimeter away.
So if the physical wire stops, but the magnetic field doesn't, then this changing electric field must be picking up the baton.
Exactly.
A changing electric field essentially is a current as far as the magnetic field is concerned. It's completely seamless.
It is entirely seamless. And, having proven this fix works, Feynman takes a moment in his lectures to just step back and look at the completed masterpiece.
That's quite a view.
It is. You can essentially write the entirety of classical physics, known by the year 1905, on a single small napkin.
Just a napkin. And it really is a short list. Let's look at it.
It's remarkably brief. You have Maxwell's 4 equations, now fully complete. You have the conservation of charge.
Though, wait, based on what we just discussed, conservation of charge is technically redundant now, isn't it? The bank ledger is baked directly into Maxwell's equations?
Well, yes, it is functionally redundant now, but it's traditionally listed just to show the foundation.
Gotcha.
Then you add the Lorentz force law, which translates how these invisible fields actually push and pull on physical moving charges.
Okay, so that connects the fields to matter.
Right. Then you add Newton's law of motion, linking force to momentum. Feynman even notes the early relativistic modifications, showing how momentum bends as you approach the speed of light.
Oh, interesting.
And finally, Newton's law of gravitation.
And that's it. That is all of the fundamental operating logic of classical physics, just sitting on a single page.
Feynman describes reaching this point in the lectures as climbing a great peak. He says we are standing on the top of K2.
I love that analogy.
Right. We have climbed the peak of a great divide. Mount Everest, which is quantum mechanics, is still off in the distance. But for classical physics, we are at the summit. Now we can just coast down the other side and observe the landscape.
And the landscape we see when we coast downhill is, frankly, bizarre.
It's completely alien.
Because the most profound consequence of these completed equations is the discovery of fields that can travel entirely on their own, like completely disconnected from wires or charges.
Yeah. And to visualize how this happens, we have to run a very specific thought experiment.
Okay, let's do it.
Imagine an infinite flat sheet of electric charge just hovering in space.
A completely uniform static sheet of charge, just sitting there.
Right. Then suddenly we jerk it into motion, we pull it sideways, so it's sliding at a constant speed.
Okay, so instantly, our static sheet becomes a massive uniform sheet of current. Now, because we have a current moving, we immediately generate a magnetic field right next to the sheet. But because we just created a magnetic field where there wasn't one a second ago, that magnetic field is technically changing.
And here is where we bring in Faraday's law. Faraday discovered that any changing magnetic field will automatically induce an electric field.
Okay, but thanks to Maxwell, we know it doesn't stop there, right? Because this new induced electric field is also changing from zero to something, which means it creates more magnetic field.
Yes, it triggers a continuous, unending chain reaction. The changing fields feed into each other and they march outward from the infinite sheet into empty space like a tidal wave.
Just a wall of energy moving out.
Exactly. They have a distinct, sharp front edge moving forward at some constant velocity. Let's call it Vs.
Yeah, here.
Behind this advancing wavefront, the space is filled with constant fields. Ahead of it, the space is entirely empty.
So let's focus on that advancing wavefront, because we have two different rules governing how it moves. If we apply Faraday's law, the changing magnetic field creating the electric field, we get a very simple constraint. The magnitude of the electric field, E, has to equal the velocity of the wave, V, multiplied by the magnetic field, B. So E equals V times B.
Right. But we also have to satisfy Maxwell's new rule, the changing electric field creating the magnetic field.
The new part of the ledger.
Exactly. And when you map that out, it gives you a second constraint. A constant which we'll call C squared times the magnetic field B must equal the electric field E times the velocity V.
So we have two mathematical conditions dictating the identical physical wave. E equals VB and C squared B equals F.
Yep.
And logically, there is only one way both of those equations can be true at the exact same time. If you do the algebra, the velocity V at which the tidal wave travels cannot be arbitrary. It must be exactly equal to C.
Right. The wave is totally locked into traveling at that specific predetermined speed.
Which brings us to the truly beautiful part. What happens if you jerked that sheet into motion, sending this wave expanding outward, and then, a moment later, you abruptly stop the sheet dead?
Wow.
So if moving the sheet creates this endless tidal wave, stopping the sheet shouldn't just turn the wave off, right? Because the energy is already out there, moving away at speed c.
Exactly. The principle of superposition tells us that stopping the original sheet is mathematically identical to sliding a second negatively charged sheet in the opposite direction.
Okay, so it sends out a second wave front that exactly cancels out the fields behind it.
Yes. And the result is mind-blowing. A finite block of electric and magnetic fields literally breaks off from the sheet.
Just detaches.
It completely detaches. The fields have taken off. They're traveling through space entirely on their own, completely severed from the physical source that created them.
I think Feynman writes that the caterpillar has turned into a butterfly.
It's a great metaphor.
And this isn't just like some abstract math concept. That detached block of self-sustaining energy, that is the Wi-Fi signal hitting your laptop right now.
Yeah.
It is the text message flying through the empty space of your living room.
It really is. And the mechanism of how they survive without their source is essentially a perpetual dance. The changing magnetic field constantly creates the electric field, and the changing electric field constantly creates the magnetic field.
They just keep each other alive.
Exactly. They maintain themselves, just swishing back and forth through the vacuum of space forever.
A self-sustaining dance propagating outward at speed c But, I mean, that demands an answer to the biggest question. What actually is c?
When Maxwell looked at his equations, how did he know what that speed was?
Oh, this is a moment where the history of science literally reads like a thriller. Because c was actually already known to physics, but merely as a static coincidence.
Wait, a static coincidence? What do you mean?
Well, long before anyone was talking about waves or moving fields, physicists were just studying basic static electricity and static magnetism. Just simple stuff.
Right. And there were two specific constants that kept showing up in the math. One constant dictated the simple push and pull between two stationary electric charges.
Like rubbing a balloon on your hair.
Sure, yeah. And another constant dictated the magnetic force between two steady, unchanging wires carrying current.
So we're just talking about measuring everyday static forces on a quiet lab bench. No tidal waves, no infinite sheets flying around.
Exactly. Just bench science.
Mm.
And experimentalists had carefully measured the ratio between these two stationary constants.
Okay.
The square root of that ratio, literally just that number popping out of basic lab bench experiments, turned out to be roughly 300 million meters per second.
300 million meters per second. That number is undeniable.
It is. So when Maxwell finished the math for his self-sustaining wave of fields, he saw that the wave must travel at this exact speed.
And he recognized the number.
He recognized it immediately from those earlier static experiments. And, more importantly, he recognized what else travels at that exact speed in nature.
The speed of light. Maxwell realized what he had just uncovered. I actually have his quote here, and it still gives me chills. He wrote, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena."
It remains one of the greatest conceptual unifications in human history.
It's incredible.
Because before that realization, light was simply light. It was an entirely separate category of existence from electricity, which was, sparks, or magnetism, which was just rocks pointing north.
Right.
Suddenly, Maxwell proved that light wasn't something else. It literally is electricity and magnetism. It's just a detached block of fields doing their perpetual dance through space.
But, and tell me if I'm wrong here, the math involved in tracking that dance is notoriously brutal, right? Dealing with an electric field and a magnetic field constantly swirling and creating each other in 3 dimensions.
Oh, it is.
It's like trying to accurately map a swirling tornado, while you're standing inside it.
It is incredibly complex, which is why physicists look for ways to simplify the underlying geometry.
Okay, how do they do it?
Well, instead of dealing directly with the interdependent swirling electric field E and magnetic field B, they introduce a mathematical trick. They define a scalar potential called phi
Okay.
and a vector potential called A.
But how does trading 2 complex fields for 2 new potentials actually simplify anything? It sounds like you just swap the letters.
Think of it like this. Instead of tracking the chaotic, swirling winds of the tornado directly, the potentials allow us to map the underlying atmospheric pressure gradients and the general flow lines that actually cause the wind.
Oh, I see.
Because we have the freedom to define how these abstract potentials relate to each other, physicists can set them up really cleverly. Specifically, they align the spatial geometry of the vector potential with the time derivative of the scalar potential.
And when you map that underlying topography, what happens to the messy Maxwell equations?
All the cross-contamination just cancels out. The interdependent mess separates perfectly. Yeah. You get one isolated equation for the scalar potential driven only by electric charge, and one isolated equation for the vector potential driven only by current. And the mathematical form they take is exactly identical to the standard 3D wave equation.
Meaning the math is exactly identical to the equations we use to describe, like sound waves propagating through a room.
Exactly the same.
Just mapped onto the fundamental fabric of the universe. That reveals a perfect underlying symmetry in the x, y, and z directions of space and in time.
Yeah, the only caveat is a factor of -1 over c squared attached to the time derivative, which simply exists because we measure time and space in different units.
Right.
But the symmetry is breathtaking. It makes it immediately apparent that electromagnetic waves must exist, rippling through the geometric landscape of free space.
Wow. So we started this journey with a completely broken bank ledger, a mathematical glitch where a leaky block of jello violated the fundamental conservation of charge.
Very weird start.
Right. And Maxwell fixed that glitch by simply adding the invisible reality of a changing electric field.
And that one tiny addition completed the equations of classical physics, taking us all the way to the summit of K2.
Coasting down from that summit, we watched a static sheet of charge turn into a tidal wave. We saw the caterpillar turn into a butterfly, and we literally witnessed the birth of light itself, not as a new physical object, but as an eternal self-sustaining dance of electric and magnetic fields.
It is a profound shift in how we understand reality.
Hmm.
And, I think there's a haunting idea drawn from this history that we should really consider.
Oh, what's that?
Think about the fact that by simply measuring the static, unmoving push and pull between magnets and stationary charges on a quiet laboratory bench, scientists were able to mathematically uncover the absolute speed limit of the universe.
That is
What
wild.
makes you wonder, what other profound cosmic secrets are hiding entirely in plain sight, just waiting to be found in the quiet, everyday forces right in front of you?
Are there other quiet glitches in the code of reality we're just accepting as normal? Holding the key to an entirely new universe? Definitely something to think about the next time you connect to Wi-Fi or, just turn on a light switch. Thank you for joining us on this deep dive. Keep questioning, keep wondering, and we'll catch you on the picture a high school classroom. The air smells like, chalk dust and floor wax. Sitting at one of the desks is a young Richard Feynman. This is years before he'd become a Nobel Prize-winning physicist. And he's incredibly bored.
Oh, completely. The physics class is moving entirely too slowly for him.
Right. And his teacher, Mr. Bader, notices this. He calls Feynman down after class and says, you look bored. I want to tell you something interesting. And what Mr. Bader shared in that quiet moment wasn't just like a neat physics trick. It was a complete paradigm shift regarding how the universe fundamentally operates.
It really is a profound shift in perspective. Because if you think about how most of us are taught Newton's laws, specifically force equals mass times acceleration, that is a moment-by-moment rule.
Yeah, like inching along.
Exactly.
Yeah.
It tells you how an object inches its way forward. A force pushes, the object accelerates, instant by instant, blindly feeling its way through space. But Mr. Bader introduced Feynman to a completely different view.
Which is just so cool to think about.
What if the object isn't just reacting blindly to pushes and pulls? What if instead it's taking a grand, holistic view of its entire journey from start to finish and trying to minimize a specific grand total?
The idea that the universe is fundamentally lazy, right? Like always looking for the absolute most efficient path. So in this deep dive, we're going to unpack this concept. It's called the principle of least action.
Yes, a very famous principle.
We'll explore how physicists mathematically prove that objects take this laziest path. We'll demystify the bizarre, almost philosophical question of how a simple particle actually knows which path to take before it even gets there. And we'll see how this single principle unlocks everything from classical physics to the absolute mind-bending weirdness of quantum mechanics.
It's quite a journey. And to understand how the universe minimizes this thing called action, we really have to define what action actually is without getting lost in the weeds.
Right, keep it grounded.
In classical mechanics, action is calculated over the entire path an object takes from a starting time to an ending time. And it's defined as the object's kinetic energy minus its potential energy, constantly added up over that whole journey.
Okay, let's unpack this, because taking an energy and subtracting another energy sounds, I don't know, a little abstract for a physical journey. Let's look at the kinetic energy part first.
Sure.
Kinetic energy is the energy of motion. If there are no outside forces acting on an object, meaning zero potential energy, the rule says it has to minimize just its kinetic energy over the trip.
Let's bring this down to earth with a practical scenario straight from the source material. Imagine your job is to drive from home to school, and you have a fixed, specific amount of time to get there. You can't arrive early, and you can't arrive late.
Okay. And the physical distance between home and school is fixed, too.
Right, exactly. So you have a few options. You could, accelerate like mad out of your driveway and then slam on the brakes and coast for the last mile.
Sounds like how I drive, actually.
Or you could put the car in reverse, back up a block,
Yeah.
and then speed up to compensate.
Right.
Or, and this is the key, you could just drive at a perfectly steady, uniform speed the entire way.
Right.
No matter which option you choose, your mathematical average speed has to be exactly the same because you are covering the same distance in the exact same amount of time.
But the action principle isn't looking at your average speed, is it? It's looking at the kinetic energy, and kinetic energy is based on the square of your speed.
Yes, that squaring effect changes everything. The mathematical mean square of a varying quantity is always greater than the square of its steady mean.
Well, break that down for me.
So if you wobble your velocity, say you drive 100 miles per hour for a bit and then 20 miles per hour, that 100 miles per hour creates a massive spike in your kinetic energy because you are squaring that large number.
Oh, I see. So any variation, any speeding up and slowing down totally punishes your total score.
Exactly. The total kinetic energy over the trip will always be higher if you vary your speed than if you just maintained a constant, boring, steady velocity. The mathematical minimum is a uniform speed.
Which beautifully matches what we know about free-floating objects in space.
Right?
Without outside forces, they just glide at a constant speed in a straight line.
Exactly.
So minimize the movement variations to keep the kinetic energy low. I get that part. But the full formula is kinetic energy minus potential energy. Let's bring gravity into the mix. Say I take a baseball and throw it up in the air to you.
Now the math gets a bit of a twist. Because we were subtracting the potential energy, which is, the energy an object gains by having height in a gravitational field, the object actually wants to accumulate as much potential energy as possible.
Because we're subtracting it.
Right. By getting high up in the air, you are subtracting a big negative number from the total action.
So wait, if I want to minimize the final total, but I'm subtracting the height, it's almost like taxes. Yeah, like I want to spend as little cash out of pocket as possible. That's the kinetic energy, the movement.
Yeah.
But I want the biggest deduction possible. The potential energy is like a tax write-off. So the ball wants to go as high as possible to get the biggest tax write-off to lower its final bill.
That is honestly a remarkably perfect way to visualize it. You want to maximize your deductions to lower your overall liability, but the ball can't just shoot straight to the moon to get an infinite write-off.
Because it still has that fixed time limit to get to your hand.
Exactly. To get incredibly high up into the atmosphere and still come all the way back down to my hand in that exact same specific time frame, the ball would have to travel incredibly fast.
Right.
And traveling incredibly fast means an enormous spike in kinetic energy.
Your out-of-pocket expenses would skyrocket, which completely ruins the benefit of the tax write-off you just got.
It becomes a delicate balancing act. The ball goes up just high enough to gather a good chunk of potential energy, but not so high that it has to speed like crazy and ruin its kinetic energy score.
So it's optimizing.
Yes. When you calculate the absolute perfect mathematical balance between those two, the minimum total action, the resulting shape of the journey is that beautiful, familiar, parabolic arc of a thrown ball.
It's so elegant when you lay it out like that. But understanding what the ball is doing conceptually feels very different from understanding how a physicist actually proves it mathematically.
It is different, yeah.
I mean, if I have a rod that's heated in the middle, I know ordinary calculus can find the single hottest point on that rod. But here, we aren't looking for a single point. We're talking about an entire curve drawn through space and time. How do you even do math on a whole path?
You have to step away from ordinary calculus and use a branch of mathematics called the calculus of variations. It's designed specifically for this.
Calculus of variations. Okay.
A classic example outside of physics is trying to find the shape of a given perimeter that encloses the most possible area. The answer is a circle, but to prove it mathematically, you have to find a way to vary the entire shape, checking all possible boundaries.
So to do this for our baseball, we have to imagine the true, perfect path of the object and then somehow compare it to all the, wrong paths.
Yeah, exactly. We set up the true path. Let's call it the underlined X path. Then we imagine a false trial path that deviates just a tiny microscopic bit from the true one. We call that tiny deviation eta.
Eta, like the Greek letter.
Right. And this brings up a crucial misunderstanding that even some physics students fall into. We constantly call this the principle of least action. But that's actually a misnomer.
The name itself is misleading. It doesn't have to be the absolute minimum.
The true requirement is that if you are on the correct path and you make any first-order variation, that tiny shift we called eta, it results in a zero first-order change in the total action. The formal term is that the action is stationary.
Help me visualize stationary versus least, because that's a subtle difference.
If you visualize the total action of all possible paths as a massive rolling landscape, you aren't necessarily looking for the bottom of the deepest valley. You might just be looking for a perfectly flat plateau.
Oh, I see.
The key is that if you take a tiny microscopic step in any direction away from your spot, your altitude doesn't change in that first instant. It's completely flat all around you.
I picture it like trying to tune a loose guitar string. The true path is the natural resting state of the string.
Mm-hmm.
If you pluck it, which is adding that little deviation, that eta, and the overall tension of the string doesn't change in that first initial instant of the pluck, you found the true resting get line of the string.
The guitar string is a great mental model. To prove this mathematically, physicists write out the formula for the action of the true path plus that tiny deviation. And, well, the algebra gets messy.
I can imagine.
We have to use a mathematical trick to essentially peel away the complex layers of the path's derivatives, isolating that tiny deviation until only the core rule of the physics is left exposed.
So you shuffle all the physics stuff onto one side of the equation and multiply it by that tiny deviation, Ada. And because of the rule, that whole thing has to equal zero.
And this leads to a brilliant logical trick using what the source calls the blip concept. Yes. We said the total integral of our physics equation multiplied by the deviation has to equal zero for any variation. So imagine drawing the path of the ball on a chalkboard. Now imagine the deviation is completely flat zero everywhere except for one momentary tiny little bump, a blip up and down at one specific fraction of a second.
Just a sudden tiny twitch in the path.
Exactly. If the grand total of our physics stuff multiplied by the blip equals zero, and we can physically see the blip itself is not zero,
then the physics stuff occurring at the exact moment of that blip must be zero, because anything multiplied by zero is zero. If the blip is an actual number, the physics side has to be the zero.
You got it. And since we can draw that little blip anywhere we want along the entire timeline of the journey, that physics stuff must be zero everywhere at all times, moment by moment.
So we peel away all the math, we isolate the physics inside the brackets. What actually is that physics stuff that gets mathematically forced to zero?
After all the peeling and shuffling, the term left in the bracket is simply the negative mass of the object times its acceleration, minus the derivative of the potential energy, which is just the force.
Okay.
You set that bracket to zero, move things to either side of the equal sign, and you get mass times acceleration equals force.
That is wild. The grand, holistic, whole path principle mathematically perfectly derives Newton's formulae.
The two views of the universe are mathematically identical for conservative systems. You can view the universe as inching forward instant by instant, or you can view it as solving for a grand total over time. The math doesn't care.
Okay, the math is flawless. I see how they connect. But stop for a second, because here's where I get completely stuck on the physical reality.
Okay, where do you get stuck?
It's one thing to say Fulminaller works moment by moment. A particle feels a push, it moves, but this whole path perspective implies foresight. Are you telling me a literal baseball thrown in the air is somehow calculating all possible paths to the moon and back in real time just to figure out which one has the stationary action?
It's a great question.
Does the particle somehow smell the neighboring paths before deciding where to go? That sounds like magic, not physics.
It is the elephant in the room, for sure. From a moment-by-moment perspective, causality makes intuitive sense. But the whole path perspective implies the particle knows the end destination and physically tests all routes. It's a massive philosophical red flag.
Yeah.
And the answer to your question, does it smell the paths, brings us to the absolute core of quantum mechanics. The bizarre miracle of our universe is that, yes, it actually does smell all the paths.
Wait, really? A macroscopic object is testing alternative realities?
It breaks our macroscopic intuition entirely. In quantum mechanics, a particle doesn't take one single path. It takes all possible imaginary trajectories simultaneously.
All of them.
All of them. Every single path you can draw, no matter how absurd, has a probability amplitude associated with it. And that amplitude is tied to the action of that specific path.
So how does the action dictate which path we actually see?
Think of every possible path having a tiny internal stopwatch. As the particle travels a specific path, the hand on this stopwatch spins around, and its final angle, its phase, depends entirely on the total action of that path. If the action is large, the hand spins furiously.
And this is where Planck's constant comes into play, right? It's the microscopic gear driving the stopwatch.
Yes. In the quantum formula, the action is divided by Planck's constant, which is unimaginably, infinitesimally small.
So tiny.
Because we're dividing by such a tiny number, even a microscopic change in the action will cause that little stopwatch hand to spin wildly, hundreds or thousands of times.
So if a particle tries to take a wrong path, say our baseball deciding to take a quick detour to the moon before hitting my hand, the action for that path is huge. And for a path just a millimeter to the left of that moon detour, the action is slightly different.
Exactly.
But because Planck's constant is so small, that tiny difference makes the stopwatch hand for the second path end up pointing in a completely different direction than the first one.
You've hit on the crucial mechanism. When you add up the results of all those millions of wrong paths, their stopwatch hands are pointing in completely random, wildly different directions. A hand pointing up cancels out, a hand pointing down. Left cancels right. They obliterate each other entirely. Physicists call this phase cancellation.
All the absurd paths just mathematically erase themselves. But obviously they don't all cancel out or nothing would ever move.
There is one magical place where they don't cancel out. Think back to our plateau. Where does the action barely change at all when you shift the path a tiny bit?
The stationary point, the path of least action.
Around the true path of least action, the plateau is so flat that the total action barely changes from one neighboring path to the next. Because the action is basically the same, all their little stopwatch hands end up pointing in roughly the exact same direction. They add together, reinforcing each other, creating a massive spike in probability that the particle will be found right there.
So the baseball is quantum fuzz. It is taking all paths.
But as we scale up from the quantum world of a single electron to the macroscopic world of a baseball, the action becomes incredibly massive compared to Planck's constant. The cancellation effect on the wrong paths becomes so brutal, so absolute, that the macroscopic object appears to cleanly, perfectly follow just that one single classical path.
The quantum fuzziness is just shaved off by the sheer massive scale of the universe, leaving us with what looks like a simple, lazy, parabolic arc. That is honestly breathtaking.
It is one of the most beautiful connections in all of physics. It bridges the microscopic and the macroscopic seamlessly. And because this principle is so deeply baked into the reality of the universe, we can actually step outward and see its utility across completely different fields of physics.
Right, because this isn't just about throwing baseballs and calculating kinetic energy.
No, the concept expands. The function we've been integrating over the path, the kinetic energy minus potential energy, has a formal name. Physicists call it the Lagrangian, named after the mathematician Joseph Louis Lagrange.
Okay, the Lagrangian.
But it's important to understand that the Lagrangian isn't always just kinetic energy minus potential energy. That specific recipe only works for classical slow-moving mechanics.
So if you start looking at things moving near the speed of light, does the lazy universe principle break down?
The principle holds, but the recipe for the Lagrangian changes. In relativity, the Lagrangian becomes a much more complicated formula. It has to factor in the rest mass of the object and the speed of light.
Makes sense.
If you are dealing with electromagnetism, the Lagrangian has to include the invisible scalar and vector potentials of the magnetic fields. Finding the correct Lagrangian for a brand new area of physics is actually a process of educated trial and error. Physicists fiddle with the equations until they fit perfectly into the principle of least action.
But once they find that specific Lagrangian, they basically hold the master key to that entire domain of physics. And the incredible thing from the source material is that this isn't just for theoretical chalkboard derivations. We can use these minimum principles as practical brute force tools.
We can. For instance, in electrostatics, you can find complex electric fields without having to solve horrific page-long differential equations. You do this by relying on the fact that the true electric field in nature will naturally minimize the total electrostatic energy of the system.
Let's walk through the example they gave because it turns high-level physics into a literal guessing game.
Okay, sure.
They talk about finding the capacity of a cylindrical condenser, which is basically just a wire running down the inside of a hollow metal tube. Let's say you're an engineer, you need to calculate its capacity, but the math for the exact electric potential between the wire and the tube is just too complex to solve directly. The minimum principle gives you a massive cheat code.
It provides a very structured framework for guessing, because the true potential distribution is the absolute lowest possible energy state. Any wrong guess you make for the mathematical potential will inadvertently add artificial energy to the system, meaning your calculated capacity will always be slightly too high. It acts as an absolute mathematical upper bound.
I was reading this and thinking, this is exactly like the game, The Price is Right.
Huh, how so?
Well, you are standing there throwing out bids for the capacity, and the fundamental rules of the universe guarantee that your guess will always overbid the true capacity. You can't ever accidentally guess lower than reality. So if you know you are always overshooting, you just keep tweaking your guess to get the number as low as possible without worrying about dipping under.
Yeah, it's an incredibly powerful optimization technique. In the condenser example, they start with a very crude guess. They assume the electric field is simply constant, a straight, linear line from the wire to the tube. It's a rough approximation, but because of the math of the minimum principle, the error is only second order. Even a bad guess gives a surprisingly decent estimate.
But then they upgrade the guess to get closer. They say, let's try a curve instead of a straight line. Let's try a parabola. But they leave one parameter in the parabola equation completely blank, an unknown variable.
They insert an unknown parameter, let's call it alpha. By calculating the total capacity using that equation with the unknown alpha, they get a new formula. Then, Using very basic standard calculus, they find the exact value of alpha that pushes that specific formula to its absolute mathematical minimum.
You essentially use calculus to automate finding the lowest possible bid.
And the result is remarkably accurate. For a cylinder where the outer radius is exactly twice the inner radius, the true, agonizingly difficult mathematical answer for the capacity factor is 1.4427.
Okay, 1.4427.
The optimized guessing method, which is vastly easier to calculate, gives 1.444. It gets you incredibly close, turning an intractable math problem into a simple optimization game.
It's just wild to me that whether you are plotting the orbit of a planet through space, calculating the quantum probability of an electron, or engineering a condenser tube on a workbench, you are relying on the exact same underlying philosophy. The universe is constantly optimizing.
It really brings our journey full circle. We've traced the evolution of thought from inching along a path moment by moment, reacting blindly to forces, to understanding the grand holistic sweep of a particle's journey through space and time. It elevates physics from mere mechanical reaction to an almost elegant mathematical inevitability.
But of course, Feynman doesn't just wrap everything up in a neat little bow. He always leaves you with more mysteries. At the very end of his lecture, he left his students with a massive, unresolved question. We've seen how action rules mechanics and electrodynamics, but there are other minimum principles out there in nature.
Yes. For example, if you push an electric current through a regular wire, classical theory dictates that the electrons will distribute their velocities in a specific way that minimizes the generation of entropy, which is basically heat and disorder.
Another lazy principle, the electrons want to generate the absolute least amount of chaos possible while flowing through the wire.
But Feynman points out a friction point between classical and quantum theory. The true, deep description of those electrons moving through something like an ionic crystal requires quantum mechanics. They're in little billiard balls. They're operating in that fuzzy multipath realm of probability amplitudes and spinning stopwatches we talked about earlier.
So the provocative thought for you, the listener, to take away is this.
Yeah.
Does that beautiful classical principle of minimum entropy generation still hold up when the world dissolves into the quantum fuzz? When the electron is smelling all possible paths through a crystal, is it still somehow trying to globally minimize the heat it generates? It's a tantalizing reminder that even the greatest minds, standing in front of high school chalkboards, are still searching for the absolute limits of this lazy universe.
The search for those minimums and where they break down continues to drive the very frontier of physics today.
So next time you see a ball flying through the air in a perfect, graceful arc, don't just see gravity pulling it down moment by moment. Look closer. See a universe balancing its ledger, canceling out infinite quantum possibilities, and finding beautifully the path of least action. I want you to take a second and just look at the space in the exact room you are sitting in right now. Like just the empty air between you and the wall.
Yeah, or between you and whatever device is playing this audio.
Right. It looks empty, you know?
Quiet.
Quiet. Still. But if you could put on a pair of magic glasses that revealed the actual physical reality of that space, you would be entirely blinded.
Oh, absolutely blinded. What we perceive as nothingness is actually a violently active medium.
It's just teeming with an invisible, chaotic symphony of electromagnetic field.
Right now, in your room, there is the steady, quiet pull of the Earth's magnetic field. And overlaid on that, you have irregular static electric fields generated just by you moving in your chair.
Just the friction of your clothes against the fabric.
Exactly.
And that is barely scratching the surface of the local stuff. I mean, if you look closer, there are magnetic fields wiggling at exactly 60 cycles per second, completely in sync with the alternating current generators at the nearest power plant.
There are infrared waves radiating from your warm forehead toward the colder windows.
Visible light bouncing from the floor to the ceiling at 186,000 miles per second.
And add to that the radio waves. There are waves flying right through your body carrying the music of a jazz band from a local station. Waves carrying data, text messages, Wi-Fi packets.
Oh, and if we look at the tiniest, most subtle wiggles of all, there are fields crossing through your room that originated millions of miles away. Like the faint telemetry transmitted from a spacecraft passing Venus.
Or waves from remote galaxies billions of light years away, all intersecting right where you are sitting.
It is so wild to think about. So how does this invisible chaos actually work? That is our mission for this deep dive.
We're unpacking Chapter 20 of Volume 2 of the legendary Feynman Lectures on Physics.
Yes, we want to understand the mechanics of how these fields detach from their sources, how they travel totally alone through free space, and why trying to picture them might literally short-circuit your brain.
And of course, the beautiful strict mathematics that make this entire invisible symphony possible.
So let's get into it.
To understand the sheer complexity of the room you're in, we have to strip away that chaos first. We have to isolate the phenomenon.
Right. Look at the absolute simplest possible scenario.
Exactly. How a single electromagnetic wave is born and how it physically detaches from its source.
And Feynman starts this by having us imagine an infinite sheet of electrical current. Just this massive, flat wall of charge sitting there. Suddenly we flip a switch and turn the current on. It starts moving.
Yeah, and when that flat current sheet is turned on, it generates an electric field and a magnetic field. But the critical insight here from Maxwell's equations is that these fields do not just appear everywhere in the universe instantaneously.
Oh, right. They push outward from the sheet at the speed of light, which we call c.
Yes. So if the current has been flowing for a certain time, t, there is a uniform field extending out a distance of c times t.
And beyond that physical boundary.
The universe doesn't even know the current was turned on. The wavefront simply hasn't arrived yet.
That is so crazy. The text references figures 20-1 and 20-2 to visualize this. It is a literal wall of energy sliding forward.
Right. Let's say we turn on 1 unit of current and just leave it flowing. We get this flat plateau of electromagnetic field stretching out into space, pushing forward at the speed of light.
But Feynman doesn't stop there. He asks us to imagine a sequence. What if we turn the current onto 1 unit for a while, and then suddenly crank it up to 3 units?
This is where the principle of superposition comes in. It allows us to handle this without having to calculate some massively complex new dynamic system. You simply add the separate scenarios together.
Okay, let's unpack this. How does that addition look?
Well, you take the field generated by the 1 unit of current, and then at a later time you add the field generated by turning on 2 additional units of current.
So the result is a field that looks like a set of stairs.
Exactly. You have a lower step further out in space from the earlier lower current, and a higher step closer to the source from when you crank the current up.
So if we extrapolate that, turn it to 1 unit, then up to 3, then completely off to 0. Figure 20-3 shows the result. You get a literal blob of electromagnetic field that has fully detached from the source.
It is an independent block of energy sailing through empty space.
And here's the thing that really blew my mind. The shape of that field distribution flying through space is an exact, perfectly detailed graph of how the current varied with time at the source.
But it is drawn backward.
Yes, I want to linger on this because it is such a profound aha moment. It is exactly like holding a long rope and wiggling it up and down.
That's a great analogy.
Like the wiggle currently in your hand is what you're doing right now. But the wave traveling 10 feet down the rope is a literal physical memory of what your hand did 2 seconds ago.
Right. The part of the electromagnetic wave furthest from the source was created first. The part closest was created last.
So if you are standing miles away letting this field wash over you, you are basically reading a vinyl record of that current's exact history.
It fundamentally updates our understanding of what a field is, Long after the source has been turned off, after all the charges completely stop moving, that block of field continues to travel.
So electric and magnetic fields are not just invisible, static tethers attached to charges.
No, not at all. Once created, they are dynamic, autonomous entities. We can calculate the field at a given time by looking at the current at the source, but at an earlier time. The time delayed by how long it took the light to reach us.
Wow. Okay, so we have this autonomous memory blob flying through space. But to understand the room I'm sitting in right now, we need the actual traffic laws it follows. How does it move through the emptiness?
Well, in regions of space where there are no charges and no currents, just free space, Maxwell's equations simplify down to the 3-dimensional wave equation.
And to grasp the mechanics of it, Feynman strips it down to 1 dimension. We look at waves moving just along the x-axis.
Right, and the mathematical solution to this 1-dimensional wave equation is a function written as f of x minus ct.
Figure 20-4 shows this. It represents a constant, rigid shape, like a specific squiggle or a bump, that simply translates forward toward positive x at the speed of light.
And the mechanism behind that is actually incredibly intuitive.
Right. Think about the math of f of x minus ct. If time, t, ticks forward, then to stay at the exact same spot on the wave, say the peak of the bump, your distance, x, also has to move forward to balance out the subtraction and keep the input the same.
Exactly. That minus sign in the math is literally the engine driving the wave forward. The math is wonderfully elegant here.
But wait, so we just cook up a forward argument because we already know the answer.
Well, physicists often skip deriving it from scratch and just sort of guess the solution f of x minus ct. Experience tells them this function perfectly satisfies the second derivatives required by the wave equation.
I mean, whatever works, right?
But the mathematics also offer a second valid solution. The equation perfectly accommodates a function of f of x plus ct.
Meaning a wave traveling in the exact opposite direction. Because if time moves forward, distance has to move backward to keep the equation balanced.
Precisely. The most general solution for a one-dimensional wave is simply the sum of two arbitrary functions, one moving forward, one moving backward.
But Maxwell's equations also dictate a critical piece of geometry here, right?
They do. For these plane waves, the electric field is strictly at a right angle to the magnetic field. Furthermore, both of them are at right angles to the direction the wave is actually traveling.
So if the wave is shooting straight forward toward you, the electric field might be oscillating up and down, while the magnetic field is oscillating left and right.
They are locked in this perpendicular forward-marching dance.
Okay, so we started with a simple flat wave moving in one dimension to understand the rules. But the three-dimensional wave equation allows for a superposition of these plane waves moving in every possible direction simultaneously.
Yes, and if we connect this to the bigger picture, this is where the linearity of Maxwell's equations becomes the absolute hero of the story.
Because the equations are linear, there are no cross terms. The waves don't multiply or twist each other up.
That is physically why the dense traffic jam of waves in your room doesn't just devolve into white noise.
Thank goodness for that.
Because of that linearity, you can have infinite plane waves crossing through the same space at the same time. The radio waves from the local jazz band don't physically crash into or destroy the infrared waves radiating from your body.
And neither of them disrupts the incredibly faint, delicate signals arriving from the Mariner 2 probe passing Venus.
They all just slide right through each other, independently obeying the wave equation.
The text mentions that when we build a giant radio telescope, we are basically just building a highly sensitive trap to catch these tiny wiggles of electric and magnetic fields that have been traveling undisturbed for billions of years.
It's staggering. Everything humanity knows about the cosmos, all of astronomy, is just an inference drawn from studying these unendingly complex, overlapping undulations of fields reaching the Earth.
But, with billions of these signals passing through your head right now, the natural instinct is to try and picture what that actually looks like in the air around you.
Oh, and this leads to a rather profound psychological barrier.
Yes. My brain hits an absolute wall. And honestly, reading Feynman's candid confession here was incredibly validating.
It is comforting, isn't it?
One of the greatest physics minds in history admits that even he couldn't truly picture the electromagnetic field. He says that when he tries to imagine the field swishing through space, he just sees vague, shadowy, wiggling lines with E's and B's written on them.
And the moment he tries to look closely at the arrows on those lines, the whole mental image just evaporates.
So if even Feynman can't do it, what hope do we have?
Well, he acknowledges a terrible inherent confusion between the mathematical symbols we use to describe the reality and the physical reality itself.
He uses this brilliant comparison to invisible angels. He argues that imagining a room full of intersecting electromagnetic waves is actually much harder than imagining a room full of invisible angels.
Right, because to imagine invisible angels, you just picture regular angels, wings, halos, robes, and then you abstract them by turning their opacity down to zero. You make them transparent.
But you cannot do that with an electromagnetic field. There is no visible physical approximation you can just turn invisible. It has no mechanical equivalent.
And this lack of a mechanical equivalent was a massive stumbling block in the history of physics. Early Victorian scientists, brilliant minds like Maxwell and Faraday, desperately craved a physical, mechanical picture.
Right, they imagined the universe was filled with a rigid, invisible substance they called the ether.
Yes. They tried to frame electromagnetic fields as physical stretchings, twistings, or gears grinding within this ethereal jelly.
Because if it's jello, you can picture it. You can imagine jello jiggling. It gives your brain something physical to hold on to.
Exactly. But clinging to that physical jelly was actually actively hindering progress. The universe simply doesn't have an ether. We are strictly limited to the mathematical abstractions.
And Feynman uses this to highlight the straitjacket of scientific imagination.
That's a great term for it.
I am obsessed with that concept. People usually think of imagination as this boundless, unconstrained ability to dream up wild fantasies, but scientific imagination is an incredibly rigorous, almost punishing game.
It really is. You have to imagine something completely novel, but it must remain perfectly consistent with every single known physical law.
You are entirely restricted by the uncompromising math of how nature actually works. It is a straitjacket.
It demands extreme discipline. You cannot permit yourself to imagine a field moving faster than light or a bundle of field lines that magically vanishes if you try to run alongside it.
But I have to ask, does it feel a bit disappointing to know that even the greatest physicists can't truly see these waves and we just have to trust the math? It feels a little isolating.
It might feel isolating initially, but abandoning the mechanical picture opens the door to a much deeper structural kind of beauty, intellectual beauty.
Okay, tell me more about that.
The text offers a wonderful analogy about a rainbow. When you look at a rainbow, your eye immediately processes the beauty of the colors. But how would a blind person appreciate that same rainbow?
Well, it can't process the visual spectrum.
Right, but a blind scientist could build an instrument, a spectrophotometer, to measure the intensity of the radiation at different angles and wavelengths.
Oh, I see.
They could produce a graph, like figure 20-5 in the chapter. This graph would show a steady, flat line that suddenly spikes with a distinct bump in intensity at specific angles.
And at 40 degrees, the bump appears at the wavelength we humans call green. At 42 degrees, the bump shifts to the wavelength we call red.
Exactly. So the blind scientist is seeing the exact structure of the rainbow through the data. And the graph actually contains far more precise, objective detail than the human eye can even perceive.
That is beautiful.
We have to learn to find the same profound beauty in the mathematical curve that we find in the visual colors. And there is an even deeper beauty lurking in the equations themselves.
What kind of beauty?
If you look closely at the wave equation, there is a perfect, elegant regularity in how the spatial coordinates, x, y, and z, and the time coordinate, t, appear together.
Oh, right. They all fit together perfectly symmetrically in the math.
That symmetry isn't just a mathematical parlor trick. It is a massive, blinking neon sign pointing to the underlying nature of reality.
It suggests that space and time are fundamentally intertwined in a four-dimensional geometry.
Yes. That simple symmetry in Maxwell's equations directly paves the way for Einstein's special theory of relativity. The inability to draw a simple picture forces us to look deeper and discover the actual structural beauty of the universe.
Wow. But even if we embrace that mathematical beauty, there's a physical reality we haven't touched yet. We've been using these flat, one-dimensional plane waves to build our understanding.
Right, the infinite sheets.
But in the real world, you don't have infinite flat sheets of current sitting in your living room. The sources of electromagnetic waves are tiny, localized things, accelerating electrons in an antenna. They are more like dropping a pebble into a pond.
Yeah, and when a localized source creates a wave, it doesn't travel outward as a flat plane. It spreads out in all three dimensions simultaneously, expanding like a spherical bubble.
Here's where it gets really interesting. The wave equation still holds true, but the math has to evolve to handle the geometry of a bubble.
Exactly. For our flat plane wave, the amplitude, which is the intensity of the wave, stayed perfectly constant as it traveled forward forever.
But for a spherical wave, the solution is represented as our familiar function, f of t minus r over c. But now the entire thing is divided by r, and r is the radial distance from the source.
As the wave pushes further out into space, the distance r gets larger. Because it's in the denominator, the overall amplitude of the wave gets smaller. It drops proportionally to 1 over r.
Figure 20-6 visualizes this. The wave's shape flattens out and weakens as it expands. This is exactly why the Wi-Fi router in your living room gives you a terrible signal when you're out in the driveway.
The physics of it demand that the energy gets diluted. It comes down to basic energy conservation.
Makes sense.
The energy density of an electromagnetic wave is proportional to the square of its amplitude. As that spherical bubble expands, its total fixed amount of energy has to be smeared over a larger and larger surface area.
And the surface area of a sphere grows as r squared. So to keep the total energy constant, the energy density at any given point must drop as 1 over r squared.
Therefore, the amplitude itself drops as 1 over r.
The math perfectly mirrors the physical reality of the diluted energy. But here is where Feynman highlights something deeply unsettling. Just like the one-dimensional math allowed for a wave traveling backward, the spherical math perfectly allows for a second solution.
Oh, yes. A function of g of t plus r over c, all divided by r.
Meaning an inward traveling spherical wave, which is mathematically flawless but physically insane.
It is pretty wild to think about.
It's a reverse ripple. Imagine dropping a stone in a pond, but instead of ripples spreading outward, a giant circular ripple forms at the distant edges of the pond, perfectly converging inward, getting higher and faster until it violently ejects the stone out of the water and into your hand.
Right. But in our universe, waves proceed outward from sources. We have never observed an electromagnetic wave spontaneously generate from the infinite reaches of empty space and perfectly converge onto a charge just as it begins to move.
But if the pond doesn't violently eject the stone, we must just manually throw that mathematical solution in the trash, right?
This raises an important question. We discard it based entirely on human experience, but Feynman is very careful to point out the philosophical cost of doing that.
What do you mean?
By manually throwing out the inward traveling wave, we are actively removing the time symmetry that inherently exists in Maxwell's equations. The pure mathematics of electrodynamics do not care which way time flows.
Backward in time is just as valid as forward in time to the equations.
Exactly. We are imposing our physical reality, our arrow of time, onto the pure math.
There is one more bizarre mathematical hiccup with the outgoing spherical wave. The formula divides by r. If you trace that wave all the way back to its origin exactly at the source, r equals 0.
You divide by 0.
The formula blows up to infinity.
It looks like a mathematical breakdown, but it is actually a profound proof. It means we haven't actually solved the wave equation for completely empty space.
Oh, I see.
The fact that the formula hits infinity at the origin proves that there absolutely must be a source, a physical charge or a current, sitting at the origin to generate the wave in the first place.
Just like an electric field potential that drops as 1 over d dictates, there is a point charge sitting at the center.
Yes. The mathematical mistake at 0 is actually the universe demanding a physical cause.
It is brilliant. So let's bring this all back to you, the listener, sitting in your room. The seemingly empty space around you is actually a vibrant, chaotic, three-dimensional symphony.
It is packed with plane waves and spherical waves, all sliding through each other without interference, thanks to the linearity of the physics.
Each one of those waves carries a perfectly detailed, backward-drawn memory of the accelerating charges that birthed it, whether that charge moved a microsecond ago in your wall socket or billions of years ago in a remote, swirling galaxy.
As they spread, they dilute in power, governed by strict mathematical rules that are beautiful, perfectly symmetrical, and entirely unimaginable to the human mind.
It completely reframes what we consider to be reality. The invisible fields overlapping in your room right now are just as physically real and just as deeply structured as the chair you are sitting on.
Absolutely.
But I want to leave you with a final lingering thought. Think back to that discarded inward-traveling spherical wave, the reverse ripple.
The one we threw in the trash.
Right. We threw it out because our physical experience tells us waves only move outward. But the pure foundational mathematics of Maxwell's equations perfectly allow for a wave to travel backward from the infinite reaches of the universe and flawlessly converge onto a single point just as a charge begins to move.
The math works perfectly.
So, what does that say about the true nature of time? If the foundational equations of the universe themselves don't care about the difference between the past and the future, why does the physical universe force us to choose just one direction? Keep an eye out for those invisible angels in your room. We'll catch you on the next deep dive.
If you are looking at a light bulb right now, well, you aren't actually seeing it right now.
Right, definitely not.
Because the universe enforces this incredibly strict speed limit on information. The speed of light. So you are literally always looking at outdated information.
Yeah, even if that bulb is just sitting across the room from you.
Exactly. You are seeing it as it was a few nanoseconds ago. So here is the paradox we're going to explore in this deep dive. If you physically move that bulb, how does the universe actually know to update your eyes?
It's a massive question.
Right. Like how does a tiny wiggling physical object, a charge, actually manufacture a wave that detaches, travels across the vacuum of space, and hits your retina?
I mean, that is essentially the ultimate question of classical physics. When you move an electron here, how does an electron over there know to get out of the way a moment later?
Yeah.
It's this profound mechanism that we just take for granted every single time we see a reflection or, listen to a radio.
And unlocking that exact mechanism is our mission today. We're jumping straight into the heart of Richard Feynman's famous physics lectures.
The holy grail for a lot of physics students.
Oh, absolutely. Specifically, we're looking at Volume 2, Chapter 21. We're going to unpack the incredibly dense, honestly intimidating math of electromagnetic theory and turn it into intuitive physical reality for you.
Which is definitely needed because the math gets heavy fast.
It really does. But we will figure out how a wiggling charge actually creates light. We'll avoid a mathematical trap about moving charges that ensnared some of the absolute greatest minds of the 20th century.
That part is fascinating.
And we'll see how one of the most mind-bending concepts in modern physics was actually hiding in plain sight in the 1800s.
So to understand how any of this works, we really have to start with that time delay you just mentioned.
Right, the nanosecond delay.
Yeah. Feynman introduces this as the retarded distance and the retarded time in his first figure. If you want to calculate the electric field at a specific location, let's just call it point A.
Okay, point A.
You cannot plug the charge's current position into your equations. It just won't work. You have to look at where the charge was at the exact moment the information left it to travel to point A.
So imagine you are looking up at the night sky, right?
Yeah.
At the star Sirius.
Yeah.
It's about, what, 8 light years away?
Give or take, yeah.
So you aren't seeing where Sirius is today. You are seeing where it was 8 years ago. The gravitational and electromagnetic pull you feel from Sirius is literally pulling you toward its old location.
Exactly. You are interacting with a ghost of its past.
But if I apply that logic to, say, an electron moving past me in a copper wire, shouldn't its electric field lag awkwardly behind it?
Like a wake behind a boat.
Yes. If the universe is always working with this outdated information, wouldn't a moving charge drag its field behind it like a comet's tail?
That is a very natural assumption to make. And it's the exact paradox Feynman addresses by breaking down the electric field equation into 3 distinct pieces.
Okay, 3 pieces.
Right. The first piece is exactly what you just described. It's called the retarded Coulomb field.
The retarded Coulomb field.
Yeah, it's the baseline static electric field radiating from where the charge used to be. So, yes, there is absolutely a fundamental lag built into the system.
Okay, but I mean, if that were the whole story, physics would be a complete mess, wouldn't it?
Oh, totally.
A moving electron would always be pulling things toward its past position. That would create these massive energy imbalances everywhere. So how does nature compensate for that lag?
By using the second term in the equation. And this acts like a cosmic version of predictive text.
Predictive text, like on a smartphone.
Exactly like that. The universe essentially takes the rate at which the field is changing and it multiplies it by the time delay.
Okay.
It linearly extrapolates the field to guess where the charge should be right now. That's assuming it just kept moving at a constant, steady speed.
Wait, hold on. Predictive text assumes you're going to finish the word you started. Are you saying the universe assumes the electron maintains its velocity and artificially bends the field to point to a position the electron hasn't even proven it has reached yet?
That is exactly what the math shows. It's wild, but it's true.
That is insane.
If the charge is moving smoothly, this velocity correction term almost perfectly cancels out the retardation effect.
So it hides the delay.
Yes.
Hmm.
The field lines point directly to the instantaneous position of the charge, even though the definitive proof of that position hasn't technically arrived at your location yet. The delay is entirely masked by the prediction.
That feels like nature is cheating.
It really does.
But it also raises an obvious problem, I think. What happens when the predictive text is wrong?
Ah, right.
Like, what if the charge doesn't keep moving smoothly? What if it stops or turns?
Then we get to the third term in the equation, and this is the star of the show for this deep dive. The third term is entirely dependent on the charge's acceleration.
Okay, acceleration, not just speed.
Right. If the charge speeds up, slows down, or changes direction, the predictive text fails. The field has to rapidly correct itself.
So how does a mathematical correction physically manifest in the real world? Like, let's say I'm holding a positively charged sphere.
Okay, you've got the sphere.
And I suddenly jerk it to the right. What actually happens to the field lines radiating out of it?
So think of a field line like a long, taut rope connecting the charge to an observer far away.
Got it.
If you walk smoothly, the whole rope just slants, and the observer can easily guess where you are based on the angle. That's the predictive text working.
Sure, just a straight slanted rope.
But if you violently jerk your end of the rope, a sharp kink forms in it.
Like a wave traveling down it.
Exactly. That kink travels all the way down the rope until it hits the observer. That traveling kink, that sudden violent correction in the field line caused by your acceleration, that is light.
Oh, wow. That makes so much more sense than just calling it an electromagnetic wave.
It's a very physical way to picture it.
Yeah, light is the physical snap of a field line updating its information. That is brilliant. So, okay, that handles a single isolated point charge.
Right.
But if we want to understand a radio antenna or a light bulb or a star, we are dealing with one charge. We're dealing with trillions of them.
Trillions upon trillions.
So how do we scale this up? Because Feynman calls this next mathematical step the center of the universe of electromagnetism.
To scale it up, we use what's called the superposition principle.
Superposition.
Yeah. The beauty of classical electromagnetism is that fields don't bounce off each other. They just add together.
Okay, they just stack up.
Exactly. To find the total field of a complex object, you just chop that object up into microscopic volume elements. You calculate that delayed point source spherical wave for each tiny element, and you add them all up.
That sounds like massive, relentless bookkeeping.
It is entirely a bookkeeping problem.
You have to map out the density of the charges to get the scalar potential, right? Which is essentially the voltage landscape.
Right, it's like a pressure map of the electric push and pull.
And then you have to map out how those charges are physically flowing to get the vector potential.
Which is more like mapping the currents in a river.
Yeah.
And crucially, you have to factor in the specific time delay for every single point in that volume.
Because each point is a different distance away.
Exactly. If you know the charge density and the flow of current everywhere, and you account for the retarded time to your observation point, you can describe any classical electromagnetic phenomenon in the universe.
So if superposition is the blueprint, let's actually use it to build something real. Let's look at an oscillating dipole.
Classic example.
For you listening, imagine a positive and negative charge, and one of them is wiggling rapidly up and down, like a classic radio antenna.
Yep.
I want to look at how the energy travels here, because there's a fundamental difference between a static field and a radiating field.
A huge difference.
If you measure a static electrical field, its strength drops off inversely as the square of the distance.
Right, 1 over r squared.
So if you move twice as far away, the field isn't twice as weak, it's 4 times weaker. It fades incredibly fast.
Which is exactly why magnets don't pull on your refrigerator from across the kitchen.
Thank goodness.
The static energy diffuses outward across the surface area of an expanding sphere, spreading thinner and thinner very quickly.
But light, which is just that kinked field line we talked about, it travels from galaxies billions of light years away and still has enough energy to trigger a sensor in the James Webb Space Telescope.
It's amazing when you think about it.
Its strength only falls off as 1 over the distance, not the distance squared. So why does simply wiggling a charge completely change the geometry of how its energy fades into space?
Let's go back to a tactile analogy. Imagine you are holding a very long bullwhip.
Okay, a bullwhip.
If you just pull the handle back, creating tension, that tension is like a static field. The further down the heavy leather whip you go, the less you feel that direct pull.
Because the energy is absorbed by the mass of the whip itself.
Exactly. That's your inverse square drop-off.
Right, the static pull just doesn't carry far.
But now, give the handle a sharp oscillating flick. You wiggle it up and down, you've created a kink in the leather.
Just like the field line.
Right. That kink doesn't stretch out and diffuse like the static tension. It maintains its sharp shape, rolling over itself, carrying that specific packet of kinetic energy all the way to the tip with very little loss.
Wow.
By wiggling the charge, the variations in time at the source become steep variations in space as the wave travels.
So the energy isn't spreading out like a balloon inflating. It's riding the sharp slope of the wave.
Exactly. And when you take the mathematical derivative of this wave to find the actual magnetic field, you are measuring that slope.
Oh, because derivatives measure the rate of change.
Yes. The rapid wiggling creates incredibly steep spatial gradients, sharp kinks. The derivative amplifies those steep slopes, allowing the radiation field to survive over vast distances, fading only linearly as 1 over the distance.
That entirely shifts how I picture light. Wiggling doesn't just push the field, it crumples it into these steep rolling kinks that carry energy farther.
It's a very elegant geometric solution.
But what about right up close to the wiggling charge? Like inside the antenna itself, does it still act like a bullwhip?
This is where nature gets incredibly elegant. Close to the charge, the static rules, like the Biot-Savart law for magnetic fields, they actually work perfectly.
Wait, I have to stop you there.
Yep.
We just spent this entire time establishing that there is a strict time delay, and that wiggling creates these traveling kinks. Why would the instantaneous static laws work right next to a wiggling charge, shouldn't there still be a tiny delay?
You'd think so, wouldn't you? But remember our predictive text, the velocity correction term.
Oh.
When you are very close to the charge, the time delay is incredibly short. And because the delay is so short, the predictive text is phenomenally accurate. If you break the wave down mathematically using what's called a Taylor series expansion, you find that the predictive correction perfectly mirrors the static field equation. The first-order effects of the delay perfectly cancel themselves out.
So nature hides the lag.
Completely. It leaves you with a near field that looks almost exactly like the instantaneous static theory.
So close up, the universe's guess is so good you can't even tell it's guessing.
Exactly.
But further out, the guess fails, the field snaps, and you get light. That is beautiful. But let's push this model even further. Wiggling in place is one thing. What if the source of the field is hurtling directly at us?
Okay, moving charges.
Yeah, this brings us to a specific trap that Feynman warns about in the text.
It's a mathematical trap that genuinely caught a lot of early 20th century physicists off guard, because it completely breaks your common sense.
Let's lay out the trap for everyone. If you want the total potential of a moving electron, your common sense says you just measure its charge density, integrate it over its volume, and you get the total charge.
Sounds totally reasonable.
But Feynman states definitively in the text, quote, "It is wrong," unquote. Why is adding up the charge of a moving object wrong?
It goes right back to the illusion of now. Remember, we are integrating over a retarded time. Your mathematical integral has to account for the delay of every single point on that electron.
Okay, every single point.
So imagine your integral as a scanner sweeping over the volume of the charge from back to front.
I pictured this exactly like taking a panoramic photo on a smartphone.
That's a perfect analogy.
You slowly pan the camera across a street. But suppose a car happens to be driving through the frame in the exact same direction you're panning.
Right, the camera sensor sweeps and the car moves along with the sweep. The camera ends up capturing the car for a much longer time than it should.
Yeah, in the final photo, the car looks like a bizarre, stretched-out limousine.
Exactly.
But I have to push back here. In a photograph, it's just a visual distortion. We're talking about the fundamental properties of the universe. If the mathematical volume of the electron stretches out like a limousine, doesn't that magically create more charge out of nowhere?
It sounds like it, doesn't it?
Doesn't that violate the conservation of charge? You can't just invent more electron?
You aren't creating more charge. You are experiencing the charge's effect over a longer apparent period. The inherent charge of the electron remains absolutely identical.
Okay, so why does the math change?
Because it is writing its own delayed signal toward you, the density of the field lines hitting you piles up. To your perspective as the observer, the effective volume during the integration is stretched. It essentially hits you harder than it would if it were standing still.
Wow. So how do physicists fix the sweeping scanner problem?
They introduce a crucial correction factor into the integration, leading to what are known as the Leonard-Weichert potentials.
Leonard-Weichert potentials. Okay.
You take the total charge and you divide it by a factor of 1 minus the velocity of the charge directed toward you over the speed of light.
Let me think about that. So if the charge is flying at you, its velocity is positive,
Right.
making the denominator smaller, which mathematically inflates the potential you feel.
Precisely. The Leonard-Weichert potentials perfectly compensate for the panoramic stretching effect. That gives you the true electromagnetic potential of a moving point charge.
Okay, so we've fixed the panoramic trap. We've accounted for the retarded time. We've pushed Maxwell's classical equations to handle a charge moving at a constant, uniform velocity.
We really have.
But in doing all of this perfectly classical math, we've accidentally stumbled into something entirely different.
Oh, yes. We've set the stage for one of the greatest reveals in the history of science.
Walk us through this final section because it fundamentally changed how I view physics.
So Feynman takes these corrected Leonard-Weichert potentials and applies them to a very simple scenario. A single charge moving at a constant velocity past an observer. He sets up the algebra to find the potential at a specific point in space and time. To do this, he has to substitute variables, replacing the retarded time with the current time and the velocity.
It sounds messy.
It is a heavy algebraic grind, expanding terms, factoring, but it is just algebra.
Right. There are no new physics assumptions here. No quantum mechanics, no modern twists. It's just grinding through the classical equations Maxwell gave us in the 1860s.
None at all. But as you collect the terms and simplify the equation, the algebra naturally contorts itself into a very specific structure, and suddenly, Sitting right at the front of the equation, a wild factor appears.
Here it comes.
It's 1 over the square root of 1 minus the velocity squared over the speed of light squared.
For anyone who has ever watched a documentary on Albert Einstein, that term sets off massive alarm bells.
Oh, absolutely.
That is the Lorentz transformation. That is the core mathematical engine of special relativity.
Yes, it is. The math that dictates time dilation and length contraction naturally falls right out of a classical electromagnetism equation.
That is so crazy. We usually think of relativity as this bizarre modern framework that Einstein had to invent to fix classical physics because classical physics was broken.
Right, that's the standard narrative.
But this derivation proves that relativity wasn't a new rule slapped onto physics at all. It was fundamentally baked into the laws of electricity and magnetism half a century before Einstein even published his papers.
We just had to do the math carefully on a moving charge to see it. Think about Isaac Newton's laws of mechanics. Newton assumed that gravity and forces communicated instantaneously across the universe.
No speed limit.
Right. Because of that false assumption, Newton's laws broke down at high speeds and had to be fixed by relativity.
But Maxwell's equations already knew about the speed limit.
Exactly. Maxwell's equations never needed to be fixed. Because the finite speed of light is built into the very foundation of electromagnetism, the equations have to protect that speed limit.
It's non-negotiable.
Yeah. If the speed of light is an absolute constant, then the variables around it, space and time, they have to yield. They have to warp and stretch to keep the speed of light constant for all observers.
So the coordinates in the electromagnetic potential naturally stretch and compress.
Not because we assumed relativity, but because the finite speed of electromagnetic information demands it.
So relativity wasn't a revolution that destroyed classical electromagnetism. It was an unavoidable logical consequence of it.
Beautifully said.
The universe gave us the answer key in the 1860s, and we just didn't realize we were looking at the fabric of space-time itself.
It shows that physics isn't just a collection of isolated rules, it is a deeply interconnected web. A simple time delay in an electric field ultimately forces space and time to be relative.
Let's pull all of this together. We started with the unavoidable fact that information has a speed limit, plunging us into a universe governed by retarded potentials, where we are literally always looking into the past.
Right.
We discovered that nature uses a velocity correction, a predictive text, to guess where a moving charge is, essentially masking the delay.
And when that predictive text fails because of acceleration, the field line snaps. That traveling kink is what we experience as light.
We saw how wiggling a charge creates steep spatial gradients, the flick of the bullwhip, that allow energy to travel across galaxies without rapidly fading.
Fading as 1 over r, not r squared.
Right. We navigated the panoramic photo trap of the Leonard-Weichert potentials, learning that a moving charge hits you with a denser field simply because it rides its own delayed signal.
Like the stretched-out limousine.
Yes. And finally, by just trusting the classical math of a moving charge, we watched the Lorentz transformation naturally emerge, proving that special relativity was hiding perfectly intact inside Maxwell's equations all along.
It fundamentally changes how you perceive the space around you. A wiggling electron is not just a localized event. The rules governing its behavior dictate the geometry of reality itself.
So for you listening, imagine you are looking up at the night sky later tonight, or just staring at the glow of your screen right now. Remember what you were actually witnessing. You are watching the universe continuously, painstakingly calculating the delayed acceleration of countless wiggling electrons, setting those steep, kinked spatial gradients across the void to hit your eyes.
It's a lot of math happening right in front of you.
It really is. But I want to leave you with a final thought to ponder, a scenario that pushes everything we've learned today to its absolute breaking point. We know the universe uses that correction term to linearly extrapolate a charge's motion, guessing its current position to fix the time delay.
Right, the predictive text.
It confidently points the static field toward where the electron should be. But what happens if a distant charge violently reverses direction, and you are trapped inside the time delay? For a brief, agonizing moment, the electromagnetic field interacting with your body is being projected based on a reality that no longer exists.
Oh, wow.
The universe's predictive text has lied to you. Think about the physical shock waves in the fabric of space that must ripple outward when an electron changes its mind, and reality frantically has to snap the field lines back into place to correct the error. Thanks for exploring the intricate machinery of the universe with us on this deep dive. Keep questioning the physical world around you. Imagine plugging your laptop into the wall and Instead of the internal components draining that power to run your screen or whatever, they actually start generating power out of thin air.
Right, actively feeding energy back into the system.
Like magic. It sounds completely impossible, but by the end of today's deep dive, you are going to see how circuits trick the universe into doing exactly that.
It really is a fascinating trick.
It is. So today we are looking at a pretty massive stack of physics notes and engineering sources. Specifically, we're focusing on Chapter 222 of our underlying physics text on alternating current, or AC circuits.
Yeah, that chapter is dense but incredible.
Our mission here is to totally deconstruct the anatomy of an electrical circuit. We want to take something that seems so mundane, like a coil of wire or battery, and show you how these basic building blocks create the staggering complexity of modern electronics.
Right, everything from smoothing out your computer's power supply to the invisible magic of radio waves.
Exactly. So if you're trying to understand the guts of your computer, or just want to know how the universe transports energy, this deep dive is going to connect those dots for you.
And it's a journey that really requires us to totally change how we look at the physical world. I mean, if you open up a car engine or look at a city's power grid, you just see chaos.
Oh, yeah, total chaos.
Right. Friction, heat, overlapping variables everywhere. But to understand a massive, complicated system like a radio receiver, we first have to pretend the real world is much simpler than it actually is.
Which brings us to the spherical cows of electronics.
I love that phrase.
Right. For anyone who hasn't heard that joke, physicists love to simplify incredibly complex problems by imagining things like perfectly spherical cows floating in a vacuum.
Because it makes the math easy.
Exactly. It makes the math so much easier. In electronics, our sources outline our own versions of this. Let's put our passive players on the board first.
Okay, let's set the stage.
So we have the inductor, which is just a coiled wire. We have the capacitor, which is basically two parallel plates separated by a gap, and the resistor, a chunk of material that fights electrical flow.
Right, the fundamental trio.
But to understand how these interact with alternating current, where the current is constantly reversing direction, we have to talk about impedance.
Yeah, impedance is key here. Think of impedance as the overarching concept of resistance, but upgraded for a world where current changes direction.
Upgraded how?
Well, it measures how much an element pushes back against alternating current. But because that current is sloshing back and forth like a wave, impedance isn't just about how hard the component pushes, it's also about timing.
Okay, timing. Let me see if I can picture this. It's like pushing a kid on a swing.
Oh, that's a great way to look at it.
Right, because if you push at the exact right moment, when they're at the peak of their arc, it takes very little effort. You are perfectly in sync.
Yeah.
But if your timing is off, and you try to push while they are still swinging backward towards you, you face a massive amount of resistance. You're fighting the current.
That is a perfect physical analogy. In circuits, we call that timing phase.
The phase. Got it.
Right, so a component might not just resist the current, it might delay it or shift it out of sync with the voltage. That combination of pushing back and shifting the timing is what we call impedance.
Okay, well, let's unpack this a bit more, because my brain immediately throws a red flag when I look at our sources.
Uh-oh. What's the red flag?
Well, the text talks about treating these components as perfect mathematical objects. But if you have an inductor, like a real physical coil of copper wire, that wire has to have some baseline electrical friction, right?
Oh, absolutely it does.
And the magnetic field it creates when current runs through it, that field has to leak out into the space around the coil, doesn't it?
You are absolutely right to question that. A real coil of wire is a messy, complicated object.
Super messy.
And that is precisely why engineers and physicists use the concept of lumped elements.
Lumped element.
Yes. We deliberately separate what happens inside the component from what happens outside at its connection points.
Oh, I see.
By pretending the wire itself has zero friction and that all the magnetic fields are perfectly trapped inside a tiny box, we create an idealized component. We ignore the terrifying complexity of the fields swirling inside the object.
So we basically draw a black box around the messiness and just look at the terminals.
We do. We only care about the relationship between the current and the voltage at the two little wires sticking out of it.
That is so convenient.
It is. And when we apply that black box thinking to extreme conditions, we get incredibly elegant behavior.
Like what?
Take a look at what happens at zero frequency.
Okay, zero frequency just means the current isn't alternating at all.
Right. It's pushing constantly in one direction, direct current or DC. An ideal inductor only responds to changing currents.
Oh.
So if you feed it a steady, unyielding DC current, it stops acting like a coil entirely. To the circuit, it acts like a plain, straight wire. Its impedance drops to zero.
And a capacitor does the exact opposite. Because a capacitor is essentially a physical gap between two plates.
Exactly.
If you apply a steady DC current, the electrons rush in, fill up one plate, and then they just stop. They can't jump the gap.
They're trapped.
So at zero frequency, a capacitor is a broken bridge, an open circuit. The impedance is infinite.
While the resistor just sits there, completely indifferent to the frequency, it acts like a narrowed pipe, resisting the flow equally whether the current is steady DC or sloshing AC.
All right, so we have our passive players sitting on the board. They are the obstacles.
The lumps in the road.
Right. But they don't do anything on their own. We need something to push the energy through the pipes. We need generators, and we need rules for the traffic.
So let's talk about those active pushers. The sources detail two main types. You have chemical cells, like the battery in your flashlight or your phone.
Which are wild in their own right. A battery works because heavy negative ions and lighter positive ions diffuse through chemicals at different speeds, doesn't it?
Yeah, that difference in speed causes a traffic jam of charge on one side of the battery, which builds up the electrical pressure or voltage that powers your device.
It's literally just a chemical traffic jam. That's amazing.
It really is. The other type is the mechanical generator. And this is where you encounter a really profound mechanism. Think of a generator as a coil of wire rotating inside a magnetic field.
Okay, this brings up a major paradox in the source text that completely tripped me up at first.
Oh, the internal electric field thing.
Yes, because the text states that inside a perfect conductor, there is no electric field.
Right.
If there were an electric field, it would cause an infinite, instantaneous flow of free electrons until the field canceled out. So if this perfect coil of wire is spinning through a magnetic field, how does a voltage even get generated?
It seems like a total contradiction.
Exactly. If the internal electric field is zero, what is pushing the electrons out to the circuit?
It is one of the most common misunderstandings in physics. The rule isn't actually that the electric field must be zero.
Oh, it's not.
No. The actual rule is that the total force acting on any charge inside that perfect conductor has to be zero.
Okay, total force. Let's break that down.
If the wire is just sitting on a table, not moving, then sure, the electric field inside it must be zero. But in a generator, you are physically grabbing that wire and violently dragging it sideways through a magnetic field.
Right, it's in motion.
And when you drag a free electron through a magnetic field, the field exerts a physical force on it, pushing it sideways down the length of the wire.
Oh, wow. So the physical motion of dragging the wire is literally sweeping the electrons along the copper path.
Yes. The charges are being shoved to one end of the wire by the magnetic field. This creates a pileup of electrons at one end and a deficit at the other.
And that pileup creates its own internal electric field.
Precisely. Which pushes back against the magnetic shove until the two forces perfectly balance out. The total force becomes zero. This is the E plus V cross B equals zero equation in the text.
That makes so much sense now.
And if you follow that balanced internal electric field all the way out to the stationary terminals of the generator, you have a potential difference. You have a voltage.
The mechanical sweat and effort of spinning that coil is being translated directly into electrical pressure. It's brilliant.
It's a very elegant conversion of energy.
So now we have our active generators pushing the current and our passive lumps of metal resisting it. But the moment you connect 3 or 4 of these things together in a loop, you need a way to track where all the energy is going. You need traffic laws.
Which brings us to Gustav Kirchhoff. Kirchhoff's rules are the bedrock laws for any circuit diagram you will ever look at.
The ultimate traffic cops.
Basically, yeah. The first is the loop rule.
I love visualizing this one as a hike up a mountain.
Let's hear it.
Okay, so if you start at base camp, hike up a steep cliff, walk across a plateau, hike down a valley, and eventually return exactly to your starting point at base camp, your total change in elevation has to be zero. You end up exactly as high as you started.
The loop rule works identically for electrical circuits. If you trace any closed path through a circuit, the sum of all the voltage increases, like climbing the mountain through a battery, and all the voltage drops, like losing elevation through a resistor, must add up to zero.
Because you can't just magically gain energy out of nowhere.
Exactly. It is a direct consequence of the conservation of energy. The second law is the node rule, which deals with intersections.
Think of city plumbing for this one.
Water pipes are a great analogy for current.
Right, if you have a T-junction where 3 pipes meet, the amount of water flowing into the junction has to perfectly equal the amount of water flowing out.
You can't just have water magically disappearing at an
And
intersection.
you can't have it piling up infinitely either, or the pipes would burst.
Exactly the same for electrons. The sum of the currents entering any node or junction in a circuit must equal zero. Charge cannot be created or destroyed.
So with just those two rules, the mountain hike for voltage and the plumbing junctions for current, you can mathematically solve the behavior of any circuit in existence.
In theory, yes. But practically speaking, there's a massive catch.
There's always a catch.
If you open up the back of an old radio or look at a motherboard, you don't just see one loop and one junction. You see hundreds of resistors, capacitors, and inductors woven together in an absolute rat's nest.
Oh, totally. It's a mess of solder and wire.
Right. And if you try to apply Kirchhoff's rules to that, you end up with dozens of simultaneous equations. It's an algebraic nightmare.
There has to be a way to simplify that down, right?
There is, and it is an incredibly powerful mathematical tool called the equivalent circuit.
Okay, how does this work?
What engineers discovered is that no matter how terrifyingly complicated a network of passive elements is, even if it has thousands of components woven together, as long as you are only interacting with two wires sticking out of that rat's nest, you can replace the entire mess mathematically with just one single effective impedance.
That concept is just wild to me.
It really is a lifesaver for engineers.
It's like taking a sprawling, massive novel with hundreds of characters and interlocking plot lines, say War and Peace, and summarizing the entire thing into a single, punchy log line.
That's a really good way to frame it.
Because if you are the publisher just reading the log line on the back cover, you don't need to know about the hundreds of subplots inside. For your purposes, the log line and the 1,000-page book behave exactly the same way.
And this shortcut applies even if the circuit is active. If that terrifying rat's nest also contains dozens of internal batteries or generators fighting each other, the math allows you to reduce the entire web down to just one ideal generator connected in series with one single impedance.
So from the perspective of whatever you plug into those two wires, the thousands of components act indistinguishably from one simple battery and one simple resistor.
Yep. That ability to summarize a circuit is what makes designing complex electronics even possible for a human brain.
It's the ultimate simplification.
But to truly test if this mathematical summarizing trick actually reflects reality, our sources push us into one of the most mind-bending thought experiments in physics. We have to look at what happens to the energy.
Oh, this brings us to the infinite ladder.
It does.
But to set this up for you, the listener, we need to quickly review how our components treat energy. Resistors, as we established, are like friction. They burn electrical energy into heat.
Right. If current runs through a resistor, that energy leaves the circuit forever. It warms up the room.
But ideal inductors and capacitors don't do that, do they?
No, they don't. They have what we call purely imaginary impedance. They do not dissipate energy.
Wait, purely imaginary.
Mathematically speaking, yes. It means when the alternating current pushes into a capacitor, it builds up an electric field, essentially storing the energy like a compressed spring.
Okay, I can visualize a spring.
And when the AC cycle reverses, the capacitor acts like that spring uncoiling, giving the exact same amount of energy right back to the circuit.
And an inductor does the same thing, just using a magnetic field instead, right?
Exactly. It borrows energy from the circuit, builds a field, and then returns it all. Over a full AC cycle, inductors and capacitors burn zero energy. None.
All right, so keeping that pure heat-free behavior in mind, imagine building a circuit shaped like a ladder. The horizontal rungs of your ladder are capacitors.
And the vertical sides of the ladder connecting the rungs are inductors. We call this an LC ladder.
And the thought experiment asks us to make this ladder infinite. You keep adding rungs and side rails forever, stretching out into the void of space.
So we have an endless string of components that individually are completely incapable of permanently burning energy.
Here is the paradox that makes this so fascinating.
It really is a brain teaser.
If you hook a generator up to the front of this ladder, and neither the L's nor the C's can permanently consume power, you would intuitively think the generator wouldn't lose any energy. The power should just slosh back and forth, right?
That is the logical assumption. But the mathematics reveals a brilliant twist. It depends entirely on the frequency at which the generator is pushing the current.
Okay, so what happens?
If you drive this infinite ladder at a frequency below a specific mathematical cutoff point, the characteristic impedance of this entire infinite web suddenly shifts. It loses its imaginary spring-like quality and becomes a pure, real number.
Meaning the math says this infinite chain of non-heating components suddenly acts exactly like a giant resistor.
Precisely. To the generator sitting at the front, this endless chain of inductors and capacitors constantly and endlessly absorbs energy at a steady rate.
The energy leaves the generator and never ever comes back.
Yes.
But how is that physically possible? We just spent a whole segment establishing that inductors and capacitors cannot burn energy as heat. If the latter isn't getting hot, where's the energy going?
To visualize this, let's step away from the electricity for a second. Imagine you are standing at the edge of an infinitely large pond,
Okay, I'm at the pond.
and you drop a heavy rock into the water. A massive wave ripples outward. As that wave travels, it carries energy away from you.
Right, I can see the ripples moving away.
Because the pond is infinite, that wave never hits a shoreline. It never bounces back toward you.
So from my perspective on the shore, the energy I put into dropping the rock is just gone.
Yes. The infinite LC ladder is doing exactly the same thing. The energy isn't turning into heat. It is simply propagating down the infinite line.
Oh, wow.
The first inductor hands the energy to the first capacitor, which tosses it to the second inductor, and on endlessly.
It's an infinite bucket brigade.
Exactly. Because the line never ends, there is no wall for the electrical wave to hit and reflect backward.
To the generator at the front, sending energy down an endless, frictionless pipe is completely indistinguishable from losing that energy to a hot resistor. The energy has gone either way.
It perfectly absorbs the energy not through heat, but through infinite propagation. It's a beautiful theoretical model.
But as you might imagine, we don't have infinite space to build infinite ladders in our circuit boards.
Just a minor engineering inconvenience.
Right, we have to cut the ladder.
And when you chop that infinite ladder into a finite piece, it stops being an endless bucket brigade. It becomes something incredibly useful.
A filter.
A filter, exactly.
Let's walk through how this filter works, because this exact phenomenon is quietly powering almost every piece of technology around you right now.
It really is everywhere.
Remember that cutoff frequency we just mentioned? It turns out that inductors and capacitors are incredibly sensitive to how fast you push them.
Yeah, if you look at a finite section of this LC ladder, you calculate what is known as the propagation factor. You can think of this simply as a multiplier. As the voltage tries to move from one section of the ladder to the next, it gets multiplied by this factor.
So if your generator is pushing the current slowly below that cutoff frequency, the propagation factor is basically 1.
Right. The voltage might get delayed a tiny fraction of a second, but it doesn't lose its strength. It passes cleanly through the ladder.
But if you crank up the frequency and start pushing the current incredibly fast above the cutoff, the propagation factor abruptly drops to a fraction. Maybe a half or a quarter.
Yeah, and that's where the magic happens.
So as the high-frequency voltage tries to move down the ladder, it gets chopped in half by the first section, then chopped in half again by the second. By the time it goes through a few rungs, the high-frequency signal is completely annihilated. It gets blocked.
This specific arrangement inductors on the sides, capacitors on the rungs, creates a low-pass filter. It allows low, slow frequencies to pass through unharmed, but violently kills off high, fast frequencies.
And if you want to know why you should care about a low-pass filter, just look at the charger block plugged into your laptop.
A perfect real-world example.
The power coming out of your wall outlet is alternating current. It reverses direction 60 times every second. But the delicate computer chips inside your laptop need direct current. They need a perfectly smooth, flat, unmoving stream of power.
So the charger uses a component called a rectifier to flip the negative parts of the AC wave positive. But that doesn't make it smooth, it makes it bouncy.
It's like a series of humps.
Right. It pulses up and down violently 120 times a second. It is a very lousy, dangerous form of DC power.
If you fed that bouncy power directly into your processor, it would completely fry.
It would. But mathematically, a bouncy pulsing wave is just a smooth, flat DC signal mixed together with a bunch of high-frequency noise.
Ah, I see where this is going.
So inside your charger, that lousy power gets shoved through a low-pass filter. The filter acts like a massive shock absorber. The flat, zero-frequency DC power sails right through the filter unharmed.
But those violent high-frequency wobbles,
The filter multiplier crushes them to zero. What pours out the other end into your laptop is pure, crystal smooth power.
the versatility of these filters is just astonishing. If you simply physically swap the positions of the inductors and capacitors, putting the capacitors on the sides and the inductors on the rungs, the mathematics completely inverts. You build a high-pass filter.
Which is exactly what an audio engineer uses.
Right. If you are listening to a vinyl record, the physical motor spinning the turntable often creates a low, rumbling vibration. A high-pass filter blocks that low-frequency rumble from reaching your speakers, but lets the high-frequency vibrations of the music pass through perfectly.
And you can take it a step further. If you use more complex combinations of components for the rungs and the sides, you can create a bandpass filter.
Okay, so what does that do?
This is a filter that blocks the really low frequencies and blocks the really high frequencies, only allowing a narrow window or band of frequencies to survive.
Like tuning a radio. When you get in your car and tune the radio to 97.1 FM, you are physically adjusting a bandpass filter.
That's exactly what's happening.
Because the antenna is catching millions of different frequencies from dozens of different stations all at once. The bandpass filter kills the station at 96.9, and it kills the station at 97.3. It only lets the narrow energy of 97.1 pass through into the amplifier. It's how we isolate information from the noise of the universe.
It's beautiful engineering. But there is one final fascinating limit to look at with our ladder.
Hit me with it.
Imagine that LC filter again. What happens if we shrink the physical size of each section? We make the little inductors and capacitors tinier and tinier, packing more and more of them into the exact same physical length of wire.
So the amount of inductance and capacitance in each little rung gets microscopic.
Yes. The mathematics shows that as the size of the ladder sections approaches zero, the cutoff frequency pushes toward infinity. The ladder stops blocking high frequencies entirely.
Wait, if the sections are infinitely small, that's not a ladder anymore. That's just a solid, continuous wire.
Exactly. By shrinking our idealized components to zero, we have accidentally derived the perfect mathematical model for a continuous transmission line.
No way.
Yes. The coaxial cable that brings high-speed internet into your router isn't just a hollow copper tube.
Yeah.
Physically, it behaves as an infinite series of microscopic distributed inductors and capacitors handing energy down the line.
It's LC ladders all the way down.
Pretty much.
Okay, so using these simple blocks, we've filtered energy, we've blocked it, we've transmitted it smoothly across cities. But modern electronics demand one more massive trick.
We need to amplify.
Right, we don't just need to route energy. We need to take a whisper and turn it into a shout. How do incredibly complex quantum-level devices like transistors fit into the simple puzzle pieces we've been using?
It seems like a massive leap, right? A transistor uses the quantum physics of semiconductors. Old vacuum tubes use the physics of boiling electrons off hot metal.
You would assume we have to throw away our simple equivalent circuits and invent an entirely new framework to understand them.
Because they operate in a totally different realm of physics.
Exactly.
They do, fundamentally. But structurally, inside a circuit diagram, as long as these devices operate linearly, meaning if you double the input signal, the output signal doubles proportionally, we don't have to throw away our models.
We don't.
No, we just add one new trick, which is the auxiliary ideal voltage generator.
Okay, so we use the same puzzle pieces, but we give one piece a magical set of instructions based on what another piece is doing.
Exactly. If we want to model a transistor, we draw our normal resistors and capacitors, but we drop a fake voltage generator into the output side of the diagram.
I see.
And we write a mathematical rule that says the power this generator pushes out is directly controlled by the tiny current trickling into the input side.
Oh, that's clever. A tiny fluctuation on the input dial triggers a massive swing on the output generator.
But here is where we reach the grand reveal of this deep dive.
The moment we've been waiting for.
These devices, transistors, tubes, don't actually make energy out of nothing. They are connected to a heavy DC power supply, like a wall outlet or a big battery.
Right, they need juice to run.
And when you run the math on how they convert that DC power into an amplified AC signal, the effective impedance of the transistor takes on a truly bizarre property.
Bizarre how?
The real part of its impedance, the resistance part, becomes a negative number.
We brought this up at the very beginning of the deep dive. Negative resistance. Let's really visualize what this means.
It's a trip.
Normal resistance is friction. It slows things down and burns energy. If normal resistance is friction, negative resistance is like anti-friction.
It is an active supplier of energy.
Think about pushing that kid on the swing again.
Good analogy. Back to the swing.
The air resistance and the squeaky chain are positive resistance. If you just let go, the swing loses energy and eventually stops dead.
Right. It fades out.
The transistor acts like you standing there, pushing the swing every single time it comes back. Your push is the negative resistance. You are adding energy back into the system to exactly counter the friction.
And where do you get the energy to push the swing? From the DC power supply. The meal you ate earlier in the day is the battery.
So if you take a normal circuit that naturally loses a little energy to heat positive resistance, and you wire it to a transistor that provides the exact same amount of negative resistance,
The positive friction and the negative anti-friction cancel out. The total resistance of the circuit becomes precisely zero.
wow, and if a circuit has zero total resistance, an alternating current wave, once it gets started, will never, ever stop. It will slosh back and forth, pushed by the transistor, forever.
It becomes a perfect oscillator. This is how humanity generates signals.
Every radio broadcast, every cell phone transmission begins with an oscillator using negative resistance to create a steady, endless wave.
The clock ticking billions of times a second inside the processor of the device you are listening to this on right now, it is driven by this exact principle. A crystal paired with negative resistance, endlessly ringing like a bell that never fades.
That is genuinely profound. We started with a simple coil of wire and some basic rules about mountain hikes and plumbing junctions. We use them to realize that a horrifying rat's nest of parts can be summarized into a single black box.
And we explored how infinite ladders act like endless bucket brigades, swallowing energy without getting hot.
And it all culminated in the sheer magic of negative resistance, tricking a DC battery into pushing a swing forever, creating the endless heartbeat of the digital age.
It is a testament to the power of those spherical cows. By stripping away the messy reality and idealizing the components, we discovered the fundamental rules required to build the modern world.
And it leaves you, the listener, with one final, deeply provocative thought to mull over. We talked about how a physical wire, like a coaxial cable, is secretly just an infinite ladder of tiny inductors and capacitors handing energy down the line.
The microscopic bucket brigade.
Well, light itself is just an electromagnetic wave. When light from a distant star travels through the dead, empty vacuum of space for billions of years without losing its structure, what does that imply about the vacuum itself?
Now that is a question.
Could the completely empty fabric of the universe actually be the ultimate equivalent circuit, perfectly tuned with its own invisible inductance and capacitance to carry energy forever?
That is a beautiful mystery to sit with.
It really is. Thank you for taking this deep dive with us. Keep questioning the invisible forces powering the world around you.